Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the first chapter of our machines. Also, this will be a common chapter with network theory because wherever we have finished on network theory, that is two-port networks. After that, two topics were left, that is magnetic circuits and three-phase systems. So we will cover those common topics as well, that is common to all the branches EE, EC, IN, and few miscellaneous topics are there which will be only for EE and IN aspirants, okay, which will be prerequisites to electrical machines. So this will be the chapter 0 of electrical machines. This will be a whole marathon and make sure to watch everything. Like for EE, EC, IN aspirants, I will say you have to watch till these three topics, okay, magnetic circuits, three-phase systems and magnetically coupled circuits. After that only, this is for all the branches EC, EE, IN, and this is only for the EE and IN branch. Okay, now that was about the syllabus what we will discuss. Now we will start with the first lecture and today we will revise few things. So before starting out, I just wanted to clear this out that of course I told you that EEC IN aspirants have to watch these three topics. Mainly this will be covered till lecture 4. So after lecture 4, EE like EC aspirants don't need to watch, you can leave the video. Also here also whatever I will explain right in this lecture and in next few lectures, I will tell you where you don't need to focus much, okay, because of course in EC right, transformer is not there in the syllabus, but for me to explain the magnetically coupled circuit, a bit of basic knowledge of transformer I need to teach. Otherwise I will not be able to explain you the concept behind the magnetically coupled circuits. Okay, what does dot mean, what is the significance of dot? So to explain that I have to explain bit of transformer. Don't worry, it will not be difficult, just trust me. Okay, and I will tell you as well that I will tell at that point of time, EC aspirants, you just listen to me whatever I am saying. You don't need to do any numericals or practice anything. Just for understanding purpose, I will explain bit of transformer. You can totally just listen to it. That's it. You don't have to study that separately or something. Don't have to study that. Just whatever I am saying, just listen to me. That's it. In this lecture as well, we will revisit few concepts of electromagnetism. Okay, and we will also discuss about transformers. So for EC aspirants, just take this first lecture lightly, listen to me, okay. You don't have to worry that whether this will come in exam or not. This will not come in your examination, but it's good for you to understand because it will be helpful in magnetically coupled circuit. That's why just listen to me, that's it. You don't have to worry anything. I'm talking about EC aspirants. WIN aspirants, this is totally in the syllabus, so you have to obviously listen to me, you have to practice questions that I will tell. Okay, so in today's lecture we will first of all revise electromagnetism, concepts of electromagnetism, which we actually studied in class 11th and 12th, and of course which we have discussed in the EMFT part of EE syllabus. Also we will discuss flux for a transformer. So what happens when we apply a DC supply in a transformer? This is the most asked question in interviews in case of transformers. So this we will discuss. Trust me, you will learn something new. I'm telling you, you'll learn something new here. Even though you have studied this thing previously, you will learn something new. Then of course we will discuss about magnetic circuits and inductance. So this I have already taught in my EMFT full course. I will just quickly go through what does each terms mean. Let's first start with the magnetic field. What is a magnetic field? Magnetic field is like a closed loop lines which has no starting and ending point. Okay, whenever a current flows through a wire, it generates a magnetic field. Okay, and the strength weakens as we move away from the current carrying conductor. Okay, this we have studied in class 11, and its shape is like something rounded. Of course you will not be able to see it, you will not be able to see it or observe it, but once you place any component or a particle which is magnetically attracted, you that object will feel actually the attraction if there is a magnetic field near it. Okay, so these are my magnetic field lines. These are few properties that magnetic field lines never intersect with each other. And yeah, and whenever a magnetic pole has been generated, it will be always a dipole, that is both north and south poles together will exist. So we will just quickly revise our concepts. So this all this will be actually required in machines. Whenever we will study machines, all these concepts will be required. So do listen to me carefully. We are just revising our concepts because we already know all this, because we have already learned this in EMFT, we have already learned this in class 11, just revising the things. So another important rule about magnetic circuits is that right hand thumb rule. So what is right hand thumb rule? So if I somehow know the current, direction, I will be able to know the direction of my magnetic field. So let's say currently if I'm seeing the current is upwards, okay, so I will take my right hand, I will just curl my fingers, and the direction of my thumb will be in the direction of the uh, current. Okay, so now if I curl my fingers, what I'm observing that my fingers are curling in this direction. Okay, in the screen, if you see, it is curling in the anti-clockwise direction. Okay, in the screen, if you see, it is rotating in the anti-clockwise direction. That means the direction of the magnetic field will be in the clockwise direction. Okay, so this rule is used to find the direction of the magnetic field. Okay, so this magnetic field, how do I measure the magnetic field? So these lines are actually known as the flux lines. Magnetic field lines are actually known as the flux lines. And the more concentrated the flux lines are, then the more dense it is, right? In a particular area, if I choose, if I have more number of flux lines, then it is more dense. That means my magnetic flux density is very high. So generally the measurement metric for flux is magnetic flux density. It is what? It is the number of flux lines per unit area. Number of flux lines per unit area, that is the metric unit. That's how we measure the magnetic flux density. I will discuss about this later on as well. I will discuss about this. Okay, and what is like what are they telling here? They are telling that point your thumb in the direction of the current. So generally, right, current is not a vector quantity, current is a tensor quantity. So current as such does not have any direction. So what we do is we take the direction of this wire. So we say this wire is a small, say this wire is a length of dl. Okay, the length of the wire is dl, very small, and the direction will be along the direction of the current. So current is moving from bottom to top in the wire. So length of the like direction of the dl will be like this, top, right, top, and my fingers, like my magnetic field will rotate in the anti-clockwise direction. That's it. Okay, magnetic field will rotate in the anti-clockwise direction. Okay, so that is the direction of the current, and that is the direction of the magnetic field. That's it. That is how we use the right hand rule. So these are the terms. Okay, first term is magnetic flux density. This is known as the magnetic field lines per unit area. So field lines, magnetic field lines is measured in Weber, and area is meter square. So that's why Weber per meter square. Okay, this is the unit of field lines or flux. We can also say flux. Okay, now this is very analogous. If you remember electric field intensity, like there a term was there known as electric field intensity. Okay, in electrostats, if you remember that, it is very old. I know you have forgotten everything, but there is a term known as electric field intensity. It is analogous to that. Okay, then we have, so not electric field intensity, what I am talking, electric field density, electric flux density. Okay, electric flux density. Then we have another term known as magnetic field intensity. Now what is magnetic field intensity? So engineers actually, like this magnetic flux density is actually dependent, it is dependent on medium. If my medium is, if my medium allows more magnetic field lines to pass, so the flux density will be a different number. If my medium is very bad, like it does not pass any field lines, so it will have very bad flux density. Same like if I have a like a voltage source here, and if I have a resistor, so if the resistance value is very high, so current will be low, right? So it does not pass high amount of current. If my resistance value is low, then current will be again high, so it passes the high amount of current. So the current actually is dependent on the resistance value. Same here as well, the number of field lines actually depends on the material. Okay, how much good the material is, how much it can permit, how much magnetic field lines it can permit. But engineers actually wanted a term that is independent of this. So it does not matter wherever I am, that term should be fixed. And if I want to calculate the magnetic flux density, I will have some constant term, I will multiply with that, and I will get back this magnetic flux density. So due to that reason, another term came known as magnetic field intensity, which is independent of medium. And these two are actually interrelated with a constant. That's it. So the purpose of this term was just to get a term that is independent of medium so that engineers have easier calculation. That's it. Okay, so the relationship between the magnetic field intensity and magnetic flux density is just with a constant mu, which is known as the magnetic permeability. It is similar, if you remember, it is similar to the resistance. So resistance is rho L by A, right? So rho is the resistivity of the resistance. Same something like that. If the resistivity is very high, then it will resist the current very high. If the resistivity is low, it will not resist the current that much. So same here. Okay, if the magnetic permeability, no, it's just the opposite here. It is permeability. So if the magnetic permeability is high, the number of field lines will be more. If the magnetic permeability is low, the number of field lines will be low. Just the opposite, but like they are, I mean, they are analogous. How they are analogous, I have explained. Okay, so these are the basic terms. So whatever I've said, same thing is written, that magnetic flux density describes the influence of a current carrying conductor in its surrounding, represented by B with a vector, because it is a vector quantity. How is it a vector quantity? If you see, it has a direction, right? What is the direction? Direction is in the along the circle. So it is like AR cap. So not AR cap, E theta cap. E theta cap is the direction. If someone has studied vector calculus, they will know what I am talking about. Else you can ignore whatever I have said now. Okay. Now um, the number of, so the actual definition, the number of magnetic field lines per unit area passing normally through a surface is called the magnetic flux density. What is magnetic field intensity? It is used to measure the strength and the direction of the magnetic field at a particular point. It is independent of medium. So my relationship between the magnetic flux density and magnetic field intensity is this. This will be used in magnetic circuits. So EE and IN aspirants can remember this. EC aspirants don't need to remember this, but it's good to know. Okay, it will never be asked, but it's good to know this thing. So EC and EC aspirants, just listen to me whatever I'm saying. Okay, don't have to think that do I need to remember this formula? No, you don't need to remember this formula. Now let's understand the direction of the magnetic field if I have a circular current carrying loop. Previously we discussed when I have a linear current carrying loop, how do I find out the direction? How was the direction? Just put your thumb along the direction of the current and curl your fingers, and the fingers will tell you the direction of the magnetic field. Now here actually we will do it a bit differently. Okay, so first I will tell you the basic method, whatever we have discussed. So I will use the right hand rule. So if I use the right hand rule, I know place your thumb along the direction of the current. So at this particular point, the direction of the current is like this. So I will place my thumb along the direction of the current, and if I curl my fingers, I am saying that the current is coming towards me, right? Sorry, not the current, the magnetic field is coming towards me. So the direction will be somewhat like this, right? Magnetic field will be coming towards me. Same here, if you just curl at this particular point, the direction of the current is like this. So my thumb will be in this direction, and magnetic field will be coming towards me again, right? And going into the screen. Magnetic field will be coming towards me and going into the screen, correct? It will go into the screen. Okay, go into the screen. Same here, go into the screen. Okay, it will go into the screen. If I just place my finger, it will go into the screen, not like this, like this, go into. So if I am observing that the magnetic field is always going into the screen inside this loop, magnetic field is always going into the screen inside this loop, and it is outside, it is coming outside the screen, outside the loop. If you see, outside the screen, outside the loop. So what is the difference? Basically the difference is, instead of this doing all this business, right, individually finding the points and just curling my fingers, we can holistically find out the direction of the magnetic field. How? Just do the opposite, right? Previously what I told you that your thumb should be along the direction of the current and your finger should be along the direction of the magnetic field. That was when the coil was linear. Okay, if the coil is, if the coil is a circular kind of coil, you place your finger along the direction of the current. Okay, so the direction of the current is clockwise, so I will place my finger along the direction of the current. So I'm curling my fingers along the direction of the current, and your thumb will now give you the resultant direction of the magnetic field. So if I curl my fingers along the direction of the current, so it is going into the screen. So it is going into the screen, and we show the into the screen like this. This I have taught in my electromagnetism, so don't have to worry about this. Just I'm explaining you the basics, how to find out the direction of the magnetic field. This will not be asked in examination, but it's good to clear your basics. So this is the direction of the magnetic field. This is the direction of the magnetic field. So instead of doing that, taking thumb as the direction of the current, now I have taken the fingers as my direction of the current, and my thumb will be the direction of the magnetic field. This you will use when you have a circular kind of current carrying loop. Now let's discuss about a law known as Ampere's law. It is very similar to Gauss law. So I will just discuss with a very basic example. So let's say I have a current carrying conductor like this, and I want to find out the magnetic field at a distance r from this current carrying conductor. This conductor is carrying current I. Okay. So of course I have not discussed about Biot-Savart law, because that is totally not required. That is required in EMFT. So I have not discussed about that. Without Biot-Savart law, can you find out the magnetic field density at this point r or point P at a distance r? So what we'll do, we can observe this current carrying wire from the top. So I want to observe this current carrying wire from the top. My drawing will be very bad. Okay, ignore my drawing. I will try my best, but I will not promise. I will not promise. Okay, so I guess our eyes will be somewhat like this. I don't know how to draw the eyes. This is like an alien eye. Oh no. Okay, so our eyes are here. Okay, ignore whatever I have drawn. So my eyes are here. I'm observing from the top. So if I'm observing from the top, what I can do is I can draw the top view. So if I draw the top view, that the current is coming towards me. So how we show current? If something is coming out of the screen, coming towards me. If something is coming towards me, we show it as dot. Okay, don't have to worry about the notation. This will not be asked in your EC exam, but WA aspirants anyways have to study EMFT, so they will study it over there. So now what I observe, I have to find out the magnetic field at a distance r from this wire. Okay, at a distance r from this wire. Magnetic field at a distance r from this wire, and the current flowing is I, coming out of the screen. Okay, so now what we'll do, what does Ampere's law say? Ampere's law says that if I assume a symmetrical surface, okay, I have to calculate the magnetic field here, but the magnetic field will be some, if I curl my fingers now, magnetic field will be something like this, right? It will be same throughout this r distance. It will be same. It will be like a circular region. So if I choose a circular region like this, if I choose a circular region of radius r, okay, and I know the direction of the magnetic field will be something like this, right? This will be the direction of the magnetic field. It will be along the circle. It will be along the circle. So now what I can say is Ampere's law tells me that the line integration of the magnetic field intensity along the line, whatever line I have chosen along the curve, will be equals to the net current that flows through the surface enclosed by this line. The surface enclosed by this line, that will be the resultant. Okay, so this is my Ampere's law, basically same as Gauss law. If you remember Gauss law was as well, Q enclosed will be equals to integration E dot dl, something like that. So here also we are doing the same only. Okay, so here what is the net current that is flowing out of the surface along the enclosed by this line, circular line? It is I, right? So it is I. Now H is just proportional to B. Okay, H is just proportional to B. What is the relationship between B and H? So H is equals to B by mu. That's it. Direction will be same. Direction does not change. A mu constant is there. That's it. A mu constant is there. That's it. So now I observe that the B direction is always along the line. So this dl is the dl of the surface, right? So this B vector and the H vector, or the H vector and the dl vector, are always in the same direction. So what we do is, this is H dot dl. So what is H dot dl? H dot dl, I can write magnitude of H, magnitude of dl into cos of theta. So in our case, as both of them are parallel to each other, so they will have 0 degree angle. So theta will be 0. So it will be always integration of h dl. That's it. It will be always integration of h dl. Vector component has gone away because the angle between them is 0 degrees. That's it. Not that important for EC aspirants. I'm saying over and over again. So this will be integration of b. I can convert h into b. So h will be equals to b by mu. So it will be b by mu into dl vector, and I'm going over the whole circle, right? I'm enclosing the surface because this is a closed line integration. So I will go from what, L equals to 0 to L equals to 2 pi r, because what is the length of this whole circle? 2 pi r, right? I'm starting from here and I will go along whole perimeter, whole circumference. So it will be 2 pi r. So I will go from L equal to 0 to L equal to 2 pi r, and I know one thing, okay, this is already known to me, that the magnetic field density will be constant. If I am at a distance of r, the magnetic field density will not change. So what I can do, I can take this b out of the integration. I can take this b out of the integration. If I take this b out of the integration, b by mu into 2 pi r will be equals to I, or I can directly write that magnetic field intensity will be mu into I divided by 2 pi r. So this is a very basic famous formula for the magnetic field uh, through a current carrying wire. Okay, current carrying wire. So that is the formula. Okay, very famous formula. So I hope you have understood this basic point. Okay, and like without using any big formulas, something bad Sever's law, we have derived this. Okay, and this will not be asked in exam, but I just wanted to give you a feel how to use the Ampere's law. EE and IN aspirants will learn this in the EMFT portion of course. Okay, EC aspirants just need to observe whatever I am doing. That's it. That is more than enough. So whatever I have discussed about Ampere's law, that is written over here. No, the statements are not that important. How to use the Ampere's law is the most important part I have discussed. The very basic thing. Okay, so this is the main like equation of the Ampere's law. So previously there was B dot dl, H dot dl. Now there is B dot dl because H and B are almost same. Just a constant is there, that is magnetic permeability. Okay. Now let's discuss about the formal definition of magnetic flux. Okay, so I have already told you magnetic flux are the field lines, number of field lines. Okay, so we can measure the magnetic flux as the product of the, we can measure the magnetic flux as the product of, just hold on, product of magnetic field intensity into area. Okay, that is how we can measure the magnetic flux. So this I've already discussed, right? Here the higher the number of field lines, the more the magnetic flux will be. So when will the number of field lines will be higher? When the magnetic flux density is higher. So in per unit area I have more number of field lines, then only magnetic flux density will be higher. So it's just like vice versa, right? Whatever I'm discussing, they are going both ways. So your magnetic flux definition is very simple. It's just the product of your magnetic flux into area in the normal scalar format. In the vector format, it will be the surface integration of B dot ds. That's it. Okay, B dot ds. So units is like unit of the magnetic flux density is Weber per meter square. Also, its unit is magnetic flux density has a unit of Tesla. Okay, so we can write it as Tesla into meter square because this has a unit of Tesla and has a unit of meter square. So its unit will be Tesla into meter square, or its unit can be told as Weber. Why? Because magnetic flux density has a unit of Weber per meter square. So if I multiply meter square with Weber per meter square, it will be Weber only. Okay, which is equivalent to Tesla, like same these two units are same only. Okay, now flux through open surfaces. So for open surfaces, the magnetic flux is calculated by integrating the magnetic field over the surface area. Okay, so don't have to worry about this. How do you open surface? Open surface is something like this, right? It is just like this. It is open surface. So let's say the magnetic field flux lines are going like this. Okay, I will just draw a 3D figure, that will be better for you. So so this will be my flux basically. And how do I calculate them? Like this is the open surface. How do I calculate the flux? So magnetic field intensity is this, so flux will be whatever the area of this sheet, area into obviously B into area, that will be the flux. Okay, what is a closed surface? Closed surface is somewhat like this. It is a 3D figure, right? Closed surface will be somewhat like this. So it's like a cuboid kind of box. So whatever the flux is going, whenever there is a closed surface, the overall flux throughout the whole closed surface will always be zero. Okay, this you will learn in EMFT. Okay, I'm not discussing, I'm just giving you a idea that whenever there is a closed surface, the overall flux will be zero, because whatever flux comes in will come out. Okay, because magnetic field lines are always closed in nature, they're never like only open, they're never open. Like if, like a charge, right? Charge, if I have a positive charge here, so magnetic field lines, sorry, electric field lines will go out like this, right? It is not a closed in nature, if you remember, but magnetic field lines are always closed in nature. So if I kept a closed surface over here, if I kept a closed surface over here, whatever field lines will come in, same will go out. Okay, this you will learn in EMFT. Okay, all this base we have been building up because we want to come to this. Okay, we want to understand the flux in a transformer. So that's why we have been building all these terms. That was the reasoning behind explaining you all that. So all that won't be asked in exam for EC aspirants, but we have to understand the transformer, right? So that's why we have to understand those terms. So here we have a transformer, okay, which currently has a DC supply, I am supplying a current I in the coil, which has a number of turns as N on the this left hand side. Right hand side is open circuited for now. So you know the direction of current is like this somewhat. So uh, it is a circular coil. So I will place my fingers along the coil, okay, and the direction of the thumb will give me the direction of the flux. This we have already discussed in this lecture. So if I place my finger along the wires, along the winding, I am observing that the direction of the flux is going topwards. So direction of the flux will be somewhat like this, right? So this will be the direction of the flux. So if I have to just draw the direction of the flux, I will draw it. So this will be here, 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 and here. Okay, so this will be the direction of the flux. Basically this will be the direction of the flux. Now what next we have to understand is that what is the value of this flux? How do I find out the value of the flux? Okay, I know the direction I have found out. So it will always flow in the core only, because the core is a highly permeable material. We will discuss about this later on, but for now let's just trust me that whatever flux has been developed here due to the current, that will flow through this core only. Direction we have already discussed with the right hand thumb rule. Now how do I find out the value of this flux? So what I have discussed, I will use a Ampere's rule here, right? I will use Ampere's law. What does Ampere's law say? Ampere's law says that the flux, the line integration of H dot dl, okay, line integration of H dot dl will be equals to the I enclosed, correct? So I am observing, if I just take this particular point in isolation, if I just take this particular point in isolation, okay, what I can comment is that what is the total I enclosed here? The total I enclosed will be like, first there is one turn, so some I current is going inward here, correct? I current, then another I current is going inward, then another I current, then another I current, so on. So total I have N into I current, N into I enclosed, because total I have N number of turns, and each time it is going into the coil. I'm winding, the more times I will wound this particular core, this Ni value will increase. Okay, already I have discussed, right? Previously here I have discussed, previously there was only a single current carrying coil coming out of this loop, so only I have written I once. If let's say there were two current coils coming out of this loop, then it will be 2I. So overall I enclosed will be 2I. So same will happen here. Overall I enclosed will be n into I. Okay, because n times it is going into the loop. Okay, and what is my loop? My loop is this symmetrical, right? Loop is like this. I have taken my amperes loop somewhat like this. This is my amperes loop. Exactly, this is my exact amperes loop. So this is my amperes loop. So A, B, C, D. So in this amperes loop, the overall I current that is incoming to this in this whole loop is how much? It is n into I. So that I have written. So here I have four like individual curves. So I will write them individually. So it will be again the same thing I will write here. It will be integration of h dot dl eb plus h dot dl bc plus h dot dl cd plus h dot dl this is cd and da, correct. So overall I enclose I have got, that is n into I, that I have got. Okay, what about this flux? So if flux is in this direction, I know magnetic field lines also will be in this direction only, correct? Magnetic field lines will also be in this direction, and my uh, line is also in the same direction. DL vector is also in the same direction. So every time my surface is along the direction of the flux only. My not surface, my line, my curved line is along the direction of the flux only. So what I can comment? I can comment that my theta will be equals to 0 degree. Okay, always, no matter what, theta will always be equals to 0 degree. And one more assumption is that flux will be constant throughout the core. Okay, just have to take my word, flux will be constant throughout the core. So this dl vector and h and b are same only, are they have 0 degree in angle between them. So this can be converted into h dl plus h dl plus h dl plus h dl equals to n into I, and this is AB, this is BC, this is CD, this is DA. Okay, so this will be h dot dl. So this will be h into like length of the AB section, LAB. H is constant. My assumption is h is constant, so I can take this h outside and I integrate dl from A to B. So let's assume that that is LAB plus h into LBC, because h is constant. That was my assumption, that h is constant, plus h into LCD plus h into LDA will be equals to n into I. So I can take the h common, and this will be LAB plus LBC plus LCD plus LDA equals to n into I. Now this is a very important equation. What is this? This is assumed to be length of the mean length of the core. Okay, this we write as mean length of the core. This will be discussed later on as well. So this I can directly write as h into L will be equals to n into I. So this is a very important equation. Okay, so where my L is the mean length of the core. L is the mean length of the core. That's it. Okay. So I hope you have understood this basic point. So here this term n into I actually resembles MMF. What is MMF? It is magnetomotive force. Motive force. Okay. So that is what my MMF means, and this is a very important equation. This is a very important equation. From this directly you will be able to find out the flux. How will you be able to find out the flux? So you know H is what? H is N into I divided by L. So what will be my flux density? B will be N into I divided by mu into L. Okay, this is what my, sorry, B is mu into H, and yeah, B is mu into H, sorry, mu into H, right? So it will be mu Ni by L, because B is mu into H, so B will be mu Ni divided by L. Okay, mu Ni divided by L. So this will be equals to mu naught mu r, like mu is written as mu naught into mu r. Mu naught is the permeability of vacuum and mu r is the relative permeability. Okay, just these are constant, don't have to worry about this. So my B comes out to be this. Now how will you find out the flux? So B actually is the flux density throughout this core. So how do I find out the flux? So to find out the flux, what you will do is, you have found out the flux density. So what you will do is, let's say the flux is constant throughout, okay, and the magnetic flux density is also constant throughout. So if I assume a small cross section area here, okay, I know the magnetic field intensity density through this area, that is B. So what will be my flux? Flux phi will be B into E. So this area will be given to you, and from there you can simply find out the flux. So your flux actually comes out, this will be equals to mu naught mu r, NIL is there, mu naught mu r Ni into A is there, because area of the whatever cross section you have chosen, divided by L. Okay, divided by L. Okay, so this will be mu naught mu r Ni divided by L into A. Okay, so yeah, that is the flux basically. So now this is the formula that you actually have seen, I guess. This is the formula what you have seen, because this is a very famous formula. Okay, flux is equals to mu naught mu r Ni divided by L. This can be rewritten somewhat like this. Flux will be equals to this mu naught mu r Ni, mu naught mu r Ni, not Ni, sorry, mu naught mu r A divided by L, or this can be written as mu naught mu r L divided by A. So this actually has a very famous what do you say, very famous term associated. So actually this I can rewrite as 1 divided by L divided by mu naught mu r A. Okay, this is actually known as the reluctance. This is actually known as the S or reluctance. Now why is it called reluctance? So you can rewrite this equation, okay, you can rewrite this equation as phi will be equals to Ni is the MMF, right? This portion is the MMF. Okay, and your area L, all this is the reluctance. So this can be written as MMF by reluctance, that is S. Okay, is this something familiar? is this something familiar? So this is something familiar, right? This is something familiar. So what is the familiarity? Familiarity is that this is something like I current is equals to voltage EMF by resistance. Okay, so that's why we have like same familiarity analogous in magnetic circuit. So phi is the current, okay, mmf is the EMF, and S is the resistance. So this reluctance is also somewhat like resistance only. Okay, so what is resistance if you remember? So my S is actually equals to L divided by mu naught mu r S. Okay, A. So what is my resistance? Resistance is rho L by A. So here I had resistivity, here I have permeability. That is the only difference. Okay, except L by A is also there. So both of these are dependent on the dimensions, but here I have permeability, here I have resistivity. That's it. So that's how these are analogous. Okay, I'm just linking the things. Of course, I will come to when I will like for now I have just applied a DC current. Okay, I have not discussed about the DC voltage. Not discuss about the DC voltage. So your circuit, right? So this whole magnetic circuit, whatever I've discussed, can be replaced with a similar electrical circuit, okay, analogous to electrical circuit. So this whole thing can be replaced here, that I have a mmf source, that is Ni, and I have a reluctance of S. And if I have source like this, then the flux phi will flow through the circuit. It is a magnetic circuit. This is not a electrical circuit, although it seems like it is a electrical circuit, but it is a magnetic circuit. Okay, so flux will be equals to Ni divided by S. Ni divided by S. Okay, so just like voltage divided by EMF divided by resistance, same, something similar. Okay, so that is what my flux is basically. So very simple things. I hope you have understood all the uh, like similarities, all the similarities between these things. So whatever I have discussed, that is written over here. A magnetic circuit consists of one or more closed loop paths through which flux flows. For now we have discussed only one of the path. Like there will be some leakage flux, I will discuss about that later. Okay, uh, and that is what my magnetic circuit is. So magnetic field is related like this, P equals to mu h. Magnetic flux is related like this, P equals to phi equals to B into A. Okay, all these things have been discussed. So what is magnetic motive force and reluctance? So just like EMF drives current in an electrical circuit, MMF produces magnetic flux. So EMF is responsible for driving current, MMF is responsible for producing magnetic flux. So MMF is equals to F is equals to N into I. So I have derived everything. Okay, I have derived. It's not like I've just written the formula MMF equals to Ni. I have derived how this Ni came. Then magnetic reluctance is analogous to resistance. S equals to 1 by mu A, where mu equals to mu r mu uh, mu r and mu not mu r. So this will not be here. Okay, this will not be mu not mu r. Okay, so that is the permeability of the material. Now these are all the analogy from the electrical circuit to the magnetic circuit. EMF, current, resistance, conductance will be just opposite of the reluctance. In magnetic circuit, it is known as permeance. Ohm's law will be V equals to IR. In magnetic, what is the magnetic Ohm's law? It is the MMF will be equals to reluctance into flux. Very simple. Just because if you remember, my flux was equals to MMF divided by S. Okay, so electric field, magnetic field, current density J, flux density B, conductivity, permeability. Okay, so that is the thing here. Now my Faraday's law. Now we will come to the next portion, that is Faraday's law. So Faraday's law, everyone has heard about this, that if I have a current carrying conductor and if I change my magnetic field around the current carrying conductor, then this current carrying conductor will actually generate a voltage that is governed by the Faraday's law. So Faraday's law, like what will be the magnitude of the voltage? The magnitude of the voltage will be the change in the flux linked in this coil, and the direction is given by the length. So this is the Faraday's law, that is V induced will be equals to minus d phi dt. So there are many ways by which we can change the flux linkage. Okay, like how many flux lines are passing through this coil, through the area generated by this coil. Okay, fictitious area by this curve. One thing is, if you change the area of this coil, if you make the circle smaller than larger, then the flux is changing. Whatever the flux linkage is changing, because magnetic field is magnetic flux density is constant, but area is changing. If area is changing, then obviously the flux will change. So that's how you can generate a induced EMF. Or if you keep uh, like take this magnet more nearer to the coil and then take it away from the coil, again the magnetic flux density will change. So if I bring it more near to the coil, then of course the magnetic flux density will be higher. If I take it away from the coil, the magnetic flux density will be lower. So the amplitude of the magnetic flux density is changing, hence the magnetic flux also, amplitude of magnetic flux will also change. Okay, so that was about the magnetic flux. Now let's discuss about the sign and about the induced EMF. So induced EMF will be in the coil, right? So why is it important for a transformer? So if I have applied a AC source across the coil, so we know that a flux will be generated. Okay, that much we know, a flux will be generated, and that flux will be somewhat like this, correct? Flux will be somewhat like this. This will be the flux. Now, very interesting thing will happen. So as this voltage is AC, okay, it is changing, the flux will also keep on changing, correct? So as the voltage is, let's assume the voltage is a any random sinusoid function, cosinusoid or sinusoid function. Let's assume it is root 2 V1 cos omega t. Okay, root 2 V1 cos omega t. Now, if the voltage is changing, it is sinusoidal, flux will be sinusoidal also. Flux also will be sinusoidal. So just take my word that flux also will be sinusoidal. It will be some phi max sine omega t. Frequency will be same, of course. Frequency will not change. Okay. Now, what is the interesting fact here? The interesting fact here is, yes, flux is sinusoidal. Like this will also generate a flux. Previously also, whenever there was a DC current, that was generating a flux. But the interesting fact to note here is that flux is time varying. Time varying. What do I mean by time varying? Time varying means it changes. It changes. Okay, flux is time varying and it changes. So what I can say is that as it is changing, we have to apply the Faraday's law, because whenever I have a current carrying coil and through the current carrying coil, flux is changing. So if flux changes, I have to apply the Faraday's law. So if flux is changing, that means it will induce a voltage. So what will be the induced voltage? V induced will be, magnitude of the V induced will be d phi over dt. Okay, rate of change of the flux. By the rate at which the flux is changing, that will be the value of the induced voltage. So this will be equals to d phi over dt. So this is d over dt into phi max into sine omega t. Okay, so this will be equals to, phi max is a constant term, this will be cos of omega t. Okay, so magnitude of the induced EMF will be phi max cos, and omega is also there, right? Omega is also there. Okay, because like we are differentiating with respect to time, so omega is a constant number, so it will be omega into cos of omega t. Okay, now the important fact to note here is that yes, this coil will generate a induced EMF. Okay, this coil will generate an induced EMF, and the magnitude I have discussed. What about the direction? What about the direction? So how do I discuss about the direction? So first of all, we don't have any fixed direction here because this is a AC supply. So the plus minus will keep on alternating, like my source, right? It will be sometimes positive, sometimes negative, sometimes positive, sometimes negative. So my flux also will be sometimes positive. My induced EMF also will be sometimes positive, sometimes negative. But whenever my actual supply is positive, what will be the sign of the induced EMF? That we have to identify. So how do I identify that? So Lenz law states that whatever was the root cause for producing this flux, that I have to minimize. That I have to minimize. Whatever was the root cause for producing this flux, because why did this induced EMF get generated? It was generated due to the change in the flux. Okay, initially there was no flux. As soon as I given any supply, so there is change in flux, right? So if this is, let's say, phi max sine omega t, so initially the flux is increasing. That's why in the positive half cycle it is increasing. Then in the negative half cycle it is decreasing. So if the flux is increasing, the induced EMF will be such that it will try to decrease this flux. It will try to decrease this flux because initially I had zero flux. It does not want to change its state. So my sign will be such that I will actually overall flux I will try to decrease. I will try to oppose the change. Okay, I will try to oppose the change. So if on the supply side, if the voltage is increasing, so the induced EMF side, what I will do is uh, I will actually increase the voltage here as well. I want to increase the induced EMF voltage as well, because if the supply side voltage is increasing and if the voltage here is lower, more current will flow, because like there will, like even if you assume that there is some winding resistance, okay, some winding resistance, so this is higher potential, this is lower potential, so more current will flow. I do not want that, because when more current will flow, more flux will be generated. I do not want that. So we want to keep this in the same potential. So whenever my V will increase, I will want my V induced to also increase. Okay, so that's how you identify the direction. Okay, whenever your V will increase, I want my V induced also to increase. Okay, so that is the important fact over here. So my sign of the V induced will be somewhat like this. If basically if I write a coil, if I just draw this left hand side of the circuit, okay, if I just draw the left hand side of the circuit, I have a supply here, AC supply, I have the inductor here, okay, and I have the voltage. So the voltage, like if this is dot means plus, I will explain you what does dot mean. Not plus, actually dot means the instantaneous polarity. I will explain, we'll come to the dot polarity later on, don't worry about it. For now, if this is dot, then this also will be dot, then this also will be dot. Okay, because if this is increasing, this induced EMF also should increase, so that I can overall reduce the change in flux, I can oppose the change in flux. So that was about the polarity. Okay, one more very interesting fact, interesting fact to note here is, here, right, the winding resistance is very low. Like if you measure the resistance of a wire, the winding resistance, okay, the winding resistance R winding is negligible. It is almost equals to 0 ohms. R winding is negligible, it is almost equals to 0 ohms. Okay, so R winding is negligible, it is almost equal to 0 ohms. Now what I can say is that to satisfy KVL, right, so to satisfy KVL, so this is my V induced, this is my V induced, so satisfy KVL, my V, this is my input voltage, right, that whatever I am giving, V input has to be equals to V induced, because my assumption is there is very low drop. Okay, very little drop. This winding resistance is very small, almost equal to 0. Okay, that is my assumption. So the induced EMF V induced is actually whatever I had told you earlier. It is root 2 into V1 cos omega t, root 2 into V1 cos omega t. Okay, also I know what is the magnitude of the induced EMF. Magnitude of the induced EMF is phi max omega cos omega t. So it will be equals to phi max omega cos omega t. So actually there is a very good equation that we get. What is the equation? Equation is my flux phi max will be equals to the root 2 V1. V1 is the RMS value. This is the RMS value. Okay, RMS and all those things have been taught to you in network theory. So I hope you have already studied those topics. Okay, so this will be equals to root 2 V1 this. So root 2 V1 phi max divided by omega, correct, omega, and cos omega t automatically gets cancelled. So this also we can write, this is root 2 into this is some RMS value, so I can write this as V max also you can write, or you can directly write this as RMS only. So root 2 into V1 RMS by 2 pi f. Okay, so this will be equals to root 2 divided by 2 into pi. Okay, so 0.22, whatever this value is. Like what I am coming to is like what is the main point? Main point is my flux phi max is proportional to V by F. So the main point is in an AC circuit, or whatever we are discussing, all this is in an AC source. In an AC circuit, if the voltage, applied voltage is fixed, if the applied frequency is fixed, then the maximum flux through the core also will be fixed. This is for a AC circuit. So for a DC circuit, we had to find out the MMF, then divide by reluctance, then only we were able to find out the flux. But in an AC circuit, it does not matter. In AC circuit, it does not matter. The phi max mainly depends on the voltage and the frequency of the supply. It does not depend on the core. Okay. But of course, to increase the magnetic flux density and the intensity of the flux lines, for that we will need a better core. Okay, and for more flux lines to pass through the core, for that we will need a better core that we will discuss later on. But mainly your maximum flux depends on these two parameters. Okay, so here like whatever I have discussed, that is what I have told you. So if I have a AC source, so if I apply a AC source, an induced voltage will be generated in the AC source, and due to that, once the supply voltage and its RMS value are known, the magnetic flux in the core is essentially determined. So we don't need to go through this hassle that DC current is there, then find out the MMF, then divide by the reluctance. No, we don't need to do. We do not need to go by the step-by-step approach, first calculating the MMF, then finally dividing the MMF by reluctance, and instead the flux gets established instantly as soon as I apply a AC source. Okay. So yeah, same thing whatever I've discussed is written over here, that when an alternating voltage is applied at the coil, it induces an alternating current, which in turn generates a time varying magnetic field. The flux oscillates with time, sometimes flowing in the clockwise, sometimes flowing in the anti-clockwise direction. So sometimes it will flow like this. Okay, sometimes it will flow like this. Okay, because the flux is a sinusoid function, so direction obviously will change. Okay, this flux will oscillate with time, sometimes flowing in clockwise and anti-clockwise direction, and sometimes reaching zero as well. So as my like this is the induced EMF, as my flux changes with time, hence there will be a induced EMF, and that induced EMF will be exactly equals to my input voltage, because there is very little winding resistance. So if I draw this in the circuit diagram, circuit analysis, how will I draw this? So this will be V, and this will be my MMF basically. So my like the coil in itself will generate a EMF, basically induced EMF E1, that will be generated. It will be generated such as it opposes the cause. Okay, So who generated who, like, what was the cause? Cause was this voltage source. As soon as I applied a voltage source, what happened? Flux got generated. So of course the coil would not like any change in the flux, so it will generate a EMF such that it opposes the voltage source. That's why the signs of instantaneous polarities will be same. So if, like, I will discuss about dot polarity later on, don't worry, because this is a AC source, I cannot just simply write plus minus, okay, that will be wrong. So if if at a particular instant this is positive, then this will also be positive. If in a particular duration V is increasing, E1 will also increase. So sometimes we denote our signs like this as well in AC. Of course in AC, right, the polarity is relative, it is not instant, it is not fixed polarity, right, polarity keeps on changing. So that is the important point that I wanted to discuss over here. Okay, I hope you have understood this very very basic point. Okay, I hope you have understood this very very basic point. Now let's discuss about the this induced voltage. I've already discussed how the voltage will be induced. So since the flux in the core is time varying, the coil itself act as a source of the EMF. This means that even though the applied AC voltage drives the systems, an induced EMF will appear across the coil, and it is modeled like we have modeled it like this, right? So the model I will copy here. Basically this is the model of this whole circuit. So I will come to all this, like I will come to this when what will happen in DC and all those things. So we have to first clear out our basics. I know initially you might feel like we're not doing any questions, but trust me, all the questions will be solved after this. Just have trust on me. So the same thing whatever I have discussed, that this, right, uh, winding resistance is very very low. So I can assume it to be very very low, so there will be very less voltage drop. Okay, so the same thing is written, the induced EMF is an equal to the magnitude of the voltage. In contrast, DC magnetic circuit, there is no induced EMF. Why in DC, right, we have not discussed about any induced EMF or something? Because the flux there was fixed, it was constant, it was not time varying. So that's why the flux was fixed as the current is fixed. How is the current fixed? So there will be a winding resistance, some very negligible winding resistance, and if I am applying a voltage source, so it will be V by I, V by R, basically the current. So if the current is fixed, then the flux is fixed, because what is my flux? Flux is equals to mmf by reluctance. Mmf is equals to N into I divided by S. So N will not change, S will not change, I will also not change, because I is a DC source. Okay. If I assume the winding resistance, but if I assume an ideal transformer, we will discuss about that as well. What will happen to an ideal transformer? So the same thing whatever I've discussed here, like the winding resistance is 0 for AC circuit, so R is negligible, R is almost equal to 0. Okay, so my KVL will be equals to E will be equals to V1, because I have to satisfy the KVL here, because I have to satisfy the KVL, that's it. Okay, so we got our phi max. What is phi max? Phi max, what was the expression for phi max? Phi max we derived was uh, root 2, not root 2, sorry, this is E1 RMS, or whatever the voltage is, V1 RMS, V1 RMS divided by root 2 pi f. Okay, V1 RMS divided by root 2 pi f n1 if it's in the primary. Okay, n1 if it's in the primary. If we see, right, this was the derived expression. Okay, sorry, I missed one thing, right? uh okay, one thing I missed here, sorry. Actually this, right, if I have n number of turns, this should be n d phi dt. If I have n number of turns, this one I missed. Actually, I'm sorry about this. This will be n d phi dt. So this will be here, this will be n d phi dt. Okay, and that is my bad. So here I will already have a n here. Okay, and this n will go in the bottom denominator. I'm sorry. So this n will go in the denominator, n1. If I assume the turns in the primary is n1, so this will be n1. Okay, because the flux is changing here only. Okay, we are not discussing about this, we will discuss this about later on. Once we will go into the transformers chapter, we will discuss what will happen here as well. Okay, so this will be n1, this will be n1, and yeah, n1 will come here. N1 will come here, yes. So ultimately, right, my flux, if the voltage, RMS value of the voltage is fixed and the supply is fixed, so my phi max also will be fixed for a EC circuit. This is a very, very independent, like a very, very important expression. Okay. So what is the key point? Key point is my flux phi max is actually independent of what? Independent of the permeability mu. It is independent of the permeability. It is only dependent, my phi max is function of either the input voltage V1 RMS, the input frequency, supply frequency F, and the N1. Okay, that is what my flux is dependent on. Okay, this is what my flux is dependent on. So these are the key points. Now let's come to the most important point of this lecture. Okay, most important point. We have discussed about these many things. Now what if I have a transformer? Okay, this is how we discuss a transformer, like 200 volt to 100 volt. Basically, the LV side is the 100 volt, that is the low voltage side, and 200 volt is the high voltage side. Frequency is given fixed. It is connected to a 10 volt DC transformer, and if they have not mentioned anything about the transformer, my assumption will be that it is a ideal transformer. It is an ideal transformer. So what will be the resultant voltage? So one more thing I want to derive here, that this is my phi max, right? This is my phi max. So same flux will actually flow through this as well. Like this is a series circuit, right? Whatever flux will flow through here in this core, same flux will flow through this winding as well. If the same flux is flowing through this winding, same flux is flowing through this winding, right? Same flux, same time varying flux. So again, in this winding, there is a time varying flux. There will be a induced EMF, correct? There will be a induced EMF here named as E2. Okay, what will be the value of the E2? It is E2 value will be equals to N2 d phi dt. Okay, I'm not discussing about the sign right now. Sign I will discuss later on. Okay, N2 into d phi dt. So from here I can directly find out the magnitude of it. So what is my E2? E2 E2 will be equals to uh, N2 into d phi over dt, right? So d phi is sin omega t, phi max sin omega t, not cos omega t. So this will be omega into phi max into cos omega t. Okay, and same, right? Same flux is flowing here. So what will be my E1? Magnitude of E1. Magnitude of E1 will be n d phi n1 d phi by dt. Same flux is flowing, so through the primary and the secondary. So it will be same expression, just n1 will be here. Okay, n1 omega into phi max cos omega t. Now, what is the ratio of E1 over E2? The ratio of E1 over E2 is very simple. It is like all these are constant, right? The omega, phi max, cos omega t is like same time domain. So at any particular instant of time, the ratio of the E1 over E2 will be N1 by N2. Or also one more thing, that my E1, magnitude of E1 over N1 will always be equals to magnitude of E2 over N2. That is, this term is also known as EMF per turn. This we will discuss later. So EMF per turn will be same throughout the core. Okay, all this is for AC supply. Okay, so here the same question is there, that we have a 200 volt on the high voltage side, 100 volt on the low voltage side, and it is connected through a 10 volt supply. What will be the resulting voltage on the high volt? Okay, on the low voltage, that is on the 100 volt side, I have connected 10 volt. What will be the high voltage? So if you just simply blindly apply the formula, that my E1 over E2 ratio will be always fixed, right? It will be N1 over N2. So if I go by the rating, that is 200 volts divided by 100 volts, and in the 100 volt side I am connecting 10 volt. So what will be the value in the 200 volt side? So this will be Vx by 10. So this will be Vx will be equals to 20 volts. Okay, so Vx will be equals to 20 volts. You will write this down and it will be totally wrong. In the interview, or if you get asked this question, it will be totally wrong. First thing is, this is a DC supply. Okay, so obviously something different is there. So we have already discussed, if I apply a current, right, constant current, if I apply, what will happen? If I apply a constant current, my flux will be constant. It will not be a time varying flux anymore. Okay, if I apply a constant DC current, flux will be constant. What is the value of the flux? It is mmf by reluctance, Ni by S. If I apply constant DC current, because the current is constant, flux will be also constant. In AC, the current was time varying, it was sinusoidal, so the flux also will be time varying. Hence, there will be an induced voltage in the coil. But as here the current is constant, if I apply constant current source, the flux will not change, so there will not be any induced voltage, and simply flux will be constant. But what happens if I apply a voltage source? What happens if I apply a DC voltage source? So you have already heard this, that the coil gets damaged, huge current flows, all those things you have already heard. I know you have heard that. Okay, but how huge current flows? Is it very simple? Is it very simple that just as soon as I applied the DC voltage source, the coil gets damaged? No, it is not like that. So for this, right, we have to go to basic networks. Okay, I will not explain you any concept of transformer and all those things. I will not tell you that. I will just go into the basics of networks. Okay, so this is the most important part for EC aspirants. Okay, before that I was discussing about magnetic materials and properties. Now I will discuss what happens if I apply a DC voltage source to a transformer. So this circuit I can equivalently replace with the inductance. Okay, very basic thing. So this is just a coil, right? So this is just a inductance. So I am applying a voltage source. I'm applying a voltage source VDC, and I have a inductor here, L, correct? Or whatever the number of turns is N1 here, and inductance, let's assume inductance is L. I will discuss as well what is inductance. Okay, this you have already learned basics of inductance in network theory. So I will just simply apply the formula. It is a concept of, if I apply a DC voltage source across a transformer, it will be in the constant, like it will be linearly charging. So in the interviewer, this is a very good interview question. So it's not like the coil will get instantly damaged, not like that. It will start linearly charging. What do I mean by linearly charging? Use the very basic equation of inductor. What is the very basic equation? VL is equals to L DIL by dt. Okay, I know the voltage across the inductor is constant, fixed. What is the voltage? Voltage is VDC. Voltage is VDC. So voltage is VDC. Inductor is L, and your DIL by dt is this. Okay, so if I integrate this, my IL will be equals to integration VDC. VDC is a constant number, so is L. L is a constant number, dt. Okay, I'm integrating from 0 to t. Okay, so this will be VDC by L into t. Okay, so what is happening? That my current is linearly increasing. That's why we say it is linearly charging. My current is linearly increasing. That's why we say it is linearly charging. So my current will linearly increase in the circuit. It is not like it will instantly get damaged. It will not instantly get damaged. So current will increase linearly. So if current increases linearly, one thing I know, that my flux, right? Flux. If you see in this equation, flux is proportional to current. So my flux is also proportional to current only. So if flux is proportional to current, that means that if my current is increasing, then my flux also will increase. Okay, so my graph of flux will be something like this. Flux also will increase linearly. Now you will have a question, sir, here the flux is changing, right? So won't it actually induce a EMF? your question is valid, but if you observe, what is the magnitude of the induced EMF? Magnitude of the induced EMF, E induced, is actually the d phi over dt, right? N d phi dt, whatever is there, okay? N d phi dt or L dit dt, whatever is the current, right? L dit dt or N d phi dt, this is the inductance property. So here, right, as the flux is increasing at a constant rate, so the slope is constant. Slope is constant. So if the slope is constant, that means what? V induced is also constant. So V induced actually will be a constant number. It will not change actually, and it will be actually equals to VDC. You can figure this out. You can do it by yourself. You will see it will be equals to VDC. How? So either you can write V induced will be equals to N d phi dt, exact equation, or you can write V induced is equals to L dit by dt. This also is the same equation in the current domain, not in the flux domain, in the current domain. So if I write L dit by dt, so if I differentiate this with respect to time, it will be VDC by L, and I will multiplying L. So LL will get cancelled. Simply VDC will be left out. So everything is satisfying. So voltage will be equals to VDC. That is satisfying anyways, right? But what is the problem? The problem is that the core will not instantly get damaged, but after a certain point, what will happen? Every core has a saturation. This is a property, magnetic property of a magnetic material, that I cannot infinitely flow current. Just same thing, like if I have a resistor here, and if you ever go to the market and purchase a resistor, you will tell them that I need a 1 watt resistor, I need a 0.25 watt resistor. So every resistor has a rating. So what does this rating signify? If I flow a current more than the rated power whatever they have given me, then it will damage the resistor. Okay, if I flow any current that will actually consume a power more than 1 watt, that will damage the resistor. Same thing, same concept is here as well, that of course this material, core material, whatever the amount of flux that it can pass, that it can flow, is fixed. Okay, I cannot let it pass infinite amount of flux, so that is fixed. So of course I cannot pass infinite amount of flux, so it will get saturated, and as it will get saturated, the first of all core will saturate. This is the first thing, core will saturate. Okay, and next thing is, if I apply a DC source, what will happen is, if I assume there is no inductance, then the students say that I am applying a DC voltage source through a wire. Okay, hence the resistance of this wire is 0. So current will be VDC by R, it will be infinite. VDC by R, that is VDC by 0, it will be infinite, so it will be huge current, so that will damage the coil. It is actually not completely correct. Okay, this I know you have learned in any other course, any other place, wherever you have studied machines, that it will burn the coil, it will damage the coil, but totally this is not correct actually. Totally this is not correct. The correct thing to say is that whenever I will apply a DC voltage source, the inductor will linearly charge, so current will linearly increase. So as current linearly increases due to inductance, the property of inductance, what will happen? After a certain point, the core will have its saturation point, where I cannot pass like infinite amount of flux, it will saturate after a certain point. So if it saturates after a certain point, then I cannot pass infinite amount of flux, so core will simply saturate, and that can damage the core as well, because it is not rated to work always at saturation. Okay, that can damage the transformer. So it is not that simple that it will be okay, V by R, V by 0, infinity current. No, not like that. Actual thing what is happening internal to the transformer, that is what you have to understand. So if you have enjoyed this concept, and trust me, this will no one will explain you this. Okay, this I am telling you in the first lecture of basics of machines, prerequisites of machines. We have not even started transformer. And there is a huge misconception regarding this thing, right? So to build up the base, that's why I had to explain everything, magnetic circuits, reluctance, everything, to come to this point. This is the most important point. EC aspirants can listen to this most important point. And trust me, this is no one, like if you tell this to the interviewer, right, interviewer will literally be impressed by you. Trust me, because everyone tells the same thing. This thing they say, that coil will get burned, damaged, because infinite current will flow. But that is completely not true. This is the actual scenario. So if you enjoyed this concept, please go into the comment section and please comment, okay, about this concept, and tell, like, just let everyone know that this is something new that you have learned, right? And I know this is something new. No one will teach you this in this whole industry. No one will teach you about this. Okay, I have not, like, although I have to explain magnetic circuit, all those things, but in this particular concept we did not use much of magnetic circuits, right? I just used simple inductor concept. Okay, and with that basic concept I've explained you one of the most asked interview questions. Most asked interview questions. Okay, so yeah, I hope you have enjoyed this thing. And of course the transformer, like, it will burn, the winding can burn because high current will flow, but that is not the completely correct answer. That is not the completely correct answer. So here whatever I have discussed is written, the flux behavior in AC and DC, whatever I have discussed, same thing is written over it. Okay, so just for your notes, proper notes, it is there, so that I don't waste my time in, like, yeah, I don't waste my time in writing these things. So one more thing is that, so why does, like, primary winding will burn, right? Primary winding will burn here because current will keep on increasing, and after a certain point the rating, the winding rating, the current that will increase, it will go beyond the winding, the rated current of the winding, so of course it will damage the winding. Okay, now why does the secondary does not burn? That can also be asked in the interview. So if, why the secondary does not burn? If you just keep the secondary open, right, so here the current is zero actually, no current flows to the secondary. So if no current flows to the secondary, yes, a voltage is induced at the coils but no current flows, that is totally fine. Same concept, like, I have a voltage source here, so I am not connecting it, right? So still if I measure the potential across this point, I will measure V, that is no problem, but there is no resistance connected, so current will be zero. Okay, so as current is zero, so this winding is not carrying infinite amount of current, this is carrying very low amount of current, so this winding will not get damaged or burnt. Okay, that is the reason. That can also be asked in interviews. So that is the reason, right? The secondary winding does not carry any current unless load is connected. The primary, however, experiences a high current surge leading to overheating and insulation failure. Okay, so how can we prevent this? So there are many safety measures, like transformers are always connected to AC sources. So we never connect it to DC source. Even if we must mistakenly connected to DC source, there are few protection circuits such as fuses, circuit breakers are used to disconnect power in case of huge current that flows. Okay, current limiting resistors are also there to prevent the high inrush current. Okay, these are protective measures. So now I will just quickly go through the whatever we have discussed about magnetic circuit. So in a transformer, there needs to be a path for the low reluctance path for the magnetic flux to flow. So that is actually known as the core. Okay, and generally our core material type is ferromagnetic. Okay, I will discuss about the magnetic materials later on. Okay, that is not important for EC aspirants, so that's why I have skipped it for now. I will discuss it later on. So that's why we have a ferromagnetic core, because it will provide the least reluctance. Same like if I have a resistance, if the resistance is very high, then of course the current will be low, right? So I don't want that. I want as much current to flow. So I will have to choose a material such that it can flow the maximum current. Same for the magnetic circuits. I will choose a core that will have the least reluctance so that the flux can flow easily. Okay, and of course it will provide the structural support for the windings, for the coils. Next term is the magnetomotive force that we have already discussed. It is N into I. Magnetic field intensity, it will be mmf by I, that is Ni by L, right? This also we have derived. Magnetic field intensity is mmf by I. How we have derived? We have used the Ampere's law. We have derived the, not I, sorry, mmf by L. We have derived the Ampere's law, where L is the, what? L is the mean length of the path, magnetic path. However my flux will flow, that will be the L. Okay, in whichever direction the flux will flow, that will be the L. This is my direction of flux. Okay, so yeah, so what is my magnetic flux density? Magnetic flux density represents the number of field lines passing through a unit area. This we have also discussed. So it is like phi over A, or magnetic flux is equals to B into A. This we have all these things we have already discussed. So whatever we have discussed is just written over here. That's it. The new term is like permeability of materials. Okay. So there is a term known as absolute permeability, that is the permeability on the free space on the vacuum. Okay. And as we move along, different mediums like air, like water, so those will have different kind of permeability, that is how they flow the flux. So the term is relative permeability for those mediums. So overall permeability of any medium is equals to mu naught, that is the absolute permeability of vacuum, into the mu r, relative permeability of that medium. Okay. So ferromagnetic materials has mu r 2000 to 6000, which is very high. So that's why the flux, the reluctance of the path is very low. Okay. Now there are few things known as series and parallel magnetic circuits. Okay. So if we see, observe here, right, there are actually two magnetic circuits, although you can see only in the this area only the coil is wound, but there are two magnetic circuits here. How are there two magnetic circuits? I will explain. So here if you see that if the current is flowing like this, then current direction is somewhat like this, right? Okay, current direction is somewhat like this. So magnetic field direction is somewhat like this. Okay, this will be the magnetic field direction. Magnetic field, like if I just curl my fingers along the wire, current carrying wire, so my thumb is on the right hand side, it is in the clockwise direction. Very basic, right? It is in the clockwise direction. So magnetic field lines direction will be somewhat like this. So this is the current carrying wire direction, and this is the flux direction, correct? So actually flux is flowing through this particular core as well, and through this air gap. This is known as, if nothing is there, no core is there, this is known as air gap. Okay. So the flux is flowing through here as well, the flux is flowing through here as well, the same amount of flux. Flux density will change, but flux will flow. Okay, same flux will flow. Now as there is air gap here, what will happen is that the flux density will be lower because air has high reluctance. So the flux will be somewhat like this. So it will come here, then it will be somewhat like this. Okay, and this will be here. So just let me draw this thing. Yeah, like flux will flow throughout this core, right? Not like just it will flow in one of the circles, it will flow in many circles. I have not drawn it previously, but I hope that is understood. So due to the air gap, what will happen is that the flux density will be lower. Why? Because air has high reluctance. So air has high reluctance because let's assume that this is a ferromagnetic core. So this mu r of this is like 5000. Okay, and this is air gap. So here the mu r is 1. So what is the reluctance? So everything is almost similar. Reluctance is L upon mu r. Sorry, it is, yeah, reluctance is L upon mu into A, correct? So the area is same, length is different, I do agree, but if you see, mu r is very high in case of ferromagnetic core. So the core reluctance will be lower than the air gap reluctance. Why? Because the mu r is higher than the mu r of the air gap. Okay, so this will be, so my, if my mu increases, my simply reluctance will simply reduce. That's it. Okay, so that was about the S core and S air. Okay, so yeah, so what is happening, flux is same flux is flowing. So if I want to draw this in the circuit, how will happen? So I have a mmf source, mi. What is the mmf of this source? It will be what? Current, that is I, and how many number of turns I have? N into I. So mmf of the source will be N into I. Okay, this will be mmf. And initially I encountered this core. So this core, let's assume, has a reluctance of S core. And of course the same flux, it is a series circuit, right? Same flux, whatever flux is coming here, like flux always follows a closed loop path. That was the property of magnetic field lines. So if it follows a closed loop path, whatever flux is here, same flux will again reach this point. Okay, although the flux density will be lower in this air gap, but still it will somehow reach this point, right? So it will be same flux will come here, so both of them will carry the same flux, so it will be a series circuit. So this will be S gap. Okay, reluctance of the S gap. So flux, magnitude of the flux will be what? It will be the addition of these two series reluctance. So it will be mmf Ni upon the overall reluctance of the system. What will be the overall reluctance of the system? It is S core plus S gap. Okay, so it is Ni upon S core plus S gap. So very simple, right? Very simple. So basically that's how it is a series circuit, similar to a series resistance. The current is the division of voltage, like voltage divided by the summation of the resistances. And what happens in a parallel circuit? So parallel circuit is somewhat like this. So if I have applied a, like any voltage source or current here, so flux will flow like this. So somewhat of the flux will come here. Okay, just hold on. So if I draw the flux lines, right, flux lines will be somewhat like this. So it will be here, and okay, the color change, sorry, no, not the color change, color did not change, just give me a second. This will be in this direction, and just copy this thing here. Let me change the color. Yeah. So like the flux will get divided, right? So some of the flux phi 1 will go on the left hand side, and like because both of them are in the same magnetic material, very good like low reluctance path, so flux will get divided, same as current. So here some phi 1 flux will flow on the right hand side, some phi 2 flux will flow. Okay, so flux is divided, so what will happen is that I can draw my circuit, equivalent circuit is mmf is here, that is N into I, and it is providing phi flux. So from this region, overall flux, how much flux is going? Let's assume from this region phi flux is going. Okay, let's assume from this region phi flux is going. Okay, so from this region if phi flux is going, so this will be like S1 on the left hand side and S2 on the right hand side. Okay, and through S1 the reluctance phi 1 flux will flow, and through S2 phi 2 flux will flow. So again, what will be the equivalent reluctance? How do you find out the equivalent reluctance? Very simple thing. Again, the formula of flux phi will be mmf Ni divided by the overall equivalent reluctance. So I know phi is equals to phi 1 plus phi 2, and as what is happening, both of them have the same mmf, right? It is like a parallel circuit, so mmf is same. mmf is same in the, like this core, this point of the core, this leg is common to both the left hand side and the right hand side. So mmf is same, so it is equals to Ni divided by S, or I can write my phi 1 is equals to Ni divided by S1, the reluctance of the S1 path, plus Ni divided by the reluctance of the S2 path. Okay, so this will be equals to Ni divided by S. This will be equals to Ni divided by S. So this From here I can directly write my S equivalent 1 by S will be equals to 1 by S1 plus 1 by S2. Same parallel formula that we have used for resistance. Okay, same thing. Whatever we have discussed, same thing. Now, one more thing is that flux, right? It's not like it will only flow in this line. There will be multiple lines. I'm just showing one line, but there will be multiple lines. Multiple lines of flux will flow. It's not like only one single line will flow. Like same thing is represented over here. So flux will flow in multiple lines, but we will not be able to find out the reluctance, because for this path the reluctance will be different. Why? Because the length of the core will be higher, right? Like if I'm choosing the outer periphery, the L increases. So if the L increases, the length of the core is higher. Okay, if the L increases, the length of the core is higher. In this region, the reluctance will be lower because the L has reduced. So the path that the flux has to take has reduced. Okay. So what we do is we choose a mean length. Okay, we do not choose the outside, we do not choose the inside, we choose the average mean. Okay, so this whole thing can be converted. Although it is understood, practically it is understood that yes, there are multiple lines, but for our better, easier calculation, for our understanding, we assume that the overall flux is flowing through this mean length, and we assume a constant length L. So overall reluctance of the path will be L mean length upon mu A. Okay, for our better understanding and for our better symmetricity. And roughly, right, of course the reluctance will not be exactly equal to this, whatever reluctance we have calculated, but roughly both of them will be equal. Okay, whatever approximation we have done, some approximation that although the flux, right, flux is sometimes flowing outside, so the mean length is like length is different. When it is inside, the length is different. But here, so here, right, here as we have assumed that flux is flowing through this mean length, the reluctance will come out to be a single value only. Okay, here multiple, okay, this got deleted. So here multiple lengths of the flux is there, so calculation of reluctance will be difficult. But once you calculate the equivalent reluctance here and the reluctance that has been calculated through the mean length, both of them will be approximately equal. So this is a very good approximation that we take, that is the mean length of the core. Another point for magnetic materials is the fringing effect. What is the fringing effect? So as I have already discussed that if I have an air gap, then the magnetic flux density will be lower because the reluctance is higher. So what happens? Yes, flux reach at this end and at this end, and then they separate out basically. So of course flux will always follow a closed path. So what will happen is some of the flux will not exactly be in the straight line. It will not be very dense, it will be less dense. Okay, so as it is very less dense, so that's why the flux lines will be spread out. It will be spread at the edges. Flux line will be spread out. It will be not like straight like this. So due to that, what will happen? The effective cross section area will increase. This is known as the fringing effect. What do I mean by effective cross section area? So this is my cross section, right? So the area through which the flux flows, effective cross section area has increased, hence the flux density will basically reduce. That's why we say flux density reduces, because what is flux density? Flux density is phi over A, number of field lines divided by area. So as the effective area increases, because my field lines are spread out more, so if area increases, the flux density will simply reduce. That's it. Flux density will simply reduce. So this kind of thing is known as fringing effect. How can I reduce it? So we can reduce it by reducing like this gap is known as the air gap length, Lg. Okay, so if I reduce the Lg, then what will happen? This will be more closer, so the fringing effect will be minimized because the Lg has reduced. And what is my reluctance? Reluctance is L upon mu A, right? So if I reduce my L, reluctance will reduce. So at least the reluctance will be somewhat comparable with the core. Okay, I'm trying to reach to the core level of reluctance. So reducing L will actually reduce the fringing effect. Okay, that was the basic thing. Another important term is known as the leakage flux. So what is leakage flux? So leakage flux is basically the amount of flux that does not link with the secondary coil. Okay, what do I mean by it? So this is also another term for magnetic coupling. So like let's assume some very basic thing. So if I have a, let's say, current source here, okay, and there is a, let's say, 1 amp of current source, and there is a 1 ohm of resistance. Okay, and let's like we want to measure the voltage across this resistance. How will I measure the voltage across the resistance? So what we'll do is we'll connect a voltmeter here, right? And if you have studied measurement, you'll know that the voltmeter is of high impedance. Okay, voltmeter has very high impedance. So voltmeter has high impedance. So let's assume, like, of course ideal voltmeter will have infinite impedance, but let's assume the voltmeter currently whatever we are using has 999 ohms of impedance. So if it has 99 ohms of impedance, what will happen is that this circuit I can equivalently write like this. This will be 1 ohm, this will be 999 ohms. So actually, right, ideally what voltage should I should have measured? Ideally voltage should have been I into R, that is 1 into 1, so it will be 1 volt. Okay, and what actually am I measuring? Actually I am measuring, this is, let's say, I2 current and this is I1 current, right? There will be current division. So I1 will be equals to 1 into 999 divided by R1 plus R2, so 1 plus 999. So this will be equals to 999 divided by 1000. So this will be 0.999 volts actually. So what I was expecting was 1 volt, but I am actually measuring 0.999. Why? Because whatever current was actually supposed to go through here actually is not going. So the rest of the current is going through this circuit, right? 0.001 amperes of current. Something similar is happening over here. So my expectation was, if let's say this has n turns or n1 turns and I'm supplying I current, so the flux, right, should be n1I divided by S. That is my expectation. But what is happening is that S is the S of the core, reluctance of the core. What is happening is that due to some leakage flux, because this winding is actually present in the any medium, right, air medium. So what will happen? Some of the flux will actually not go through this core. Some of the flux will happen. What will happen? Some of the flux lines will actually get generated. Okay, just hold on. Get generated like this. That bit of it will be going here. Bit of it will be going here. Okay, like this will also complete the field lines, and this will not. This is not actually going into the core. It is not flowing through the core. It is only flowing through the winding 1. It is not flowing through the core and going to the coil 2. It is just flowing in the coil 1. Okay, so that's why it is leakage. It is called as leakage flux. Why is it called leakage flux? Because it is not linking the primary and the secondary. It is leaking. The flux is actually leaking from the core and just flowing in this particular region. It is not going into the secondary. That's why it is called leakage flux. Same here, right? The current is actually leaking to the voltmeter. It is not going through the actual resistor. So same thing here. We, of course, we don't want this kind of thing, but we cannot avoid it because air is also a medium and it will allow some sort of flux to flow. So whatever is the flux, so flux will be, because this is a parallel path, right? Some of the flux is going here and some of the flux is going here. So flux overall will be phi core plus phi leakage. Okay, phi core plus phi leakage. So what I can say is that my phi core will be what? Phi core will be Ni, same mmf, right? Ni upon S core, and phi leakage will be Ni upon the S air, right? Whatever is the like air gap reluctance, that I will take. Okay, so there is a term known as the leakage coefficient. Leakage coefficient is the total flux, that is this phi divided by the useful flux. Why is it called useful? Because this phi core is actually the flux that is linking the secondary and primary that will be used in the transformer, and this leakage flux is actually unwanted. This will not be helpful in the transformer process, right? So that's why there is a term known as leakage coefficient, important for EE aspirants, EE ion, not important for EC. Just you need to listen to me, that's it. Okay, so to optimize this leakage flux, we always try to keep it as close as possible to 1, because then the total flux and the useful flux will almost be same. So ideal value will be, ideal value of flux will be equals to 1. Okay, so yeah, that was about the this flux linkage kind of thing. I hope you have understood this kind of things. This, sometimes this is called phi core, sometimes this is called as mutual flux. Okay, why is it called mutual flux? We will discuss about mutual coupling and all those things later on. It is called mutual flux because it is called mutual flux because phi leakage, because it is the flux linking the primary coil and the secondary, mutual. It is mutual to both the coils, same to both the coils. That's why it is also called mutual flux. Now there is another, like this, you already know about inductance. So we will discuss about inductance now. There is another term known as self inductance. What is inductance? Inductance is related with the flux. So flux is equals to Li, that is the like KVL kind of equation for inductance. This you have already learned in network theory, so I'm just explaining you. It is similar to if you remember, like V equals to IR, something like that. Okay, it is the inductance Ohm's law kind of thing. So here, where my L is self inductance of the coil, or what I can say, L will be equals to what? L will be equals to flux divided by I. So it will be what? It will be the flux, overall flux that is linked to the coil divided by the current. So it is basically total flux through the coil per unit current. So this is also another unit of self inductance. So what is the unit of self inductance? So it is flux over current. So it is unit of flux is Weber per ampere or Henry. Okay, or the unit of inductance is Henry. So L depends on the geometry. Okay, it is not like it is independent of any other thing. It is dependent on the geometry, similar to capacitor, similar to resistor. Okay, as resistance, right? Resistance value depends on the geometry, right? Rho L by A. So your inductance also depends on the geometry of the material. Okay, so like this formula was there, right? V induced was equals to minus d phi by dt, and I have used it equal to L dit by dt. How it comes? So d phi is that overall flux linked to the coil. So overall flux is what? It is minus d phi. Phi is what? Phi is overall flux linked to the coil, that is L into I. So I will write here L into I over dt. So this will be, L is a constant, it is not time dependent. So it will be L dit by dt. So from this, the equation actually comes that my induced voltage across the inductor will be minus L dit by dt. From here as well, you can actually calculate another unit. What is the unit? So this actually is, what if I take this on the right hand side? So L dit by dt. So what is the unit of Henry? So what is the unit of Henry? So this, right? What will be the unit of Henry? So Henry, right? L will be equals to V induced divided by dit by dt. Okay, so just I'm talking about the magnitude now. Okay, so this is, what is the unit of this? This is amp per second, and this is voltage. Okay, this is voltage and this is amp per second. So this will be unit of, like this is Henry, right? Unit of inductance is Henry. So this will be volt, like Henry also I can write it separately. The unit of Henry can be written as volt, like this second can go at the top, so this will be volt second per ampere. Okay, this is also another unit of Henry, and this negative sign just represents the opposition in change. That's it. Okay, negative sign just represents the opposition in change. Okay, so just one more point I want to come back to, that the self inductance of a solenoid. Okay, the self inductance of a solenoid, how is it calculated? Because the reluctance, to calculate the reluctance, it is very important. How is the formula derived? So I will just briefly, I will go through it. Okay, if you have ever studied EMFT, you will know that the magnetic flux density through a solenoid will be mu into Ni, where N is the number of turns per unit length. Okay, if you have studied class 11 and 12, you will remember that magnetic flux density is mu Ni. So for EC aspirants, you can ignore this discussion. EE and IN aspirants can listen to this discussion. Okay, so what is the self inductance of this coil? It will be overall flux linked by I. So magnetic flux density is mu into Ni. Okay, so what is the flux due to a single coil? Flux due to a single coil will be, like if I assume this cross section. Okay, so this is like a circle, and in a single turn, the flux link will be B into area. So this will be mu Ni into area. Area is pi r square, right? Whatever is the resistance, or sorry, whatever is the radius of this each turn. That is the flux due to a single turn. But I am calculating the overall flux linked in this coil, so that I will be able to find out the inductance. Because to find out the inductance, I will need the overall flux divided by the current, okay, through the coil. So overall flux will be, this flux is due to a single turn. Overall flux will be mu Ni pi r square. For n number of turns, it will be into n. Okay, into n. So this I will replace in this equation. If I replace in this equation, right, so this will become like n into mu Ni into pi r square, and current is I only. So this will be, current will be I only, I. Okay, current is I only. So ultimately what comes out is that this is n, L is n mu pi r square, correct? L is, yeah, n mu pi r square, and okay, where does the L come from? Okay, okay, this L. So one more thing is that this is small n, right? This is just a formula. I'm using the formula because this is not important at all. Just I want to show you like how this expression comes to. That's the only point. Like other educators will just simply tell you this expression. They will tell you, remember, I'm deriving you. Okay, I'm deriving it to you, so that it will be easier for you to remember. That's the only purpose. Except like this, the expression you can remember, right? So here, n is the number of turns per unit length. N is the number of turns per unit length. So what is n equals to? So if I have n turns, if I have total n turns, capital N turns, in a distance of L, so what will be the small n? Small n will be number of turns per unit length. So let's take a very small example. Let's take that I have 2 turns. Okay, I have 2 turns. Like let's take this example, 2 turns, or I don't know how many turns. This is 3 turns, right? 3 turns in a distance of 3 centimeter. So what will be small n? Small n will be number of turns per unit length. So it will be 3 divided by 3 centimeter. Okay, so it will be 3 turns per centimeter, correct? Or whatever units you want to get. Sorry, 1 turn per centimeter. So if I have 3 turns in 3 centimeter, so in a single centimeter, how many turns I will have? 1 turn. Okay, sorry for the noise. So same thing I'm applying over here, that if I have n turns in L distance, then in a unit length, what will be the number of turns? It will be n by L. Okay, so just here in place of n, I have replaced here with n by L, mu into I. Okay, so all this I have already explained in my EMFT full course. If you are ever doubtful about that EMFT, like about this concepts, you can go and watch that EMFT full course there. So those will be automatically clear, but this is not that important. Ultimate point is, overall flux links comes out to be this divided by the I. If I divide by the current, this will be mu small n square pi r square L, or this will come out to be like, if I replace in terms of capital N and L, this will be mu n square pi r square divided by L equals to mu n square A divided by L. Okay, so this is my self inductance. This is my self inductance. So this is the self inductance of a solenoid or any coil, of a coil with n turns. Okay, like n turns like this of any coil or solenoid, the self inductance will be this. This will be used later on. So educators will just simply tell you the formula. I have tried to derive, okay, derive you so that you can easily remember. This is a very, very important formula. This you have to remember. Okay, not for EC aspirants but for EE aspirants. This you have to remember. Okay, so like this was the about the inductor, basic things about inductor. What it does, it creates magnetic fields. What is the self-induced EMF? It is minus LDI dt by dt, same thing. Okay, now if two inductors are connected in series, it will be simply the inductance will be added L1 plus L2, and if I consider the mutual inductance, it will be plus minus 2m. This I will come, this we will discuss in the magnetic coupling. You have to ignore the fact for now. You ignore this for now. This will be discussed in the magnetic coupling lecture. Okay, for now you can ignore this discussion. Okay, so that's it basically for this lecture. I hope you have enjoyed this lecture. If you did, make sure to like the video, make sure to comment down. Okay, and in the next lecture we will do few assignment problems, and after that we will start with the next topic of this basics of electrical machines. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. So today we will start with the lecture 2 of our machines subject. So in this lecture we will solve few assignment problems. Okay, whatever we have discussed in the previous lecture, those we will solve. So EE and IN aspirants, of course, will try to solve them by yourself. EC aspirants just can watch me solve the questions. You don't have to take too much stress. Just understand how am I solving the questions. Okay, that's it. Because this is not completely in the syllabus of EC, but uh, still magnetic circuits are there, and if they want to, they can ask. This year also in 2025 they had asked a question from magnetic circuits. Okay, so that's why we cannot take complete risk. Okay, we will try to cover everything, but don't have to cover everything comprehensively. Just whatever I am telling you, just listen to that. This I am talking about EC aspirants. EE and IN aspirants, of course, have to solve everything by themselves. Okay, so try it out, try these questions by yourself, pause the video, and then I will solve. So let's solve this first question. A coil of 300 turns is wound on a non-magnetic core having a mean circumference of 300 mm. Basically, what is my inductance? My self-inductance is the flux linkage phi upon I. Correct? This we have discussed in the previous lecture. So I know that what is the total flux linkage? So if I assume each turn produces phi flux, and there are total n turns, so like my coil is somewhat like this, right? This is my coil, and in this coil, like this coil has 300 this coil has 300 turns, and I have a non-magnetic core. So they have told me it is a non-magnetic core. So like magnetic field lines will not pass through this core. It is there just for the physical support. Okay, whose circumference is 300 mm. So that means like this circumference means the perimeter. So the circumference is 300 mm. Okay, and area is 300 mm square. Area cross section means if I just cut this with a knife, whatever like section I will get, the area of that particular section, that is the cross sectional area, is 300 mm square. Okay, and if I assume that each turn is producing phi flux, because the same flux will flow basically. So what is the total flux linkage in this coil? The total flux linkage will be n times phi. Total flux linkage will be n times phi. That is the total flux linkage. Okay, so that is my total flux linkage. Now what is my MMF equation? MMF equation is what I know. My MMF will be equals to L into I. Okay, that is the balance equation, right? It is the balance equation. MMF is equals to L into I. So what is my MMF? MMF equals to N into I. This is my MMF, right? And if you remember that there was a formula of flux. Flux was equals to what? Flux was equals to MMF divided by reluctance. If you remember. And what is the reluctance? Reluctance is basically mu L. No, sorry, not mu L. L by mu A. This was my reluctance. Correct? If you remember. So from here I can directly find out the flux value. Flux value will be N into I into mu A divided by L. Okay, so this is something else, just delete this. So from here I can directly say flux is equals to MMF upon S. So this will be mu into Ni A divided by L. Okay, so this is my flux, but what I actually want my inductance, right? So what is inductance? So inductance ultimately from this equation comes out L equals to N phi by I. Okay, so my L will be equals to N phi by I know what is my phi, I know what is my I they have given in the question. It is constant value 3 amperes. Okay, so it will be equals to N will be there and this phi will be replaced with N into I A divided by L, and I of course is there, right? So I will simply get cancelled, like it comes out independent of the current, because inductance is like basically independent of current, right? So and of course mu is there, right? I forgot to write the mu will be there, mu will be there. So this will be mu n square A divided by L. Okay, so from here, like either like you can remember this formula in the previous lecture as well. I derived this formula, right? If you go this in the previous lecture, we discussed about this formula. It is mu n square A divided by L, or you can do with that, go with the derivation as well. Whatever is suitable for you, you can do it. Okay, whatever is suitable for you, you can do it. Now let's solve this basically. So if I solve this, this will be, so my mu is basically, it is a non-magnetic core, so mu r will be 1 here. Okay, whenever it is, they are telling it is non-magnetic, basically you can assume air is a non-magnetic medium, so you take mu r equals to 1, so your mu becomes mu naught into mu r, so mu naught into n square. N square is basically what is it, 300, right? 300 whole square into A is 300 whole square, right? So I will convert this into meters because I want to write everything in SI units. So square to meters will be 10 raised to power minus 6 meter square. Okay, divided by, of course don't forget to write the mu naught as well. What is the value of mu naught? Mu naught value will be 4 pi into 10 raised to power minus 7 divided by the length. Length is how much? Length is 300 length is 300 so this will be 300 into 10 raised to power minus 3. Okay, That is what your length will be. So now I can directly calculate the inductance value. So the inductance value, this will be 4 pi into 10 raised to the minus 7, 300 whole square, 300 whole cube. So the one 300 will anyways get cancelled. So this will be 9 into 10 raised to power 4 into 10 raised to power minus 6 divided by 10 raised to power minus 3. Okay, so this value will come out to be equals to 10 raised to power minus 3 is there, 10, and yeah, 36 pi into 10 raised to power minus 6 Henry. Okay, or I can write 36 pi micro Henry. 36 pi micro Henry. So this value will be equals to, so this value 36 pi, right? So 36 pi, 36 into pi, so this comes out to be 13.97 micro Henry. So this will be your answer for the question basically. Okay, so 113 is present in the this option B. So option B will be the correct answer for this question. So let's solve this next question. From next question onwards, EC aspirants can ignore. Okay, they can directly jump into the next lecture. Okay, they don't need to watch this question. Just this first question was important because this basic question can get asked, but like there is a very low probability, but this can get asked. Except this, EC aspirants no need to watch. You can directly skip to the next lecture, that is magnetic coupling. So EE aspirants, please focus and try to solve this question, and I will solve this question now. Okay, so we have a ferromagnetic core which is like a transformer uh, with uniform width on the three sides. Okay, or on all the three sides it has uniform width, that is the depth, right? Depth is 10 centimeter, that is fixed. Okay, this depth is fixed with other dimensions provided. So the other dimensions are provided here. Okay, you can see the other dimensions. Just the width is fixed. The coil, a coil with 200 tons is wound over the core on the left hand side of the core, given that the relative permeability mu r is 2500. Okay, so the relative permeability of the core is 2500. Determine the magnetic flux generated when 1 amp current is applied to the load. Okay, so we have to find out the magnetic flux. So how do I find out the magnetic flux? To find out the magnetic flux, basically what you have to do is phi will be equals to mmf upon the reluctance of the core. Okay, so it is basically, if I convert this into a magnetic circuit, it will be a mmf source and here and a reluctance here. Okay, so how will the flux flow? Basically, the flux, if a current is flowing, the flux will be somewhat like this. Flux will be somewhat like this. Okay, this is my phi. So this will be uh, basically flux, right? So actually the reluctance is different in different areas. So in this particular region, if I have some other color, I am running out of colors. Where are the other colors? So let me take the red color. So this region, right, has a different cross sectional area, and this region has a different cross sectional area. Why so? Because if you see that this depth is fixed, that is 10 centimeter. The depth is fixed, right? This depth is fixed, 10 centimeter. But this is not fixed actually. This is different. So in this case, this distance is given here 15 centimeters. Okay, this is given as 15 centimeters. So it is 15 centimeters. Okay, if I am able to get the space, so this will be 15 centimeters basically. 15 centimeters. Okay, and if you observe here, this is the depth, right? That is fixed, that is 10 centimeters. This depth is again fixed, that is 10 centimeters. Okay, this depth is fixed again 10 centimeters. What about this one? So what is this? This is again given by this, right? 15 centimeters. So in this case it is same, but in if you will observe in the next cross section, it will not be same anymore. So let's come to this one, right? This part. So if I check here, again this is the depth, right? Depth is fixed, that is 10 centimeter. But now if I see this distance, this is given here as, okay, this is also 15 centimeters. That's like all of them are 15. Okay, actually I guess I might have done something wrong. This is not 15 centimeters, sorry. This will be 10 centimeters only, or no, this is fine. This should be 15 centimeters only. And like, am I missing? No, this is also fine. So this should be 15 centimeters only. Okay, so this is also 15 centimeters. So this will be again, like, area will be same only, 150 centimeters square. The last one here, if I see here, the last one, okay, so this will be, this right will be given by this distance, right? This distance. So this is actually, this distance is 10 centimeter. This is again also 10 centimeter, right? Depth. So this is different here, except that everything was same. This is different. So this is 10 centimeters, this is 10 centimeters. So overall, this area is, this cross sectional area is 100 centimeters square. This cross sectional area is 100 centimeter square. Okay, and this cross sectional area is 150 centimeter square, and this one also is 150 centimeter square. It is a series circuit, right? 150 centimeter square. So what is happening is that if I check throughout, if I break it down into 4 regions, okay, it is a series circuit. So if I break it down into 4 regions, let's name this as 1, 2. Let me name this point as 1, then 2, then 3, and then 4. So in the 1, 2 region, okay, in the 1, 2 region, the area A12 is equals to, in this region, right? In this region, what is the cross sectional area? 150 centimeter square. So this will be 150 centimeter square. In the 2, 3 region, and what is the length? L12, right, is this distance. This distance. So what is this distance actually? So basically we have to identify the mean path length. So mean path length will be like, of course my flux will flow throughout the whole core, but my assumption is I will take a middle length. So I will take the length that is middle to these 2 points. Okay, so this is the middle point. So this distance is whole 15 centimeter. So this distance will be, as it is middle, it will be 7.5 centimeters. So this will be 7.5 centimeters. Okay, and this will be basically 7.5 centimeters. Again, as like this distance is 15 centimeter, so this distance will be 7.5 centimeter. Okay, and this distance also will be 7.5 centimeters. And this distance, if you see, is actually overall this distance is 10 centimeters. So this will be half. So this will be 5 centimeters. This will be 5 centimeters. Okay, that is the only difference here. So overall, for the 1, 2 section, so 1 point is here and 2 point is here. What is the overall length of the path? So this is 7.5 plus this overall distance is 30 plus 5. So this is 42.5. Okay, this L12 is equals to 42.5 centimeter. Okay, then A23 is equals to, again the area here is what? Area here is 150 centimeter. Now this is different, right? This is 100 centimeter square. So this will be 100 centimeter whole square, and L23, this length will be what? Again, this distance is how much? This overall is 15 centimeters, so this will be 7.5 centimeters. Okay, and the top distance is also 15 centimeters, and this is 7.5. So overall this will be, this length is 30 centimeters, so 30 plus 7.5 plus 7.5, that is 45 centimeters. So this overall distance will be 45 centimeters, and for 3 4 everything will be identical, right? So the area of cross section will be just same, that is 150 centimeters square, A34, and A L L34 will be the length, right? This length is how much? So this is like, this will be symmetrical, right? This and this will be same basically. So this length was 42.5, so this length also will be 42.5 only. Okay, so this length will be 42.5 only. And 41, so this will be, again here what is the area of the cross section? It is 150 centimeter square. So area of the cross section is A41 150 centimeter square. Okay, so my length L41 equals to, again it will be symmetrical, right? So this length was how much? This length was 45 centimeter, so this length also will be 45 centimeter only. Okay, so this length will be 45 centimeter only. So now I will calculate the overall reluctance. So this is a series circuit, right? So my overall reluctance will be S will be equals to S12 plus S23 plus S34 plus S41. Okay, so this will be equals to, S12, right? Again applying the same formula, it is simply L divided by, like, what is reluctance? Reluctance is L divided by mu A, correct? And mu is common factor, so mu I can take out. This will be L12. What is L12? L12 is 42.5 centimeter, and area A12 is 150 centimeter square. Okay, plus this also is same, right? L34 is almost same, like 34 reluctance is same, all the parameters are same, so I can simply multiply a 2 here. Okay, what about the other one? So other one, if you see, this parameter is quite different. 41 and 23 are actually different, because here the area of cross section is different. Okay, so this will be, if I write the 23, so it will be L23 is 45 centimeter divided by the A23, that is 100 centimeters whole square, plus L41 is 45 centimeter divided by A41 is 150 centimeter whole square. Okay, okay, So this will be what? So if I now calculate the values, so this is right, this is 75, and if I just calculate the values, I will just quickly calculate what will be the values basically. So this will be 42.5 divided by 75, so this is 0.567 plus 0.45 plus this is 45 divided by 150, so this will be 0.3. Okay, and remember like what is the unit here. So this was actually supposed to be in centimeter and this is centimeter square, so in the bottom I have centimeter, so I will convert that into meter. So this will be 10 raised to power 2. Just I have converted, like currently it is this unit is 1 by centimeter, right? 1 by centimeter. So how do I convert it into meter? So this will be 1 divided by 10 raised to power minus 2 meters, right? So if I convert this into meters, so basically this unit, this 10 raised to power minus 2 can go at the numerator, so this will become 10 square. That's it. Okay, just converting centimeter to meter, that's it. Okay, so this will be 1 by 4 pi into 10 raised to power minus 7. Also, of course, what is mu? Mu, actually I forgot this thing. Mu is equals to mu naught into mu r, right? So I have a mu r as well. Mu r they have given me. The relative permeability is 2500. So I have to write here into 2500 as well. Into 2500. So now we will actually calculate the values. So this value comes out to be, if I calculate 0.104 and okay, 4 pi I have divided already. Okay, so this divided by 2500 into 10 raised to power whatever the calculations we are doing, this will be equals to somewhat whatever the value here is. I'm not writing it, okay. I'm not writing it, so it will come out 4.192 into 10 raised to power minus 5 is there, so another 10 raised to power 7 and 10 raised to power 2 is already there, so 10 raised to power 9. So 4.92 into 10 raised to power 4, so it will be 4.1921 into 10 raised to power 4 basically. So this value will come out to be yeah, this value will come out to be 41921 what is the unit of reluctance? It is in what I remember is flux Weber. What was the unit of reluctance? That is what I am forgetting. Ampere turns per Weber, right? Yeah, because like if you remember, like your flux is equals to Ni by reluctance, so reluctance will be ampere turns per Weber. I also tend to forget the like units of reluctance, so just you can remember it like this. Okay, so this will be the reluctance. So ultimately what I have to find out? I have to find out the flux. So flux will be ampere turns upon reluctance. So ampere turns is N into I. So N is 200. Current is 1 ampere. So 200 into 1 ampere divided by 41921. So this will be just hold on, 200 divided by 41921. So this will be 0.0047, and in milliwebers if I want to write this 4.77. So in milli the value will come out to be something 4.77 milliwebers. Okay, so this will be the answer. I know this is lengthy, but I am guessing that in EE or IN someday they will ask a very basic question from this. Okay, so this basic questions also you should be able to easily solve. So this was a question of series magnetic circuit. Series magnetic circuit. Okay, so let's move on to the next question. So in this question we have been given a single phase 120 volt 60 hertz power supply. It is connected to the coil with 200 turns, and all these values are given. They are asking me the peak flux density in the core and the peak current flowing through the coil. Okay, so what is the peak flux density and the peak current? So it is a AC supply. So if I have a coil with a AC supply what happens? So again we will use that same formula, right? What is the same formula? Voltage equals to L dit by dt, or voltage equals to N d phi by dt. Okay, so all these values are given to me: core length, cross sectional area, all these things are given to me. They are asking me the peak flux density. Okay, so I know we have derived this expression in the previous lecture only. What was the expression? If you remember, the induced EMF expression for a simple coil of AC supply, ERMS, if you remember ERMS, we have derived this in the previous lecture, is equals to 4.44 F phi N. Okay, yeah, this was the expression, if you remember, F phi max. How did it come? Just like this, you might feel like, sir, this is something different, you did not tell this. I did tell you. Okay, so basically we derived in the previous lecture, my phi max was equals to root 2 pi into F into N1 into ERMS. Okay, that is what we derived in the previous lecture, correct? So what is root 2 times pi? So root 2 times pi is basically 4.44. So basically my phi max, this we have derived in the previous lecture, so I am not repeating it, will be equals to ERMS divided by 4.44 into F into N1. So ERMS was in the RMS value induced in the coil 1, right? So RMS value induced in the coil 1. So from here I can, like, this is my phi max value. So we told, right, if the RMS value of the supply is fixed, if the frequency is fixed, then the maximum flux density is also fixed. Not flux density, sorry, maximum flux is also fixed. But they are actually not asking me the maximum flux. What they are asking, they are asking me the peak value of flux density. Peak value of flux density. So what will be the flux density? Flux density Bm will be phi m by area, correct? So whatever we have derived here, just I need to divide by area, and that will give me the peak flux density. That will give me the peak flux density. So this will be 4.44 into F into N1 into E. That's it. That's it. Okay. So basically what I can say is, what is my E1 RMS? What is my E1 RMS? So this, if nothing is mentioned, by default you will assume this to be RMS value. Nothing is mentioned, you will assume to be RMS value. This we have discussed in complex power chapter. So this will be ERMS 120 volt divided by 4.44. What is my frequency? Frequency they have given me as 60 hertz. Okay, so this is 60 hertz into N1. So number of turns in the like primary, number of turns is 200. Okay, so this will be 200 into area, cross sectional area. So area is basically given here, right? Cross sectional area is given 20 centimeter square. So cross sectional area will be 20 centimeter square. So it does not actually depend on the like length of the core or something. Okay, 20 centimeter square. So I will convert this back into meter square. So centimeter square into meter square, simply have to multiply it 10 raised to power minus 4. That's it. Okay, so now I will directly find out the expression for peak value of flux density. So peak value of flux density will be equals to peak value of flux density. This I will calculate. So this will be 2 times this and this will be cancelled, right? This will be 2. So this will be 10. So this will be 10,000. This will be 10 raised to 0.1. So 2000. So 0.2 into 4.44, so 0.888. So this will be 1 divided by 0.888. So this value will be what? This, if I take the inverse, right, 0.888 inverse 1.26. 1.26 Weber per meter. Okay, or Tesla also you can write, meter square or Tesla. Okay, this will be the maximum flux density. Now let's calculate the peak value of current. What is the peak value of current through the coil? How do I calculate the peak value of current? So there are many ways to solve this question. Okay, many ways to solve this question. So if the circuit is like this, right, what I can do is I can replace this with its reactance, right? If the circuit is like this, I can replace it with its reactance. So this will be replaced with a inductive reactance, right? Inductive reactance, that is JXL. Okay, and this is my voltage. So what I can do is I can directly find out the magnitude of current, that is voltage over the reactance, and from there if I multiply the root 2, because all these are in phasor quantities and voltage is in RMS. So voltage is in RMS, so your current also will be in RMS. So at the end what I will do is, this is IRMS. So what I will do, I will I need to find out the peak value of current. Peak value Imax will be root 2 times IRMS. Okay, that will be the peak value of current. So I can directly say Im will be equals to, I have to find out XL. So what is XL? XL is omega into j omega into L basically. So, or omega L only. So omega I know. What is L? L, right? You have to again use that basic formula. Okay, to find out L, you have to use that basic formula. What is the basic formula? So L will be equals to n square mu n square into L divided by A. Correct? Or no, this is not correct. This is mu n square into A divided by L. This is the formula, right? So mu r, yeah, relative permittivity is given, relative permeability is given 2500, and mu naught is 4 pi into 10 raised to power minus 7. So this will be 4 pi, 4 pi into 10 raised to power minus 7 into mu r, that is 2500 into n square. N square is what? N square, n is 200 turns, so n square will be 200 whole square. So 200 whole square into A is 20 centimeters square. So I will convert it back into meters. So 20 into 10 raised to power minus 4 divided by L. So L is 100 centimeter, right? So L is 100 centimeter. So this will be 100 into 10 raised to power minus 2. I'm just converting back into meters. That's it. Okay, I'm just converting back into meters. So this will be what will be the inductance value. So I will calculate quickly. This will take a bit of time. So okay, let's cancel things out, right? So this 20 gets cancelled. 20 gets cancelled here. 5. This will go there. So this will be 10 raised to power minus 2, and this 5 can be cancelled here. 500. So this will be 4 pi into 10 raised to power minus 7 into 500 into 4 into 10 raised to power 4 and this is into 10 raised to power minus 2. Okay, so this will come out with, this will be 10 square and 10 raised to power 4, 10 raised to power 4 into 10 raised to power minus 7. So this will be 4 pi into 4 is there, 10 raised to power 4, 10 raised to power 2, 10 raised to power 4, 10 raised to power minus 3. Okay, and 4, and 5 is also there, right? So this will be 5 into 4, 80. So another 8 pi into 10 raised to power minus 2. So 8 pi into 10 raised to power minus 2, if I quickly write this, right, this will be 8 pi to 10 raised to power minus 2, that is 0.25. 0.25 Henry, 0.2513 Henry is the inductance value. Okay. So what is the current? What is the RMS value of the current? So IRMS will be V by XL. So voltage, RMS value of voltage already I know, that is 120 volts. So 120 divided by 120 divided by 2 into omega. Omega is like 2 pi f. So f is 60. So 2 pi f, and pi is also there, right? Into L. L is 0.2513. Okay. So this value, if I calculate, this will be 120 into 0.2513 into pi. So this into 120, this will be okay. So this is big actually. So 2 into 60 into pi into 0.2513, okay, into 120. So it comes out to be 1.2666 amperes. But they have not actually asked me RMS, right? What have they asked? They have asked me the peak value. They have asked me the peak value. So peak value will be √2 times the RMS. So it will be √2 times the RMS. This will be 1.79 amperes. Okay. So this will be the answer for this particular question. Now let's move on to the next question. So this is the next question, and I guess no, 2 more questions are left. Okay. So in this question, what we have to do, we have been given a magnetic circuit. Number of turns are also given. All this information is given. They are asking flux and flux density. Now remember, this is not a simple core, right? Here I have a gap. So if I have a gap, then first of all, again, if current is given, that is DC current. This is not AC current. This is DC current. So in DC current, what do we do? Simply we write our flux. Right? We don't use that equation 4.44 F pi N into phi max. We don't use that, right? We use that when we have a AC supply, but here we have a DC supply. So in case of DC supply, we will use the simple formula. Phi is equals to mmf upon reluctance. mmf upon reluctance. So mmf is equals to N into I divided by reluctance. Okay. So I have to find out the reluctance. So again, this is a series circuit. So the reluctance will be my overall reluctance. Again, if I convert this circuit, right, I will have a reluctance of the core, S core, and I will have a reluctance of the air gap. Okay, S core and the air gap, SG, and this is my mmf, that is N into I. Okay, so same thing, right? Same concept I will apply. So we can individually find out the reluctance of the core and SG. So S core will be what? So this cross sectional area will not change. So this cross sectional area they have given me, the area of the core and the air gap is same. Although you might have a question, sir, you have told in the previous lecture that there will be fringing effect. So you told that in fringing effect the area increases. Yes, you are correct. In case of fringing, the area will increase. But to simplify the question, they have told you don't go into the fringing effect. Assume that there is negligible fringing. Okay, that is what they have assumed. That is what they have told us, right? So they have told us the cross sectional area is same. Okay, that is what they have told us. Okay, so yeah, if there nothing is mentioned, you will assume fringing effect to be 0. Okay, you will assume fringing effect to be 0. So if I assume fringing effect to be 0, so S core will be L core, the mean path of the core, divided by the not this one. This is wrong. no, this is correct only. L core divided by mu core into the area of the core, cross sectional area of the core. So what is L core basically? L core, mean length of the core. What is the mean length of the core? So they have told me that mean core length they have given me as 50 centimeter and air gap length is 1 millimeter. So mean core length is 50 centimeter. If I want to write this in meters, this will be 15 to 10 raised to power minus 2. Okay, and my mu core is, what is my mu core is like relative permittivity of the core is 3000 and air gap relative permittivity is 1. So this will be mu not into 3000. So it will be 4 pi into 10 raised to power minus 7 into 3000. Okay, into area of the core. Into area of the core. So what is the area of the core? Area of the core is 15 centimeter whole square. So it is 15 into 10 raised to power minus 4. So this will be this, if we calculate, right, S core will be equals to let's do this. So this will be 60 here and this 10 raised to power 4 will go there, and this 6 into 90, 900, 900, 9 into 10 raised to power minus 2. So basically, right, here I have 10 raised to power minus 2, here I have 4 pi into 9 into 10 raised to power minus 7 into minus 2. So this will be 10 raised to power minus 9. So this will be 10 raised to power 7 divided by 36 pi. Okay, for now just keep it as it is. Let's calculate the air gap reluctance. So SG will be LG divided by mu G into EG. Okay, so LG divided by mu G into AG. So LG is 1 millimeter. Okay, 1 millimeter. So 1 millimeter is 10 raised to power minus 3 in meters. Mu G is what? Again, air gap permeability is mu R is 1. So it will be mu naught only. So 4 pi into 10 raised to power minus 7 into AG. Okay, so AG is like a core area is same only, that is 15 into 10 raised to power minus 4. Okay, minus 4. So this will be basically equals to uh, 10 raised to power minus 3 is here, so no, 10 raised to power minus 11, right? So this will be a bit difficult, just bear with me. So 10 raised to power minus 3 into 10 raised to power 11 divided by, this is 60 pi, correct? So ultimately this will become 10 raised to power 7 divided by 6 pi. Okay, so this becomes 10 raised to power 7 divided by 6 pi. So from here I can overall calculate the reluctance will be the sum of these two, right? So it will be sum, so it will be S core plus SG. Okay, so it will be 10 raised to power 7 if I take common, divided by 1 by 36 pi plus 1 by 6 pi. So pi also can be common, so it will be pi and 6 also can be common, right? 6 pi if I take common, plus 1 10 raised to power 6 pi 7 by 6. Okay, so this value will be 7 divided by 36 pi. Okay, so yeah, this is the reluctance basically of the whole combination. So what is the question? Question is determine the flux and the flux density in the air gap actually. So flux will be constant throughout, right? Flux will not change. So flux, for calculating flux, anyways, I have to find out the overall reluctance. So what will be the overall flux? Overall flux will be Ni divided by the overall reluctance. So N number of turns is 400, current is 1 ampere. So it will be 400 into 1 divided by the reluctance. So what is the reluctance? So reluctance will come out to be this value, right? Reluctance is this value. So it is 7 into 10 raised to power 7 into 36 pi. Okay, so I have to calculate this value. What will be this value? So this will come out something in milliwebers. Okay, so if I milli or micro, I will just quickly calculate this. So this will be 400 into 36 divided by 7 into pi and 10 raised to power minus 7 is there, right? Yeah, so this will come out to be somewhat like 646.2 micro Weber or 0.6462 milli Weber. Okay, so this is the flux. Flux is done. So this is the part one of the answers. Now they are asking me the flux density in the air gap. So for calculating the flux density in the air gap, I have to divide the flux divided by the air gap area. Okay, which is same. In this case, it is same. Okay, assumption is as nothing is mentioned about fringing, okay, it will be basically AG, the air gap length will be same as AC. Okay, so my flux I have already found out, that is 0.662 milli, 0.462 milli Weber divided by the air gap cross sectional area. So the air gap cross sectional area AG is equals to already I know this, that is 15 centimeter whole square. So this will be 15 centimeter whole square. So this will come out to be, I will just quickly calculate, am I correct? Yes, this is correct only. So this, right, milliwebers is there, so this will be 6.462 into 10 raised to power minus 3 basically, divided by 15 into 10 raised to power minus 4. So this is 6.462 divided by 15. So it comes out to be around 0.4308 Tesla. Okay, this will be the flux density on the air gap. Now let's calculate, they are asking to calculate the inductance of the coil. So they are asking me to calculate the inductance of the coil, not the inductance of the overall system. No, they are just asking me to calculate the inductance of the coil. So for that there is a like simple formula that we have already derived previously as well, that in the part B, the inductance of the coil L will be equals to mu N square A divided by L. Okay, so this will be equals to mu naught mu r. So mu naught is 4 pi into 10 raised to power minus 1 into n mu r. Mu r is the relative permeability. The relative permeability is 3000, right? 3000 into n square. N square is 400, so it will be 400 whole square into E. A is this, right? 15 into 10 raised to power minus 4. That is same cross sectional area. Like this is the core. Whatever I am doing, these are all like the coil, right? Coil length, and LC is also coil, mean length of the coil. So cross sectional area will, like in this case, the cross sectional area of the coil and the air gap is same. So this will be 15 into 10 raised to power minus 4 divided by LC. So what is the length of the core? Length of the core already we have written here as well. That is 15 to 10 raised to power minus 2. It is in centimeters, right? So it will be 15 to 10 raised to power minus 2. 50, right? It was 50. Yes, it was 50. So this L will be equals to, if I want to, like they have asked us the this inductance, right? So there are multiple ways this, like this you can solve, or if you remember, L is equals to flux, right? Flux over the current, right? That also. So you know the flux. What is the total flux linkage? Total flux linkage, right? Phi is 0.64262. Even like without doing this like complex calculation, phi is 0.6462 milliweber divided by the current. So what is the current? Current is basically 1 ampere, right? Current is 1 ampere. So current is 1 ampere. So from here you can directly find out the inductance value without doing any calculation. Okay, but remember, you're forgetting one thing. This flux was the flux in a single turn. If I have multiple turns, it will be n phi, right? Just one, that thing you have to remember. It will be n phi. So the number of turns. So how many number of turns I have? Number of turns will be n is given as 400. So that only that thing you have to take care of. So number of turns is 400. So this will be 6462 to 10 raised to power minus 3. Okay, so this will be, if I calculate this value, this will be 6.6462 0.6462 into 4, and okay, so this will be 0.258 Henry. Okay, so 0.258 Henry will be the answer for the inductance. So that is the inductance. Like if you solve this equation, right, here also you will get the same value. The inductance is done. Now considering that the fringing effects increase the effective cross sectional area of the air gap. So now they are considering. So if they want to consider, right, they will tell you that they are considering the effect of fringing. So here they are telling me that the effective cross sectional area increases of the air gap increases by 5% if we consider the fringing effect. So then the total reluctance of the magnetic circuit, what will be the total reluctance? So the core reluctance will not change, okay, but due to fringing, the effective area of the air gap increases by 5%. So the air gap area will increase by 5% of the actual area, core air gap, right? So it will be 1.05 of the actual core area. So what is the difference? So if previously my S air gap, what is it equals to? It is equals to L divided by mu gap, right? So nothing has changed, just the Eg has changed, right? So if I had, let's say, now the new reluctance Sg dash, the Lg is same, the mu g of course is same, it does not change, just the Eg dash has changed, right? They have told me to assume a greater area, cross sectional area. So now if I find out the ratio of Sg dash over Sg, so if I find out the ratio of Sg dash Sg dash over Sg, Okay, this value will be what? This value will be Lg divided by mu g, Eg dash divided by Lg divided by mu g into Ag. So this will be Ag divided by Eg dash. Okay, so this value will be Ag divided by Ag dash. So Ag, like my, this is Ag dash is basically 5% more than the previous one Ag. So Ag dash, so I need to find out the value of Ag divided by Ag dash. So it will be 1 by 1.05. Okay, because what I need to calculate? I need to calculate, ultimately I need to calculate the new reluctance, right? Sg dash, because core reluctance will be same. Core reluctance will not change. S core will be same, right? Because its cross sectional area is not changed, its length is not changed. Only Sg dash has been changed. So Sg dash will be Ag upon Ag dash, that is 1 upon 1.05 into the old reluctance Sg. So what was the old reluctance? Sg, the old reluctance was this value, right? If you remember, Sg was coming out to be 10 raised to power 7 divided by 6 pi. So this will now become 1 divided by 1.05 into 10 raised to power 7 divided by 6 pi. Okay. So now the overall reluctance will be what? Overall reluctance will be S, right? It will be 10 raised to power 7. S core will not change. Sg will change, right? Sg will change basically. It will become Sg dash. Okay. So this S core is S core is basically 10 raised to power 7 divided by 36 pi. 10 raised to power 7 divided by 36 pi. Plus this 10 raised to power 7 divided by, what is it, 6 into point whatever this is, right, 1.05 into 6 pi. Okay, so this overall value will come out to be equals to, if I take common, 10 raised to power 7, 10 raised to power 7 I will take common, so this will be 1 by 36 pi plus 1.05 into 6. Okay, so this is 1 by 6. Look, if I take 6 pi common, right, 6 pi also if I can take common, this will be 6. Okay, I don't need to multiply 6. Okay, sorry, this will be 1.105. so if I just add these two values, so 1 divided by 6 plus 1 divided by 1.5, so this will be basically 1.12 into 10 raised to power 7 divided by 6 pi. Okay, so this will be divided by 6 divided by pi. So this comes out to be 0. Or I can write this in terms of this, 0.59 is something like this is there, right? So if I want to write, if I'm just thinking how can I write it properly. So 10, this is correct only, yes. So this will be 0.593 micro ampere turn per Weber. Okay, so your value comes out to be 0.573, right? Not micro, sorry, what am I talking about? Not micro, sorry, what am I talking? Okay, not micro. Okay, so this is 10 raised to power 7 multiplied, right? So previously what we calculated, this right here, we calculated something, yeah. S score was previously this. Okay, so here, right, if I want to write this, like this is the value basically. So this is the S score, like you can put it in any number, like this will be the ampere turn over Weber. Okay, so you can convert this in any term you like, you will be able to find out the value. Okay, so total reactance will be this will be the answer of this question. Okay, if the fringing is considered, so this is a very very good question. If the fringing is considered, if it is neglected, your area of the core and area of the air gap will be same. Okay, so yeah, that was the answer. This is a good question. Now let's move on to the next question. Okay, and what we have to find out in this question, the magnetic circuit shown below has uniform cross sectional area. Okay, uniform cross sectional area, and air gap of the air gap is 0.2 centimeter long. The mean path length is shown 40 centimeter. This whole mean path length is 40 centimeter. Okay, when the core relative permeability is assumed to be infinite, the magnetic flux density computed in the air gap is 1 Tesla. So that they are telling me that if the if the permeability is infinity, the magnetic flux density in the core is 1 Tesla. With same ampere turns, if the core relative permeability is assumed to be 1000, the flux density in Tesla will be equals to what? That is what they are asking. So ultimately, right, they are telling me that if my mu r is infinity, then the magnetic flux density is 1 Tesla. Okay, how is it possible? So how do I calculate the magnetic flux density basically? So the flux, right, flux is equals to what? Flux is equals to mmf upon reluctance. Okay, and we are not changing any currents and something, right? They have not mentioned we are changing any currents. It is constant, same. Okay, under same condition. So they are telling me with same ampere turns. So mmf will not change, reluctance will actually change. So when the mu r is infinity actually for the core, what will happen? The reluctance of the core, right? S core. S core is what? S core is L core divided by mu core into A core. Okay. So this will be equals to what? L core is how much? So L core, right? L core, I need to find out L core. So L core is basically whatever it is. So mu core is what? Mu core is mu r into mu naught. So if mu r is infinity, so in the case 1, if mu r is infinity, then this will be 0. Sg will be there. Sg will definitely be there, right? Sg will be some value, that is Lg upon mu g, that is mu naught only, because mu r is 1 for air gap, into Ag. Okay, Sg will be there. So in the case 1, the flux, right, will only be due to the mmf divided by Sg, because what is my overall reluctance? Overall reluctance is S core plus Sg, and my S core is 0, right, because permeability is infinity. So only it will be equals to Sg only. It will be only equals to Sg only. Okay, so I can directly say this. Now let's calculate for the case 2. Okay, for the case 2, things will be a bit different. For the case 2, like what is the flux density then? Flux density in the case 1, it is very simple, right? It is phi by A. Okay, so this is phi 1 and this is phi 1 by A, B1. Okay, because A will not change, right? A, this is like area of the this core, that will not change. So, and fringing is not mentioned, so we will assume fringing to be 0. Now what I will do is I will directly write down for the case 2. In case 2, they are telling me that my mu r is 1000. Okay, so my S core will not be 0 anymore. So S core will be what? S core will be L core divided by mu r into mu naught. So it will be 1000 mu naught into A core, whatever is the area of the core, right, which is same as the air area. What is Sg? Sg will not change, right? Sg will be same. It will be Lg upon mu g into Ag, and Ag is A core because fringing is neglected. Ag is A core. So what I will do, what will be the flux now? Flux phi 2 will be again the same thing, mmf upon the reluctance. So in this case, the reluctance will be the combination of S core and Sg, because S core previously was 0, now it will not be 0 anymore. So it is mmf upon S2. So it is S core plus Sg. So it will be equals to mmf upon S core plus Sg. So this will be basically whatever this value is, right? So now what I will do, they are asking me what will be the flux density. So first I will calculate the, like, what is the flux density in the second case. Flux density again phi 2 upon E, it does not change, right? So ultimately let me find out the ratio of flux in the case 2 and case 1, compare the fluxes, right? So in the case 2 it is mmf upon S2, correct? And in the case 1 it is again mmf upon S1, because in the case 1 it was basically only Sg only, right? So this will come out to be, this will cancel out. So this phi 2 upon phi 1 will be what? Phi 2 is B2 upon area and phi 1 is B1 upon area. So this will be B2 upon B1 equals to mmf will get cancelled. S1 is Sg, so this will be Sg divided by Sg plus S core. Okay, if I divide by Sg on both sides, and B1 is 1 Tesla, so I'll replace B1 with 1. So this will be B2 divided by 1, and Sg this will be 1 divided by 1 plus S core divided by Sg. Okay, now I will calculate the ratio of S core divided by Sg. So what is S core? S core is L core divided by mu core, that is mu naught into 1000, right? Mu naught into 1000 into A core basically, and A core and Ag, air gap area, both are same. So this will be Lg upon mu naught, and like in case of air gap the relative permeability is 1 into Ag. So as no fringing effect is mentioned, so Ag and Ag, A core will get cancelled, mu naught and mu naught will get cancelled. So this will be L core divided by Lg into 1000. Okay, now what is L core divided by Lg? They have mentioned, right? Something they have mentioned actually. So from here I can directly find out what is L core divided by Lg. So L core, right? L core will be what? 10 centimeter. This is overall this is 40 centimeter. But out of that 0.2 centimeter I have to subtract, because this 0.2 centimeter is taken out by the air gap. So L core will be 40 minus 0.2 and Lg will be 0.2 into 1000. Okay, 0.2 into 1000. So this will be equals to 39.8 into 0.2 into 1000. So this will be equals to, if I calculate this, this will be 39.8 divided by 1000, whatever this value is, this divided by 200, correct? So 0.99. So this comes out to be 0.199. Okay, so ultimately my B2 will be 1 divided by 1 plus 0.199. So it is 1 divided by 1.2. So plus 1 inverse. So this comes out to be around, B2 comes out to be 0.834. okay, so just if you ever feel like whatever I am teaching you is useless, okay, like in the first lecture we learned a lot of things, right? I told you a lot of things. It is actually not useless, okay, it is actually not useless. Everything is useful because this actually came recently, gate 2019 IT Madras. So it's not like I'm uh, like telling you some concepts which will not be required. Every single thing will be required whatever I'm teaching you, okay. For branches which is not important, for those branches I've already told them that easy guys, you can ignore this, you can already move on. But electrical guys, you need to watch this, because whatever I've explained in the first lecture, that is actually important, okay. So whatever part, of course I did not derive everything, I did not derive self inductance, all those things, because that is not the correct time to derive. That I have already derived in the AMFT portion, and that is not required here in machines. That is not required. Whatever amount is required, that much I will teach you, don't worry. I will teach you everything to the optimum level. I will not teach you anything super extra, because extra things I will, of course I will teach you extra things, so that in the exam if something tough comes up you will be able to solve it. But I will not teach you something out of the syllabus or something, right? That will not teach, okay, because that will just waste your time. That's why our lectures, right, are totally sequential and very systematic, okay, very systematic. So yeah, answer will be 0.84 Tesla or Weber per meter square. Okay, this will be the answer. Now, this is the final question, last question. I know you are telling, sir, how long will you go? How long will you go? I cannot take anymore. I cannot take it anymore. So this is the last question that we'll solve. This is a question of parallel and series circuit. So a bit difficult, like not that difficult, but just a bit difficult. So what we are observing is we have a magnetic circuit. It consists of a cast steel. Okay, this core is cast steel with dimension as shown. The mean length from A to B through either the outer limb is 0.5 mm, 0.5 meters. Okay, the mean length from A to B. So A to B for the outer limb, these are called as limbs, okay, is 0.5 meters, and for the central limb the mean length is also 0.5 meters. Okay, both of them are 0.5 meters only. Okay, okay. Air gap, air gap length also they have given me. This also they have told me, right? This is 1 cross 1 centimeter. 1 cross 1 centimeter means this cross section is 1 cross 1 centimeter. And this also is, okay, 1 cross 1 centimeter. This cross section is also 1 cross 1 centimeter. That is same only, that will not change. Okay, in magnetic circuits shown, it is required to establish a flux of 0.75 milliweber. Okay, so the flux that is required to establish is 0.75 milliweber, 0.75 milliweber. And in the air gap of the central limb, okay, that is what I have to establish. Determine the mmf of the exciting coil if for the core material mu r is infinity. Okay, so they are telling me that mu r is infinity, so the question is actually simplified, very simplified. So mu r is infinity. If the mu r is simply infinity, the reluctance due to this path, right, is almost zero. Reluctance due to this path is almost zero. So what reluctance is left? Only the reluctance due to this air gap and this air gap, right? Because if mu r is zero, sorry, if mu r is infinity, then reluctance will be zero, correct? Because my reluctance of the core will be what? L core upon mu core upon A core. Okay. So yeah, so if mu core is in, like mu r is infinity, this will go infinity, this will go zero. So my circuit, right, if I break this down, my circuit, right, equivalent circuit, here I will have a mmf of Ni, I will have a reluctance due to the first path. So this one will cause some reluctance, that is, let's assume this as Sg1, and this path will cause some reluctance, this air gap, right, this will be Sg2, and both of them are parallel. Why? Because the flux, if you see, is getting divided between phi 1 and phi 2. So this path I will name as phi 1 because they have written here. So this will be Sg1, and the other path will be Sg2. Other path will be Sg2. That's it. Okay. So Sg1 and Sg2. Okay. Now, what have they have asked, like what is the value of the flux? What is the value of the mmf that is required to establish a flux 0.75 in the air gap. So in the air gap, we have to establish air gap of the central limb. Okay, here also we have a air gap, right? Okay, I missed this point. Here also we have a air gap. So that is the most important point, right? So if you see this air gap, right, is common with phi 2, is common with phi 1, right? This air gap. So this air gap is common with both phi 2 and phi 1. Actually, this reluctance, the reluctance caused by this air gap will come somewhere around here. Okay, SG, simple SG. Okay, so this will actually stay here, right? This will actually stay here, no matter what. This will actually stay here. Okay, so like in a better way to draw this, I will draw a better way. So my, like, I'm producing my mmf here. So this is the place where I'm producing my mmf. Okay, and here I have a reluctance SG that is common to both the path 1 and path 2. So this is, let's assume this as phi 2. So here I will have another reluctance, that is SG2, and here I will have another reluctance, that is SG1. Okay, so this will be phi 1, this will be phi 2, and phi 1 and phi 2 are common here. This reluctance is common. So they are asking me to establish a flux of 0.75 Weber in this, in the central limb, that is in this reluctance. Here I have to establish a flux of 7.5 milliweber. Okay, this will be basically like what will be the mmf required. So mmf required, right, will be basically overall, like I have to find out the equivalent reluctance, right, of this whole system. So the equivalent reluctance of this whole system, first of all, these two are in parallel. So equivalent reluctance of this will be S will be equals to SG1 into SG2, as they are in parallel. So I can write it down. SG1, just the parallel combination formula, SG1 into SG2 SG1 into SG2, SG1 plus SG2. Okay, plus this reluctance, right, because it is in series with all those ones, just equivalent circuit, right? I'm just using the equivalent circuit, that's it. Okay, so this will be plus SG. Okay, so how do I calculate this? So what is SG1? SG1 is mu, like air gap is same, right? So it will be this length air gap distance, no sorry, this one, right, that is LG1. LG1 is LG1 divided by mu g into AG1. This AG1 is actually constant to everyone, right? This AG air gap, like cross sectional area is same. Cross sectional area is same throughout, that is 1 into 1 centimeter square. Cross sectional area is same throughout, so it will simply get cancelled out. Okay, it will simply get cancelled out. So I don't have to calculate that. So plus, sorry, not plus, into LG2 divided by mu g AG divided by LG1 divided by mu g AG plus LG2 divided by mu g AG. Okay, so this value here, what will it will come to, it will be LG1 into LG2 divided by, so So mu g upon Eg will get cancelled. So 1 mu g upon Eg will still be here, right? 1 mu g upon Eg will still be here. Okay, and this will be Lg1 plus Lg2, and of course don't forget that you have this third reluctance as well, right? So this will be Lg upon mu g Ag. Okay, so plus Lg upon mu g Ag. Lg is the like central limb air gap length, mu g Ag. So this value will be, if I take common, mu g upon Ag, this value will be Lg1 Lg2 divided by Lg1 plus Lg2. Okay, for now I can write the values, right? So what is the Lg1 and Lg2? Lg1 is 0.25, 0.025, and this is 0.02. So this is 0.025 plus 0.02. Now as they are in ratio, so it does not matter actually. So automatically the centimeter unit will automatically get cancelled out. Okay, or no, 1 centimeter unit still will be there, right? Yeah, 1 centimeter unit will still be there. This will be 0.025 plus 0.02 in centimeter plus Lg. So what is Lg? Lg is this air gap length is 0.02. So this is also 0.02. So this will be 0.02, and remember all this in centimeters, so I have to multiply 10 raised to power minus 2 to convert it back into meters. Okay, to convert it back into meters, I have to multiply 10 raised to power minus 2. So this will be 1 upon mu g. Mu g is 45 into 10 raised to power minus 7 into Ag. Ag will be the air gap length. So Ag will be the air gap length. So air gap length will be what is the air gap? Sorry, air gap area, right? Air gap area is 1 centimeter square. So 1 centimeter square is the air gap area. 1 into 10 raised to power minus 4 in meter square basically. So this will be 0.045 divided by, okay, sorry, this here, right, a multiplication sign was there actually, sorry. So what will be the value? So I will just quickly calculate this value. 0.025 into 0.02 divided by 0.025 plus 0.02 plus 0.02, 0.03 into 10 raised to power minus 2 is there. So this will be 10 raised to power minus 11. This will go up 10 raised to power 9. So 10 raised to power 3 into 10 raised to power 7 divided by 4 pi. Okay, this is the reluctance actually, overall reluctance of the system. But I'm not interested in this. What am I interested in is I have to develop like my flux. Phi will be what in the central limb? It will be mmf upon the reluctance. So I have to calculate the mmf. So it will be flux into the reluctance. So flux, they have told me I have to establish a flux of 0.75 meter, milliweber, 0.75 milliweber, 0.75 milliweber into reluctance. So reluctance I have already found out, it is 3 into 10 raised to power 7 divided by 4 pi. So this value will be equals to what? So this value will be 0.75 into 3, so 2.25 into 10 raised to power 4 divided by 4 pi. Okay, divided by pi divided by 4 into 10 raised to power 4. So 171790. Okay, am I making any mistake? That is what I am trying to identify. 1790. Okay, I will just quickly check because I'm not matching with my answer. I'll just quickly verify. Yeah, one small mistake I had made is that here, right, I did not notice that this length is 2 centimeter. Okay, so actually this is 1 cross 1. That means like this side is 1 centimeter and the inside, right, inside is also 1 centimeter. So the cross section is 1 cross 1. Okay, here actually the depth is 1 centimeter but the length is 2 centimeter. So the cross section area of the middle one, right, AG, is actually 2 cross 1 centimeter square. So it is twice the area. So I made a mistake here, so my bad. So this, right, SG, what will be the difference is this will be AG only, this will be AG dash. Okay, which will be twice. So AG dash will be twice of, this is AG dash, AG dash will be twice of AG. That is the mistake that I had made, so that's why the answer was coming different. Okay, so this will be AG dash and this will be divided by 2. Why? Because I have taken common AG and AG dash is 2 AG. So if I take common AG, 2 will be still there. So this will be 0.1 added with this. So this will be basically if I calculate this value, right, this will be just hold on, I will calculate, quickly calculate. This will be 0.025 into 0.02 divided by 0.045. So this will be 0.011 plus 0.01. So this will be 0.0211. Okay, so this value ultimately will come out to be, this will be 2.1111 and this value will come out to be whatever this value is. Okay, I'm not calculating this value for now. So here, right, there will be changes. This will be 2.11. So this will get changed to into 100 into 0.75. Okay, divide by 4 into pi. So this comes out to be 1044. So like roughly the answer will be, this is 1024, right? So this will be 2000 sorry 1243 ampere tons. Roughly the answer will be 1000, this many ampere tons. So this will be the mmf required to establish a flux of 0.75 milliweber. Okay, this is the amount of ampere tons that is required. So answer will be 1243. This will be the answer, and that's the end of this lecture. This lecture also was extended, but this was needed. Okay, these kind of questions will get asked, so we have to solve these kind of difficult questions. Okay, that will be really helpful. Like one day they will ask you this difficult question from magnetic circuits and you will be not able to solve. Okay, so that was the main purpose. You should be able to solve all the questions. So that's it basically from this lecture, and I will meet you in the next lecture with magnetic coupling. Until then, happy learning, and please make sure to like this video and comment down if you learned something new from this video, whatever you feel regarding this lecture or this whole series, right? Please make sure you comment down on the video. That really helps us a lot, that really keeps us motivated. That is the only one thing that we wait for whenever we post a video. We wait for your comments, we wait for your likes, all those things, right? So that like if I'm bringing something completely for free, this much hard work I'm doing, so in return of course we expect something, right? The love from you guys. So that's it from my end. Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with a lecture 3 of our chapter 0 from electrical machines, prerequisites of electrical machines. So just wanted to say at the starting itself, if you are enjoying this whole series, and complete machines will be covered on YT itself for free. So if you are learning something new and whatever you're feeling, right, if your concepts are getting clear, please make sure to comment down in the first video. This will be the first video. Please make sure to comment down in the first video, because most of the students will continue this whole playlist only after they see the comments in the first video, right? So that really helps us out. That really like this will be really appreciable if you comment down and put your thoughts, whatever you feel like about the lecture. If you are enjoying the lecture, you can put it down. If you are not enjoying, why you're not enjoying, that also you can put it down. Okay, so let's start. So in this lecture, everyone will watch ECEEIN. Everyone, all the branches will watch this lecture. This is the magnetically coupled circuit and the dot convention, because this is in the syllabus of EC. This can get asked, and this year only a question was asked in GATE 2025. So let's start with the first topic, that is self-inductance. So in the previous lecture 1, I gave you a brief overview about self-inductance. Today we will understand more about self-inductance. Okay, so let's take a coil. Okay, with n turns, and the voltage induced in the coil due to changing magnetic field is given by Faraday's law. This I have already discussed that what is Faraday's law. What is Faraday's law? Faraday's law is states that induced voltage. For now, just discussing about the magnitude. For now, just discussing about the magnitude. The magnitude of the induced voltage will be equals to n d phi t by dt. Okay, the rate at which the flux is changing and the number of turns in the coil. Okay, that is what my flux is. That is what my like induced voltage is. And what is phi of t? So let's assume that my input current source is a AC source, because like flux will only change if I have a AC source. Flux will not change if I have a DC source, because current will be constant, and if current is constant, then flux also will be constant. Why? How? So flux, right? Flux phi is equals to mmf upon reluctance. Okay, so it is Ni by S. So of course I is constant, flux will also be constant. If flux is varying, current will also be time varying. So if my current is, let's say, I of t is some Im sine omega t, then my flux, right, also like it is just proportional, right? My flux is just proportional to current. So my phi of t will be equals to phi m sine omega t. Okay, so this is my flux. So what will be the induced voltage? So induced voltage, right, like the field lines, right, if you see, the flux will also be sinusoidal. So what is the crux? Crux is this flux, right? This flux is what? The number of magnetic field lines. The number of magnetic field lines. So the number of magnetic field lines that is flowing in this whole loop will actually keep on changing. So what will happen? It will keep on increasing. So magnetic field lines will initially increase. It is a sinusoid function, right? Sinusoid is like what? Sinusoid is somewhat like this, right? So field lines, and it has a direction. So let's assume that the positive is in the clockwise direction. So initially field lines is increasing in the clockwise direction, then slowly again it will decrease in the clockwise. Still the field lines will be in the clockwise direction, and at certain time, this is not voltage, sorry, flux. After certain time, what will happen? The field lines will be negative. Negative meaning the direction will be opposite. Initially it was clockwise, now it will be anti-clockwise. That's the only thing. That is the only meaning of negative. So negative, and the field lines will increase in the negative direction. So now anti-clockwise direction field lines will increase. So it will be more dense. Okay. So that is what, like visually, what it represents. So what is inductance now? What is self-inductance? So self-inductance is the property of this opposing change, right? Self-inductance actually is the property of oppose in change of flux. Okay, actually originally it is the opposing change of flux, and I know that my flux is just proportional to current only. Flux is just proportional to current only. So I can directly write that it basically means it is like it opposes the change, opposes the change, opposes the change, opposes the change in flux, or in other words, I can write it opposes the change in opposes the change in what do you call current. Okay, because current is just proportional to the flux only. Current is just proportional to the flux. How does it oppose the change? The opposition is done by this induced voltage. So inductor induces a voltage which helps in opposing the change in current, or in turn the change in flux. Okay, that is the crux. That is what inductance is, and the property that represents this, right, is known as the self inductance. So L is basically the opposition in change in inductance. So this Faraday's law we already know, right? Faraday's law we already know, that is V is equals to N, like I'm just talking about magnitude right now, magnitude of the induced voltage is equals to N d phi by dt. Okay, so I can directly write here that my V will be equals to N. This d phi over dt can be written in two parts. So d phi change in flux with respect to change in current into di change in current with respect to change in time. Okay, so what I did, I just multiplied and divide by di. That's what I did. Okay, that's what I did. So this, right, this term represents the opposition of change in flux with respect to current. Okay, so basically this whole thing, right, this d phi over di actually is L. This whole thing is actually L. Okay, so your V is L di over dt. From here only we get the equation actually. Okay, so this whole thing we write as L, and this is the equation that you see in your inductor, that V is equals to L dit by dt. Now if I draw the flux and the current relationship, okay, if I draw the flux and the current relationship, because I have told you that flux and current are proportional to each other. So if current increases, like what is flux? Flux, right? Flux is mmf upon reluctance. So this is not I, this is S. mmf upon reluctance. So this will be mmf upon reluctance. So mmf is n into I by S. So all these are constant terms. So flux is directly proportional to the current. So it is like linearly, it will linearly vary. But this is the ideal curve, linear curve. This is the flux versus current curve, right? But practically this does not happen actually. Practically what happens? Practically every coil, every core will have a saturation. So this is the ideal curve. Practically what will be happening is that so here, right, practically what will happen, if I keep on increasing I, there will be saturation. There will come a point where the core will simply saturate and it will not follow. Okay, this relationship will not follow. But we are assuming that we are in this range where this phi I is following. Okay, so like you get a formula. Okay, you get this formula, right? If you remember, that your L is equals to flux linkage by current. That is actually not exactly correct. That is actually not correct. If we are in the linear region, then it is correct. Why? Because like if I find out the, like it is basically slope, right? L is the slope of this phi I curve. L is the slope of this phi I curve. So this is equals to d phi by dt. That is the slope. D phi over di, that is the slope of this curve, right? So in this case, as we are lying in the linear region, so it will be what? Phi, some random point, phi minus 0 divided by I minus 0, because at 0 current, flux is also 0, so it will be phi by I. But if I am in this region, right, then of course L is not the same. Okay, so just be careful. Whenever we discuss L is equals to psi by I, we are assuming that we are in the linear region. Okay, that is our assumption. It will not always follow. Okay, so from here you can also calculate the value of L in terms of reluctance. This we have already done previously as well. Okay, just revising you this thing, that this L is equals to what? L is equals to psi is equals to the flux linkage. What will be the total flux linkage? N into the phi, correct? N into phi, because in a single turn I have phi amount of flux, in n turns I will have n phi. Okay, divide by I, correct? Will be equals to what is phi? Flux is equals to mmf by the reluctance. So it will be n, mmf is ni divided by the reluctance s, and I is already there, so this will be n square by s. So this is another formula for inductance. another formula for self inductance. So this is also very very handy. Okay, this I think we have not discussed previously. Okay, so reluctance, again you can find out what is the reluctance. Reluctance is the like L mean path L by mu A. This we have already discussed previously. Okay, so these were few key points. So if I have a coil here, and if I know the length of this coil, mean circumference, and the area of the cross section of this coil, so my reluctance S will be equals to L upon mu A. This is what my reluctance is. This is what my reluctance is. Okay, so yeah, so these are the formulas. This we have already discussed. So like in one place, in one go, all the formulas whatever we discussed previously are written here. Okay, whatever formulas we have discussed are written over here. Okay, so now let's come to the mutual inductance. So self inductance we have already understood. What is mutual inductance? So mutual inductance is quite different. So mutual inductance is the inductance that opposes the thing. It also opposes the changing flux, but something else. Okay, we will discuss about that. So before understanding that, let's understand the mutual flux. Let's understand the mutual flux. So let's say I have two coils here. Okay, I have two coils, again the same current source. So again I know that if current is flowing in this coil, it will develop a magnetic field, and this magnetic field will flow something like this, something like this. What will happen is that some of the field lines will of course flow through this flux, will flow through this coil 1, and some of the field lines will flow through both the coil 1 and the coil 2, both the coil 1 and the coil 2, depending on how close this coil is placed. If this is placed very close, then whatever field lines will come out of this coil 1 will actually go through the coil 2 as well, if they are very close to each other. If they are very far to each other, then of course the density will reduce, right? The magnetic field lines will also reduce as we move further away from the coil 1. So the number of field lines linking both the coils will also reduce basically. Okay, so that is the mutual flux. What is the mutual flux? The flux which links both coils, the coil 1 and the coil 2. That is the mutual flux. Okay, which links both coils, coil 1 and coil 2. So before going into that, let's calculate the self inductance of both the coils. So the self inductance of both the coils L1, L1 L1 will be equals to what? L1 will be again the formula that we have derived. It is N1 whole square divided by S1. Okay, so this can be written as N1 whole square divided by L1, the whatever the mean core length, divided by mu into Ag1. Okay, mu1, and like it is same, right? The permeability will be almost same only. So but still let's write mu1 into Ag1, and your L2 will be just the same, just it will be converted from L1 to L2. Okay, this will be changed to L1 to L2. L2 L2 E2 mu2. Okay, and this will be S2. This will be my L2. Okay, I will just write here, this will be my L2. So my L2 I know self inductance, my L1 also I know self inductance. Now we have to find out the mutual inductance. So what will be the mutual inductance? So as I have already told you that the mutual inductance is the amount of flux that links both the coils. Okay, not only a single coil, it links both the coils. Okay, so what is the flux that is linking both the coils? So if I see like overall this particular coil, like the current source is only present here, right? The current source is only present here. So whatever the flux is getting generated is due to only this current source. So overall flux of the coil 1 will be phi 1, and it will be summation of two fluxes. Okay, there are two fluxes, one is phi 11, another one is phi 12. Okay, so it is phi 11 plus phi 12. Okay, so like it is going into two directions. So this 511 is the flux which only links the coil 1, and 512 is the flux which links both the coil 1 and coil 2. Okay, so there will be a induced EMF in the coil 2, correct? There will be a induced EMF in the coil 2 due to which flux? Due to the flux 512, because only this flux is actually linking the coil 2, the other flux is not linking, correct? So the induced EMF in the coil 1 will be equals to what? Induced EMF in the coil 1, V1 will be again the total amount of flux in this coil, the change rate of change of total amount of flux in this coil divided by the time. Okay, right? So it is N1 number of turns into d phi 1 by dt. That is what my V1 is, correct? That is the induced EMF in the coil 1, because total flux is 511 and 512. This total flux is actually going through this coil 1. What about the other one? Other one, my V2. V2 is N2 into, it is d phi 2 d phi 1 2 divided by dt, because the total flux is actually not linking here, right? Only this amount of flux is linking. Okay, so I can write this equals to, again I will use the same formula, right? If I use the same formula here and the previous case, so V1, right? V1 can be written N1 into d phi 1 divided by d I1. Okay, so into, of course, this is d I1 divided by dt. So overall I can write this whole thing as L. This whole thing is L, so this will be L1. This whole thing is L1, so this will be L1 di 1 by dt. Okay, and in the second case, so again I can rewrite this thing N2 into d phi 1 2 divided by d I2. Okay, so not I2, sorry, d I1. Why is it d I1? I will explain. Why is it d1? Because the change in the flux 512, right? Who has developed this flux 512? Who has developed this flux? This flux has been developed by current I1, right? There is no current I2 because this is open circuited. So this flux 512 actually has been developed by I1. So that's why there is, like, I'm measuring the change in flux 512 with respect to the current I1, right? And if the change is higher, then it will have more inductance, right? It will be more inductive. There will be more induced EMF into of course I have to satisfy the equation. This will be d I1 divided by dt. So basically what is happening is that this, right, this term, this whole term is the mutual coupling or mutual inductance. So this will be equals to my M2 into d I1 divided by dt. Basically what this signifies is that if the mutual inductance is higher, right, that means the more change there is in I1, the more induced EMF there will be in coil 2. Okay, if the mutual inductance is very high, that is there is good coupling between these two coils, that is higher number of flux lines is linking here with the coil 2, then if more number of flux lines are linking, so whenever there is change in I1, so there will be change in the flux, and that change will be exactly replicated here, correct? If as more, like most of the flux lines are linking. Okay, and if that change is replicated here, that means there is a huge change in flux here, and if there is a huge change in flux, then there will be induced EMF. Okay, so it is highly linked, highly coupled if mutual inductance is higher. So like same thing is written over here. Mutual inductance occurs when two inductors or coils are placed close to each other, allowing the magnetic flux generated by the current in one coil to link, like whatever flux we have generated in one coil to link with the other coil, thereby inducing a voltage in it. Okay, so basically how do I measure the effect? We measure the effect by measuring the induced EMF. Okay, this phenomenon is fundamental in transformers and other coupled inductors. So this already we have actually discussed, that if you remember, whenever we were discussing about transformers, there the flux lines of one of the coils was linking with the other coil. There I have not mentioned about mutual inductance because I don't want to confuse you at that point of time, but it was basically a core was there, and whatever flux was flowing in the first coil, the same flux was actually flowing in the second coil. Assumption was there was no leakage reactance. Okay, so like this is the very basic example of transformer. Okay, I hope you have understood what is mutual inductance. How do I calculate mutual inductance? The basic definition of mutual inductance. Okay, same thing is written over here. Consider two coils which if they are placed near each other. Now if I flip it, right, if I change it, now, if I apply a current in the second coil and measure the mutual inductance in the first coil, same thing, right? Same thing. What is the same thing? So the voltage induced EMF in the first coil will be V1 will be equals to, again it is N d phi 2 1 by dt. Why 2 1? Because again a flux phi 2 will be generated, and that phi 2 will be a combination of the this which the flux which only links with the coil 2 and the flux which links both with the coil 1 and coil 2. So it will be phi to 2 plus phi to 1. Okay, so this will be this is n1, right? N1. So again I can rewrite this. This will be n1 d phi 2 1 divided by d I 2, because the current is in the second coil now, into di2 divided by dt, and this whole thing is the mutual inductance of the coil 1 with respect to coil 2. So this will be M21, and in the first case this will be M12. Okay, this will be M12 basically, because the flux has been developed. Okay, sorry, the notations are wrong. This is the mutual inductance of coil 2 with respect to 1, because the current was there, and this will be mutual inductance of coil 1 with respect to 2. Okay, and what you will observe is there is a symmetricity. The M21 and M12 both will be same. Always they will be equal. Okay, so this will be equals to M, and this will be equals to N2, either N2 d phi 12 divided by dt, or equals to, oh sorry, no, not dt, sorry, d phi 1 divided by I1, or N1 into d phi 21 divided by di2. Okay, so these values will always be same, always be equal. Okay, I hope you have understood this point. So what is the value of the mutual inductance? So if I break this thing down, right, d phi 12 divided by d phi 2. Okay, if I break it down, so if I assume we are in linear region. So what do I mean by linear region? So by linear region I mean this, that I have this phi I curve, right? I have this phi I curve. Okay, so an assumption is I am not going into the saturation. So I am not going into the saturation. Okay, so I am lying in this region. So directly I can write my d phi 2 by di I2. This will be equals to phi 21 divided by di2 into n1. Okay, not di2, sorry, I2, because I am in the linear region, so I can directly write phi 21 divided by I2. I can directly write it. Okay, so what is this phi 21 divided by I2? Do you remember what is this phi 21 divided by I2? So we can actually have a constant here basically, right? What we can assume, instead of writing this, what we can assume is, already I have told you that my phi 1, let's take for the first case phi 1, if I just choose this circuit, right? If I just choose this circuit, okay, so if I just choose this circuit, my phi 1 equals to phi 1 1 plus phi 1 2, because there will be two fluxes. One flux will totally link the both coils, and and other flux will just link the first coil only due to this current I1. Okay, so I can assume that my phi 1 2, right, which is linking both of them, is some k times phi 1. Of course it will be a fraction where k will be between 0 to 1. Maximum value of k can be 1, because all of the flux that is coming out of this coil 1 is linking coil 2. If k is 0, that means none of the flux that is coming out of coil 1 is linking coil 2. Okay, that is the physical significance of k. Okay, this is also known as coefficient of mutual coupling, which we will come to. So I can replace this equation, right? This equation was there. This equation was there initially, correct? That is m21 is equals to n2 d phi 1 2 divided by d1 di1, right? m21 m21 equals to n2 into d phi 1 2 divided by di1, correct? I can replace d phi 1 2 as k into phi 1. So this will be n2 into d of di1 into k into phi 1. So this will be equals to, okay, just look. So k is a constant, right? It is like a just a constant number. So k can come outside. This will be k into n2 into d phi 1 divided by di1. And do you remember this expression? Do you remember this expression? So this expression is what basically? So this is basically flux phi 1 if I am in the linear region. So this will be k into n2 phi 1 divided by I1. Okay, and what is phi 1 divided by I1? Phi 1 is the like mmf upon the reluctance. mmf upon reluctance. So it will be k into n2. Do I have space here? Just hold on. Okay, so let me go to the next page basically. Let me delete this. So here, what is phi 1? Phi 1 is mmf upon reluctance of the coil 1, right? S1. So mmf is equals to n1 into I1, correct? Because this is the flux in the coil 1. Current in the coil 1, I will calculate, divided by S1. S1 you can write, basically S1 you can write anything, it does not matter. Like S1 and S2 assumption is they are both same. Okay, they are almost identical coils. I can write here S only. Okay, so this, right, ultimately my mutual inductance M21. Okay, M21, this will be equals to mmf, that is k into n1 n2 I1, and like there is a I1 in division and there is a I1 in numerator. Automatically it gets cancelled out. N1 into divided by S. Okay, so ultimately what you get is your mutual flux mutual inductance expression is this. Okay, this is the mutual inductance expression. Okay, what is k? K is known as the coefficient of coupling. So if you observe here, if the coils are placed really close to each other, Okay, these two coils are placed really close to each other. If these two coils are placed really close to each other, that means whatever flux, right, whatever flux that will come out, like whatever flux that will come out of this coil 1 will actually link to the coil 2. If I place the coils really further away, right, let's say currently the expression is something like this. If I place the coils really further away, so let's say my coil is here, okay, this is my I1, and like my coil 2 is here, okay, really further away, and this is open circuited only, this is N2, this is N1. Okay, so the flux lines that will be generated here, like very difficult to actually like link, right? If you remember that my magnetic flux density, it was mu naught Ni divided by R, correct? R was where R was the distance. So if radius increases, the magnetic flux density will reduce. Okay, something like this. So basically my magnetic flux density was inversely proportional to the distance R, right? For a simple coil. So magnetic flux density will keep on reducing if I move the coil to further away. And if I move the coil to further away, that means if magnetic flux density is reducing, that means the flux linkage phi 1 2 will also go down. That means what? What is phi 1 2? Phi 1 2 was equals to k into phi 1. So this will not change actually. Phi 1 will not change because phi 1 is what? MMF upon reluctance of the coil 1. So MMF is not changing because the current is not changing. So phi 1 is constant, but my phi 1 2 is reducing. So what has to change here? So of course k has to reduce. So that's why we say that like k will be lower as we move further away from the uh, coil 1, initial coil. So the k, the coefficient of coupling k is actually inversely proportional to distance between the coils. So if the distance increases, then the coefficient of coupling also will basically reduce. Okay, that is what will happen. So this is whatever we have discussed written over here. Mutual inductance occurs only when inductors are close to each other and influenced by a time varying field. Of course, time varying current, sorry, not field, time varying current needs to be there, right? If time varying current is not there, of course there will be no induced EMF. There will be no induced EMF. It enables energy transfer between circuits when, which is basis of the transformers. Inductors act like short circuit in DC, so mutual inductance is relevant only in AC or time varying systems. Mutual inductance is not relevant in DC. Okay, mutual inductance is not relevant in DC because there will be no induced EMF. Okay, why? Because there will be no induced EMF in DC. Okay, so we have a formula that your mutual inductance can never be more than the geometric mean of L1 L2. Okay, like that comes from this formula only. Okay, it can never be more than geometric mean. So we have another formula that will mutual inductance, because M12 and M21 will be same. Mutual inductance will be equals to K into under root L1 L2, where K is the coefficient of coupling basically. Simple as that. K is the coefficient of coupling. Okay, I hope you have understood. So K is the amount of flux, let's say, that is getting linked to 1 2 out of the overall flux, or it can be written as phi 2 1 divided by overall flux phi 2. Okay, whatever the amount of flux that is linking both the coils, that is the ratio of those two is the K. Okay, so K, if K is higher than 0.5, we say it is tightly coupled because the coils are placed nearer to each other. Coils are placed near to each other. And here the coils are placed further away to each other. Further away. Okay, So that was about it. So this, right, just to, yeah, sorry, just my recording got stopped for a second, that's why I had to re-record. So like you can see the example here. So these two coils, right, are actually away in the same core. The coils are away, and here, right, the coils are very near. So whatever flux this will generate, same flux will link here, but here the coils are very further away. So the flux lines, linkage of the flux lines will reduce. So definitely it will be loosely coupled, this will be tightly coupled. So few examples are there, like what are the tightly coupled transformers. So these easy guys can ignore this. Okay, now let's understand the mutual inductance in the, like, transformer, right, magnetically coupled circuit. Okay, so I know that if I have a voltage source here, this will generate a flux. Okay, how it will generate a flux? Because a time varying current will flow. Due to the time varying current, mmf will be generated. Due to the mmf, flux will be generated. Okay, as there is like reluctance and flux can flow through this core path, flux will be generated. So a time varying flux will be generated, correct? And if a time varying flux is generated and that is flowing in here as well, through this coil as well, linking through this coil, so what will happen? This will induce a EMF. Okay, and this will also induce EMF according to Faraday's law. Why? Because if a time varying flux is generated, automatically this coil will generate a induced EMF, and the same induced EMF this also will generate. Not the same actually, because the number of turns are different, so it will differ by number of turns. So if I have a time varying voltage source, then I get a induced EMF, time varying induced EMF according to the Faraday's law. So E1 will be equals to N1 into d phi 1 divided by dt. Okay, and your E2 will be equals to N2 d phi 2 divided by dt. Now the difference is that this phi 1 and phi 2 are same, right? Whatever flux is coming out of this, generating from this coil 1, same flux is linking, because it's a single uh, core only. So in case of transformer, what happens is phi 1 equals to phi 2. Whatever the flux that comes out of the phi 1, right, actually links with the secondary coil as well. Okay, so in this case the coefficient of coupling K is 1. So in case of transformer, the coefficient of coupling is 1, and that's why you see that my E1 over E2 is simply equals to your N1 over N2, because d phi 1 and d phi 2, these are same, so they will simply get cancelled. So it will be N1 over N2. Okay, E1 over E2 will be equals to N1 over N2. So this was about the mutual inductance. Now let's come to another topic, the most interesting topic, that is the dot convention. Okay, what is the dot convention? So dot convention, again I will discuss in transformer as well, don't worry. So here I will briefly discuss for the easy aspirants. So mutual inductance is always positive, but the induced mutual voltage can be positive or negative depending how the coils are actually wound in the core, how the coils are actually arranged. Depending on that, the the induced mutual voltage will be opposite in sign. Okay, it can be positive or negative. It really depends on the sense of the winding, how sense of the windings, how the windings are wounded. We will discuss that. So let's basically discuss what is dot convention. So we have already discussed, if I have a transformer core like this, okay, and if the windings are wound like this, these are my sense of winding. So initially let's assume that everything is AC source, right? So whenever I say this is plus, this is minus, actually, right, there is no physical significance, because it's a AC supply. So at certain instant this will be positive, at certain instant this will be positive. Okay, so but let's assume that we are at time t equals to 0 seconds or 0 plus seconds. Okay, and assume that initially this node is positive, this node is negative. So initially voltage is positive. So if voltage is positive, what will happen? If voltage is positive, a current will flow like this. Okay, so what will be the direction of current? Direction of the current will be somewhat like this, because this source is delivering some power, correct? If this source is delivering some power, because this is the load, so current will leave from the positive terminal. Okay, so the direction of the current is like this, and due to this direction of the current, we know there will be a induced EMF. If I just curl my fingers, right hand thumb, if I just curl it, I can observe that there is a induced EMF. Okay, so it is going in the top, so which is here as well. So flux is going in the top, and it is linking the second coil. Now I know that if some flux is there, right, according to Faraday's law, due to the current a flux will be generated, and due to that flux a EMF will be generated, correct, according to Faraday's law. I know that EMF generated in the coil 1 E1 will be N1 d phi 1 by dt, and EMF generated in the coil N2, I am talking about magnitude only right now, will be N2 will be equals to d phi 2 divided by dt. Okay, and we know that like this is the same transformer core, so whatever flux is coming out, same flux is linking, right? So basically whatever flux is coming out of this coil 1, same is linking, so phi 1 and phi 2 are same. So I can directly say the magnitude of E1 over the magnitude of E2 will be equals to N1 by N2. This we already know, this we have already discussed previously as well, right? N1 divided by N2. Now the interesting fact is, what are the signs of the induced EMF? What are the signs of the induced EMF? Now in this case, right, the sign of the induced EMF will be same, right? Why it will be same? If this is plus minus V1, this also will be plus minus E1. Why? Because like if I assume the winding resistance to be very low, the KVL has to satisfy. So if whatever voltage there is, same voltage there will be. So this sign is fixed. What about E2? What about V2? So sign can be like this, plus minus or plus minus. Which one will I choose? Which sign will I choose? Okay. So another person came, if you remember, in the Faraday's law, in the equation, there was a sign named, like sign was there, that my induced EMF V induced will be equals to minus N d phi by dt, correct? So this sign was there actually. Now that sign will come into action. I know there will be an induced EMF, okay, and due to that induced EMF there will be a current flow, correct? So now whenever you want to find the sign, right, don't worry, slowly it will feel like it is bit complex, but once I will come to the conclusion, everything will be simple, don't worry. Okay, whenever you have to find the sign, what you have to do is you have to actually connect a load. Without connecting a load, you will not be able to actually discuss about the sign. Okay, so let me connect a load, a resistor at the output. So if I connect a resistor at the output, what will happen? If I connect a resistor at the output, if I assume, let's assume a sign, let's assume this sign, okay, plus minus. So if I assume this sign, then I know if like in a resistor, if this is positive terminal, so resistor only can absorb the power, so current direction will be like this. So this will be the current direction, this, right? This is how the sense of winding is. This is my current direction. If this is my current direction I2, then I know that this will actually generate a flux also, right? This will generate a flux. So if I now curl my fingers along the current direction, I see that the flux generated by the coil 2 phi 2 is in the downward direction, which is actually in the same direction as the initial flux. Initial phi 1 flux, whatever flux was there, which is in the same direction. But is that, should it happen? Because Lenz has told us that the induced EMF will be such that it opposes its initial cause. So here, right, induced EMF will be such that it should oppose its initial cause. Okay, induced EMF will be such that it opposes its initial cause. So it is actually wrong, because we are actually supporting the initial cause. Initial cause was flux phi 1. Due to this phi 1, this phi 1 was changing. So as this phi 1 was changing, that's why there was an induced EMF, right? And the induced EMF will be such that it should oppose the change. So initially there was no flux. Like now the phi 1 initially, I will assume that flux is sinusoidal. So phi 1, this is my phi 1 graph. So it is increasing in the positive direction, right? This is my omega t. This is my phi 1. So flux is increasing in the positive direction initially. So if flux is increasing in the positive direction, that is in the downward direction, I should actually oppose it by making the flux, whatever the due to the induced EMF, in the opposite direction. So my polarity of induced EMF will be such that it should oppose the initial flux, not support it. It should oppose the initial flux, not support it. So actually this is wrong. This polarity is wrong. Whatever we have assumed is wrong. So what is the actual polarity? So the actual polarity, I will copy this thing. Okay, and the load will be still connected. Okay, this will not be, just hold on, this should not be there. This will be deleted, all this will be deleted. Okay, so now if I assume the other polarity, this polarity, don't worry, you don't have to do all this business, right? Every time if you have to find out the polarity, we'll discuss about that. So plus minus is there. Now the current direction will be like this, right? Current will always enter in the positive, like resistor. So current direction is like this. So it will be this, this and this. Okay, now if I, what is the initial flux? Initial flux, right, is in this direction, correct? Phi 1, increasing in the downward direction. And what is the flux due to this current? I2. So if I curl my fingers, it is in the top upward direction. It is in the top upward direction. So the induced, like flux generated due to the induced EMF phi 2 will be in the upward direction, which is in opposition. So I can write here that phi 2 and phi 1 are in phase opposition. Okay, phi 2 and phi 1 are in phase opposition. So that is the basic thing. That's it, right? That is the dot convention. You have got understood the dot convention. Okay, I will explain what do I mean by dot convention as well, don't worry. But that is the most important point, right? So if the flux here is increasing in the downward direction, then the induced EMF polarity will be this plus minus. So if this is plus minus, this also here this will be plus or minus. So now what we will do is, now the important fact is, we have assumed at t equal to 0, this was the plus minus, right? So with plus I see a dot polarity. Same thing I will do here. So if there is a dot with a plus, so I will also draw a dot with a plus here. Okay, that is the difference. If suppose there was a dot with a negative sign, okay, if the dot was here and if the dot was with a negative sign, then the same thing I would have done. I would have put a dot with a negative sign. Okay, that is the only point about dot polarity. And the negative generally they write as like a square kind of thing. Okay, just a notation, nothing else. Okay, don't worry, we will have a shortcut. We will have a shortcut for this, don't worry. But basic thing, I hope you have understood that what is the polarity, what is the like significance of the polarity. So polarity should always be such that it should oppose its initial cause. That is the most important part. Polarity should be such that it should oppose its initial cause. So if I have a induced EMF like this, and initially if this is dot and if the current is flowing like this, so there will be a flux phi which will go in the downward direction. So due to this flux phi, a EMF will be induced, and the polarity of the induced EMF will be such that it should oppose its initial cause. So that's why this will be plus at that instant whenever this is plus. So whenever this E1 is increasing in this direction, then E2 will also increase in this direction. Okay, that is the instantaneous polarity. So dot actually discusses about the instantaneous polarity, because of course it is an AC source, so the values keep on changing, polarities keep on changing. Okay, so if I have a dot here, I will have a dot here as well. Okay, that is the only significance thing that we have to understand. Okay, so what is the most important part? Most important part is the knowing the sense of winding. Sense of windings. How are winding this coils are wounded on the core? If you see, this coil is wounded like this, right? It is coming outside, then inside, then outside, then inside. But it is just opposite, right? It is just opposite. So if it is opposite, so initially if I go in this loop, right? If I, let's say I'm going in this loop. So initially this coil, the dot is in the second point of this coil, of this, sorry, dot is in the second wire of this coil, correct? If I go in this clockwise direction. So once I will come here, the sense of winding here is opposite to this, right? If you like, if you see, if you observe, the sense of winding is opposite. This is like wounded like this, and it is just the opposite, right? Wounded in the opposite order. So the dot will come first. Previously the dot come in the second position. Now the dot will come in the first position. I will do few examples. There will understand. Don't worry. I will do few examples. It will be automatically cleared. Okay. So let me just delete these pages. Like whatever I have told you, same thing is written over here. Okay. So basically the polarity of the induced EMF will be determined by the Lenz's law, because the induced EMF will oppose the cause, initial cause. So the primary coil creates a time varying flux in the core. The flux links both the primary and the secondary, and this now which induces the EMF in the secondary. This induced EMF in the secondary winding must generate a current that opposes the change in flux, initial change in flux, because of course inductor does not like change in flux. So if we assume that at a particular instant the applied voltage on the primary coil is increasing, the flux in the core overall is also increasing. Okay, so what they do is, this is repeated, sorry, this should not be here. This will be here. So there are two possibilities, right? So whatever I have discussed, that is first thing. If the secondary coil develops a voltage such that its induced current flows in the same direction of the initial flux, so the resultant flux will increase more. So if phi 1 is in this direction and the due to the induced EMF phi 2 also in the same direction, so the resultant flux in the core becomes phi 1 plus phi 2. That means it increases. But Lenz says that we don't want this change, right? We want to reduce the change. So we don't want to increase it, right? We want to actually reduce it, because previously the flux, only flux phi 1 was there. Now we are further increasing it, correct? Previously actually initially there was no flux, so further we are increasing it, right? We don't want it. So the induced EMF will be such that it generates a flux in the opposite direction of phi 1. Okay, that is what Lenz's law says, and that is what is written over here. Okay, same thing is written over here. Nothing special. Whatever I've discussed is written over here. Okay, so we will do few problems and there will understand. Okay, so because without problems you will not be able to understand. So if the dot is here, just pause the video and try it out by yourself. Where will I place the dots here in this particular windings? Where will I place the dots? Okay, and trust me, in your exam, much simpler question will be asked. Okay, much simpler question will be asked. So now let's start with the first one. So if the dot is here, okay, now you will do it a bit fast. Okay, first time I will do slow, then I will do fast. So if dot is here, what you can do is you can assume an initial instantaneous polarity. Okay, you can assume this as plus minus. So we assume this as plus minus V1. So due to that there will be an induced EMF, of course, because there will be a flux here. So the current direction will be such like this, and flux phi will flow here. So I have to generate a flux that opposes this cause. So what will be the current? What should be the current direction here? So currently the flux is in the downward direction. Okay, so my current direction should be something like this, so that my flux is in the upward direction. So current direction will be like this, right? Like this. If you curl your fingers, it should be like this. So this will be my current direction, and if this is my current direction, just connect a load, just connect a resistor. Okay, if I connect a resistor, so this is R, so this will be plus minus, right? So this is my actually polarity of induced EMF. That's it. But don't worry, you don't have to do all this. You don't have to do all this. Okay, why I will explain. So let's come to this one. Now without doing all this, right? So if I have a dot here, then again dot should be with the same polarity, right? So plus is here with the dot, so plus will be here with the dot as well. Okay, plus will be here with the dot as well, correct? Same thing. Now I will not do all those business, I will simply directly place the dots. So in this case, right, if I observe, the sense of winding is somewhat like this, right? It is going in the like anti-clockwise direction, correct? And here also it is going in the anti-clockwise direction. So both of them have both of them have different sense of winding, right? This is going in the, sorry, this is not going in the anti-clockwise direction, this is going in the clockwise direction, right? Yeah, this is going in the clockwise direction, not in the anti-clockwise. This is going in the clockwise direction, and this is going in the anti-clockwise direction. Okay, if you see, the sense of winding is different. If the sense of winding is different, so I will just go in a loop, just go in a circular loop. So if I go in a loop, first I observe in this coil, if I will encounter coil 1 and coil 2. Okay, so if I go in this loop, I first encounter dot in the coil 1, and in the second end of the wire it is empty. Okay, so same pattern I will follow if it follows the same, like if the coil 2 also follows the same sense of winding, then dot will be at the starting and other end will be open, I mean other end will not have any sign. But the sense of winding is actually different here, right? The sense of winding is different, so it will just be opposite. So in coil 1 I encountered dot first, so in coil 2, as the sense is opposite, sense of winding is opposite, that's why I will encounter the dot second. Okay, I will prove it to you as well, I will prove, everyone I will prove. Okay, so again in this case, so if I observe, the sense of winding is something like this, right? So if I observe that the sense of winding is like this, so this end of the wire, like dot is with the end of the wire where the wire I am able to see. For this coil 1, if I write this as C1, coil C1, C2, C3. So I observe dot is with the that portion of the wire that is in front of the transformer. Okay, here as well, if you see, dot is with that portion of the wire that is behind the transformer. So here also dot will be with that portion of the wire that is behind the transformer in the coil 2. So that's why this is the point why it is dot. So here as well, if you see, dot is with that portion of the wire that is in front of the transformer. So here also same thing will happen, dot will be that portion of the wire. So we'll just zoom this up, right? This will be magnified here. So here, which portion of the wire of the coil C2 is in front of the transformer? This portion. So dot will be here. Here, which portion of the wire coil C3 is in front of the transformer? Here. So dot will be here, C3. Okay, I will prove it to you. I will prove it to you. Here again same thing, right? Dot is in front of the transformer with the wire C1, coil C1. So same will follow for the other coil. So one of the polarities they will give you, and you have to find out the other polarities. So for coil C2, again dot should be in front of the wire, so it should be here. Here also dot should be in front of the wire. I will prove it to you. Let's prove it to you. Okay, so this will work only for those in which I have a single window transformer. Okay, don't worry, electrical guys, we will learn about multiple window transformers later on, and EC guys, you have to totally ignore this term, single window transformer. You don't have to worry about this. Okay, over the code. Now I will prove it. I will prove each one of them. Let's go step by step. So again, if this is dot, so I will assume my initial polarity. Okay, I will assume my initial polarity. This is plus, this is minus. This is my V1, so induced EMF will be E1, and due to that there will be a flux. So if this is plus, this is minus, so again current will flow something like this, right? Because this is the supply, so it will deliver the power, so current will flow something like this in this direction. So the flux direction will be what? Now it is in the anti-clockwise direction. Flux direction will be in the anti-clockwise direction, phi. Okay, so flux direction is in the anti-clockwise direction. So the here again, this is the flux direction in the top, right? So the induced EMF will be such, if I connect a load here, the induced EMF will be such that it should oppose the cause. So flux currently is in the top direction, so if the I have to oppose the cause, right? So I cannot place my fingers like this because it will add the flux. So I have to place my fingers something like this so that my resultant, like induced flux, is in the opposite direction. So the fingers are curled like this, so it will be like this, right? fingers are curled like this, so the current direction will be like this, so my flux will be in the opposite direction. So this is my direction of current, so this is my direction of current. So basically current is entering into this resistor terminal, so polarity will be like this. So this will be E2, and exactly this is the case, right? If you observe, that is what we have actually discussed. Dot is here, dot is with the positive terminal. Same concept you apply here, same concept you apply here, it will be followed. Okay, I can do this on and on. So I can make more examples. So if you want, I can make more examples. So let's say if I just change this, okay, and place the dot over here. If I place a dot over here, now I don't need to do all those, right? That was only for concept building. I can directly talk about the dot in the other coils. So if dot is here, that is with the wire that is inside the transformer core, like that is what I am not able to see. So here also dot will be with that portion of the wire that is inside. So dot will be here and dot will be here. That's it. And if I change the sense of winding, then also you will be able to do it. Okay. So that's how simple the dot polarity is. And remember, all these are instantaneous polarity, right? So here whenever we say dot with positive, dot with positive, all these are instantaneous polarity. These are not constant polarity because we are in AC. So dot convention actually helps us to identify dot convention helps us to identify the instantaneous polarity. That is, if this end of the wire is positive, then at that particular instant, which end of the wire will be positive in the other coil? Okay, with the other coil. Got it? Understood? Now, if let's say in the examiner, the polarities are drawn like this, V1 and V2, and dot is here also as well. So in this case, you will write your ratio V1 over V2 as N1 over N2. Okay. Now these are the polarities given by the examiner. Okay, these are the polarities given by the examiner. This is not given by you, because internally you know that if these two are dot, that means if at a particular instant, if this is positive, this also will be positive. But let's say if the examiner is very strict and like very adamant, right? So he gave you polarity something like this. But you know, if at a particular instant this is dot and this should be dot basically, and if a particular instant this is positive, this also should be positive. Induced EMF should also be positive, right? Plus minus C2. Okay. You know this is how my induced EMF sign will be. If at a particular instant, if this is positive, then this dot terminal will be positive. But the examiner has given you polarity something like this. Then how will you solve? Then how will you write this equation ratio? So listen to me very carefully here. Okay. So there will be an induced EMF here plus minus C1 because this is just in parallel with each other. So those will be same. So if I write a KVL in this first loop, I can directly see that my V1 is equals to E1 basically. There is no winding resistance. So V1 equals to E1. Okay. And I know another transformer relation, that I know induced EMF E1 will be what? N1 d phi by dt, and induced EMF E2 will be N2 d phi to phi by dt. And the sign already I have taken here, right? Sign is already taken care of. Here using the dot polarity. Now I will simply write the ratio. Ratio is E1 over E2 equals to N1 over N2. Okay. So this is the actual ratio. This is not the actual ratio actually. This is the actual ratio, the induced EMF always. Now what I am asking you, what is the ratio of V1 over V2? You will say, sir, it will be N1 over N2. No, it will not be N1 over N2. We will apply a KVL in the secondary loop as well. Correct? If I apply KVL in the secondary loop, it is minus E2 minus V2 equals to 0. So according to the polarities given by me, by the examiner, V2 is actually equals to minus E2. Okay? Or E2 is actually minus V2. So I will replace in this equation E1. E1 is V1. So I will replace here E1 is V1. Okay, let me take another page. E1 is V1 and E2 is minus of V2 is equals to N1 over N2. Okay, so here, right, my V1 over V1 over V2 will be equals to minus of N1 over N2. That is the most important point, and trust me, one day they will frame a MSQ here and only you will be able to solve it. Only you will be able to solve it, no one else will be able to solve it. Trust me. Okay, so this, no one will teach you these kind of things, no one will teach you. Okay, so if you are enjoying the concept, finally, if the dot polarity is also cleared, everything is cleared, make sure to hit the like button and make sure to comment down below. Okay, make sure to comment down below whatever you feel about this concept. Okay, if you have understood the dot polarity. Okay, so that is the most important point here. That is the most important, this is the most important like page. Okay, why will there be a negative sign? Why will there be a negative sign? Everything I have described you. Okay, using the small details. So same thing, like same convention you can follow here as well, that if this is positive, this also will be positive basically, because there is a dot. So here there will be no sign change. Here v1 by v2 will be equals to I1 will be equals to n1 by n2, as well as if you remember the current transformation rule, this electrical guys will learn, don't worry, EC guys, don't worry, this will be equals to I2 over I1. Okay, here things will be a bit opposite. Here things will be a bit opposite. Okay, so here, right, if the direction of the current is also given by the examiner, then also things will change. Okay, because if you see here, my derived direction of the current, if you see in this first case, my derived direction of the current is here. So how do I find out the derived direction of the current? Using dot polarity. So this dot polarity is absolutely correct, because here plus is with dot, plus is with dot. So if I place a resistor here, okay, so if this is plus, this is minus, then the current direction will be somewhat like this. So whatever the current direction, this current direction will be given to you by the examiner, and my reference I2 reference current direction, that is the actual current direction at a particular instant, are same. So I2 reference or I2 induced equals to I2 only. Okay, I2 reference is equals to I2 only. Okay, and my I1 is anyways here in the reference direction, there is no problem. So I1 is in the reference direction, so I2 by I1 will be absolutely correct, there is no problem, because basically what happens, this I2 reference, actually the relationship is this I2 reference by I1 reference is equals to N1 divided by N2. Okay, but here it will be opposite, because whatever direction they have given me of the current, right, whatever direction they have given me of the current, that is actually opposite of my reference, because plus is here and this is with the dot. So if I connect a resistor here, so my current direction will be in this direction, I2 reference, but the examiner has given me in this direction. So I2 actually is equals to minus of I2 reference. So just what will be changed, same thing will be changed, just a negative sign will be there. So I will replace my I2 reference with minus of I2 and I1 reference with plus of I1. So it will be I2 divided by I1 now will become minus of N1 divided by N2. Okay, electrical guys can relate this current transformation. EC guys, I have not derived this expression. Okay, not that important. Okay, but basic rule you know, right, the ratio of currents and voltages for a transformer. Okay, so that was about it, that was about the dot convention, that was about the polarity. Now let's discuss about the mutual flux. So let's discuss about mutual inductance. So in case of mutual inductance, previously what we were discussing is that my resistance was my load was not connected, okay, but now a load is connected, things will be a bit different now. So this we already know, that if I have a current source here, and if there is a current flowing through this coil, so which will generate a flux, and this is a time varying current source. Okay, so my flux phi1 also will be time varying, and it will be a combination, phi1 of t will be a combination of two fluxes, right? One of the flux that will only link with the coil 1 initial coil, and the other component of the flux will link with both the coil 1 and coil 2. Okay, both the coil 1 and coil 2. Okay, 5 on 2. So we know now as the load is connected, right? So there is a time varying flux in the coil L2. So if there is a time varying flux in the coil L2, there will be induced EMF, and we have already calculated the value of the induced EMF. The value of the induced EMF is M d I1 divided by dt. This we had previously calculated, right? We had previously calculated this. Now something interesting will happen. There will be induced EMF, that is correct. But what is the direction of the induced EMF? What is the direction of the induced EMF? So the direction of the induced EMF will be such that it will oppose its initial cause. Direction of the induced EMF will be such that it will oppose its initial cause. Okay. So the important point is there will, like this induced EMF is there. Okay, and a current is flowing. I2 current will flow here. Let's assume any current, right? Let's assume any random current. I2 current will flow because the load is connected. Correct? Because the load is connected. Remember, this voltage was due to the current I1, that is due to the flux 512, that was linking both of this. Correct? Now as a current flows, and due to this flow of current, this current is time varying. Due to that, this coil 2 will generate its own EMF. What did I say? That initially there was a current I1. This was time varying, due to which there were two components of flux. Okay, one 511 which was only linking with the coil 1, and another one was 512 which was linking both the coil 1 and coil 2. As this 512 was linking coil 2 as well, so some kind of flux is flowing. According to Faraday's law, there will be a induced EMF. Okay, according to Faraday's law, there will be a induced EMF. So that is the induced EMF. This is the induced EMF. Okay, now as soon as there is a EMF, okay, I am not talking about the sign right now. I am not talking about the sign right now. Okay, ignore the sign. As soon as there is a induced EMF, this is the magnitude. I am only talking about the magnitude. So this is the creator, right? I1 is the creator. Due to I1 only, this EMF was created, generated. This V2 EMF initially was created, right? As soon as this current flows, I2, because there is a load, current will flow. Because there is an induced EMF, current will flow. As soon as the current flows, now current is flowing through the coil 2, and this current is time varying. If this current is time varying and it is flowing to coil 2, I know there will be another induced EMF, L2 di2 by dt. Okay, there will be another induced EMF, L2 di2 by dt. This will be there. Okay, due to what? Due to the current flowing, current being time varying, and if there is a time varying current, then of course that will develop a flux. If there is a time varying current, that will develop a flux. Okay, so what we can say is this, right, again is according to Faraday's law. Now what did I say is, what will be the sign here? Will it be plus or will it be minus? Remember that this EMF was generated due to this current I2. And who generated this current I2? Due to this induced EMF, M di1 by dt. So this is the creator and this is the sun. Okay, and what Lenz has told us? Lenz has told us that whoever is the creator, right, we will try to oppose that. We will try to oppose the creator. The creator was this. Initially there was no current flow, right? There was no current. But suddenly due to this induced EMF, there is current. So I will try to oppose this. How will I oppose? I will oppose by opposing this initial creator. So if the initial voltage is M di1 by d2 initially in the secondary coil, I will try to oppose this. So I will subtract this. I will not add. I will subtract. I will not add. Okay. So overall the voltage induced EMF in the secondary coil will be di1 dt minus L2 di2 by dt. Okay, that is the important fact here. I'm not talking about the sign of the V2, just talking about the whole magnitude. I will subtract. What? And one more thing, one more important point is, you might have a question: can this magnitude be negative because we are subtracting something? This can never be negative because this is the creator, right? M di1 by d2 is the creator. So let's say if I have 100 rupees, and if I give you 40 rupees, can I like then how much rupees I will have? 60 rupees, right? If let's say instead of giving you 40 rupees, I want to give you 140 rupees, can I give you 140 rupees? I don't have 100, I don't have 140 rupees, right? I have only 100 rupees. Same thing, this voltage V2 was initially induced due to this creator M di1 by d2. Now another voltage will be induced due to the self inductance. This was due to the mutual inductance. This is due to the self inductance. So this is due to the self inductance due to the time varying current, and this is due to the mutual inductance. Okay. So self inductance and mutual inductance are there. Of course, I cannot go above my creator, right? I cannot go more than my creator. Okay, I cannot go more than my creator. So that's why the magnitude of the induced EMF will be like this. Now another important fact is that as soon as there is a current I2, of course if there is a current I2, this I2 current will in turn generate a flux phi 2. So if it generates a flux phi 2, then phi 2 will again be a combination of phi 22 plus phi 21. So this phi 22 will only be present in this coil, and phi 21 will link both the coils. So actually what will happen is, in the coil 1, the EMF also will change because the flux linkage has changed. So initially what was my induced EMF? Induced EMF E1 was equals to L1 di1 magnitude di1 divided by dt. So this also I should write E2 only, not V2. Okay, because induced generally we write in terms of E. That is the reason. So here my induced EMF is E1, that is L1 di1 by dt. Okay, so now the flux has changed. Why? Because I have a phi 21 flux, and I know this, I have already taught in this lecture only, that if I have a flux phi 21, then I will have another induced EMF, that is mutual induced EMF, that is dm into di2 divided by dt. Okay, this is due to the flux phi 21. This is due to the flux phi 21. Okay, now again the same thing, will this be plus or will this be minus? Again, right, this is the creator, because the current initially was time varying, and due to that it generated a induced EMF L1 di1 by d2, because the current was the supplier, current was the creator, right? So that's why this was there. So now of course whatever it will induce, whatever EMF it will induce, again it will oppose. So I will choose the negative sign. I am not discussing about the sign yet. Okay, overall sign of E1, I am not discussing about that. I am just discussing about the magnitude. Okay, again this is the creator and this is the sun, right? So sun can never go above the creator, and sun will always try to oppose the creator. So just like you and your father or mother. Okay, so your father says like you want a gaming laptop, and your father says no, we will not give you a gaming laptop. But you say, Papa, please de do, please, chahiye. Like you are opposing your father, right? Whatever your father say, you will do the opposite, right? Same thing is happening. Same thing is happening over here. Whoever is the creator, I will oppose it. So I will not add, I will oppose. So overall my value will be L1 di1 divided by dt minus m di2 divided by dt. Now this is the actual sign notation. So magnitude of E1 is this one. The magnitude of E2 induced EMF is m di1 divided by d2 plus L2, so not plus, minus L2 di2 divided by dt. Okay, so all this is there. Now you don't have to worry about this. So there is a very simple notation and we will learn that. Okay, so just I wanted to explain you the basics. Now we will exactly learn what will happen basically in circuit analysis. So sir, for circuit analysis, all this circus is not required. All this circus is absolutely not required. So we will just follow one rule. What rule we will follow? So initially there will be like circuit will be given and dots will be given. Now I hope you understood the physical interpretation of the dots. What is the physical interpretation of the dots? So these dots actually represent the sense of the winding in the actual core that we are not able to represent, because every time drawing the wires, right, will be very hectic and difficult. So to escape that drawing, what we did, actually uh, we actually described a dot notation to explain. So dot convention is used to explain the sense of winding. Explain the sense of winding in core. Okay, so just follow me right now, just follow me. All aspirants, please drop your pen or whatever you're doing, listen to me. Okay, this is the most important part. Okay, from here only questions will come. Okay, so if in the figure A the current for the both the coils it is entering into the dot, then whatever EMF will be generated, both will be additive in nature. What did I say? If the current is entering in both the dots of the coil, whatever EMF will be generated, that will be additive in nature. So if this point is VA and this point is VB, then overall my VA over VAB, right, VAB will be the, of course, some current I is flowing, so it will develop a self induced EMF due to the self inductance, that will be L di by dt, L1 di by dt. Okay, and same current I is flowing through the coil 2 as well, so that will develop a voltage L2 di by dt. Okay, now what about the mutual inductance? Because in both the terms, if you see, mutual inductance is there, here as well it is there, and here as well it is there. Okay, what will happen to the mutual inductance? Here as well it is there, here as well it is there. So to the mutual inductance, what will happen is that if, as I said, if both coils, if in both coils current enters into positive dot, then the mutual inductance will be additive in nature. So the voltage induced EMF due to the mutual inductance will be additive in nature. Okay, this is the conclusion. And if in the both the coils, let's say here in this case, if you see in one of the coil the current is entering dot, and in the other coil current is leaving the dot. So here current enters the dot, and here current leaves the dot. Okay, so in this kind of cases, my VAB, okay, will be equals to, the self inductance will be anyways additive in nature, because my assumption is the coils are acting as a load, right? Coils will obviously act as a load. So self inductance will be always with plus sign, plus L1 di by dt plus L2 di by dt. Okay, the mutual inductance will be mutual inductance will oppose. Why will it oppose? Why will mutual inductance will oppose? Mutual inductance will oppose because the sense of winding are actually different. That is the actual reason. That already we have discussed that, right? Already we have discussed that. That's why I'm not explaining. And how this 2m term comes, like from here, if you see that this here also I have m, here also I have m, and I1 is equals to I2. So just to give you a feel, I have explained this here, right? Just to give you a feel, that's it. So ultimate conclusion is this one. Just to give you a feel, I have explained you. Ultimate whatever conclusion, we have to remember this one. Okay. So got it? Understood? If in the both the terminals, like if in the both coils, current enters the dot, the polarity, the voltage will be like this. Everything will be added. And if the current leaves the dot, then the polarity will be like this. And what will be the overall inductance? If I just tell you what will be the overall inductance of this coil. So in this case, the overall inductance of this coil will be L1 plus L2 plus 2M. Why it will be plus 2M? Because like if I write this equation down, right? So this equation is equals to what? This dit by dt will be taken as common. So I can write that this VAV can also be written as the L equivalent, whatever equivalent inductance I'm observing from this AB point into the current. Current is di by dt, right? That is equals to this whole thing, right? This whole thing. So here it is L1 plus L2 plus 2M into di divided by dt. Okay, so di divided by dt cancels out. So ultimately we have L equivalent equals to L1 plus L2 plus 2M. Okay, that is what my L equivalent is equals to. Now same thing, right? Same thing if I apply here. So what will happen? Just L1 plus L2 will be there, minus 2M will be there. That's why here we have minus 2M. Okay. Okay. So these are the key points. So just you have to remember the conclusion. Just for the fields, I have explained you this thing. Okay, just for the field. So conclusion you have to remember, and these are the key takeaways. So why is dot convention used? Dot convention is used to like simplify the polarities in coupled coils if two coils are coupled and how they are magnetically linked. Okay, so now we will do few questions. So this is a question basically, and we have to find out the phasor currents I1 and I2 for the following circuit. Okay, if you observe, whenever you are solving any mutual coupling question, right, and if the core diagram or sense of wiring is not given, just don't have to do all this circus. You don't have to do all this circus, right? Whatever I have explained to you, simply just solve the circuit. Simply just solve the circuit. So this is one rule that I have told you. Just remember this rule, and that's it. If so, I will write here in the conclusion part, if only circuit diagram is given, simply follow this rule. Okay, this is the main rule. Let me name this rule as rule 2. Okay, simply follow rule number 2. Simply follow rule 2. Okay, rule 2 is whatever we discussed for circuit analysis point of view. And if the sense of wires are given, right, if the transformer diagram is given, all these things are given, core diagram, how the wires are wounded on the core, all these things are given, then you follow this rule 1, whatever we have discussed regarding here, right? Then we follow this rule 1. Okay, whatever we had discussed here. So let me write this as rule. So like it is a quite a complex topic, because if you have studied for somewhere else, you will feel that still I am having doubt. That's why I wanted to clear every single thing here. So this is the rule 1. Okay, so then you go by the conventional method, and that was the simple circuit diagram method. Okay, so if sense wire is given, then follow rule number 1. Okay, simply you follow rule number 1. That's it. So in this case, we will follow rule number 2. What does rule number 2 says? Rule number 2 says that if current is entering here in this dot and current is leaving this dot, that means they are in opposition. So the mutual inductance M will oppose, N will oppose its creator, N will oppose its creator. That's it. That is what it means. So basically, I will write the KVLs and from there we will understand. So remember this, right? This technique, whatever I have told you, this is actually very important technique. Okay, this is actually very important technique. So here, what will happen is in the first KVL, this inductor are also as a load only. This inductor will act as a load only. Okay, inductor will act as a load. So if current is entering here, so that means that voltage will be somewhat like this, plus minus. Okay, and if current is flowing like this, the voltage of the self inductance will be like this, plus minus. Voltage of the self inductance will be like this, plus minus. Okay, and the mutual inductance will oppose the self inductance. That is the only key point that you have to remember. So now let us write the KVL in the loop 1. If I write the KVL in the loop 1, it is minus 12 angle 0 plus into minus J4 into I1 plus into J5 into I1, because again it will act as a load only. Now what will be the mutual inductance? So mutual inductance is J3 into what? I2, right? I2, because like this is my self inductance. So self inductance. So with self inductance, the drop will be due to the self current, right? I1. Okay, and this is the creator basically. And again, this is the mutual inductance. So the drop will be due to the current in the other branch, that is I2. This is the mutual inductance. And what will be the sign? The sign will be such that it will oppose its initial cause. Initially, it is plus sign, so it will oppose its initial cause. That's why there will be a negative sign here. Minus this is equals to 0. Okay. Now let's discuss about KVL 2. Okay, I can simplify this further. If I simplify this further, this will be I1 J into I1 will be equals to 12 plus J3 I2 J3 into I2. So this is what my I1 is equals to. This is what my I1 is equals to. Okay. So let me just delete this. Now let's apply the KVL in the loop 2. If I apply the KVL in the loop 2, this is something else. Okay, let me just delete this thing. Something else. Okay. So if I apply the KVL in the loop 2, again this will be like there is a drop here. So this is plus J6 into I2. So again this is due to the self inductance, right? I know mutual inductance will oppose. So initially if this is plus, then I will have a mutual inductance which will oppose the sign, minus into the mutual inductance value, that is J3 into the current in the other coil, that is I1. Then the drop in this resistor, it will be simply plus minus here, right? It will be plus 12 into I2 equals to 0. So from here I can directly write my I1 is equals to, so my I1 is directly equals to I2 into 12 plus J6 divided by J3. So this will be I2 into 2 minus J4. Okay, so I1 is this value, and I can simply replace this I1 here, right? Simply replace this I1 here. So this will simply become this is my equation 1. Let's assume this as equation 1, and let's assume this as equation 2. Okay, so my like putting the value of I1 in the equation 1, so this will be J into 2 minus J4 into I2, that will be equals to 3 if I take common, 4 plus J, Okay, something I've done wrong. This is I2. Okay, no. So I cannot 3 plus j into I2. I cannot simply take j common, right? This will be 12 plus j3 I2. Okay. So now what I'll do, I will just club the I2 together. So this j2 will go in this side, and this will be plus 4 I2 and minus. So this will be, okay, sorry, this will be plus 4 minus j3 will be equals to 12 minus j2. Okay, 12 minus j2. Now I will just simply write down the values here. Okay, so this is j2. Okay, no, this is wrong, right? Sorry, what am I doing? What am I doing? So this is j2 into I2 plus 4 I2 equals to 12. Okay, and plus j3 I2. Okay, so this will become I2 4 minus j. Okay, 4 minus j equals to 12. So from here my I2 value will be 12 divided by 4 minus j. So this value will be equals to, if I calculate this value will be 4 square plus 1 whole under root equals to 4.123. Like the magnitude I am calculating into 12, this will be basically 12 2.91 angle. What will the angle will be 1 divided by 4 tan inverse. So this will be plus 14.036 degrees, plus 14.036 degree. This will be the value of I2. What will be the value of I1? So the value of I1 will be this, right? 2 minus j4 into I2. So that is 2.91 into 14.036 degree. Okay, so this will be 4 divided by 2. So like I'm just calculating the angle will be minus of 63.44 degree. Okay, and what will be the magnitude? So magnitude will be 20 under root, right? So it will be 4.472 into 36 degrees. Okay, so this will be into 2.91 and okay, 13.014, and angle will be 63.44 minus 14.036. This will be for minus 49.4 degrees. Okay, this will be the answer for I1 and I2. So these are the phasor currents, and like I hope you have understood this point. Like that's why this concept was very important, the phase opposition, right? So like if you see the solutions, right, many teachers, educators, what they will do, just they will replace this inductor with a like equivalent voltage source kind of thing. Okay, I don't want you to go to that. Okay, I want you to understand conceptually what is happening in the circuit. Okay, I don't want you to go to the dependent source. Okay, so the next few questions I will give you as homework. So these are the next few questions. You can take a screenshot, and in the next lecture we will solve all these questions. Okay, so like few topics are also left, like energy in coupled circuit. This also we will do, and if you know already, you can solve these questions. Else otherwise we will, like, you just take this as homework, and in the next lecture we will solve the questions, and of course we will discuss about the energy in coupled circuits that is also left. Okay, so thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the lecture 4 of this magnetically of this chapter 0 of magnetic circuits and basics of electrical machines. So today we will discuss about energy of coupled circuits and we will solve few questions. So previous lecture I gave you one homework. That question actually is not supposed to be in this lecture. That question was supposed to be in the transformer. By mistake I had put that question. That was a mistake on my behalf. That is not for EC guys. That is only for EE. After I will teach you transformer. Okay. So yeah, that was my bad. So today we will first of all discuss a bit about coefficient of coupling, because this coefficient of coupling actually came on EC branch. A question came, right? So this we have already discussed that coefficient of coupling is the ratio of the mutual flux, whatever the flux linked, divided by the total flux. Theoretically, K can never be greater than 1. It can either be between 0 to 1. If it is 1, then it is perfectly coupled. That means it is tightly coupled. If it is equal to 0, it is loosely coupled, right? This we already know. This we have discussed previously, right? So the formula of K will come out to be, K will be equals to K will be equals to M divided by L1 L2. Okay, M divided by L1 into L2. So this is the value of K, and very basic question came in GATE EC 2014 that in the magnetically coupled circuit zone, 50%, 56% of the total flux emanating that from the one of the coil links the other coil. So if the if the flux phi leaves from this coil, first coil 1 C1, then only 56%, that is 0.656 into 5, will link the coil 2. Okay, they are asking me the value of mutual inductance. Very simple, right? Very simple, because I know what is this ratio. The mutual flux, the flux that links both the coils, mutual flux divided by the total flux. Okay, total flux. Okay, so mutual flux is basically the flux which links, that is only 0.56 into 5 links, and total flux is basically 5. So K, your coefficient of coupling, will be 0.56, and I know this formula that my mutual inductance will be equals to K into under root L1 L2, geometric mean of the self inductance. So K is 0.56, L1 L2, L1 is 4, L2 is 5. Okay, so this, if I calculate 4 into 5 whole under root into 0.56, so this comes out roughly to be equals to 0.5 Henry. So 2.5 Henry. So 2.5 Henry will be the answer for this question. Very simple question, came in GATE EC. Okay, so this type of question do come in EC, and don't worry, for EC aspirants easier questions will only come in magnetic coupling. Easier questions will come, so you don't have to take any stress over the difficult concepts. Only this kind of baby questions will come. Okay, now let's discuss about the energy in the magnetically coupled circuit. So one question also came in energy as well. I guess this was from the W branch. Okay, one question came in energy as well. So basic thing is same concept. Okay, the energy stored in coil 1 will be half half L1 I1 whole square due to the self inductance, and energy stored in coil 2 will be half L2 I2 square due to the self inductance. Okay, now if there is current as well, then the difference will be that depending on the current directions. So here I observe both the currents are entering into the dot, so the energy will be additive in nature. So in the coil 2, the mutual energy will be additive in nature because both the currents are entering into the dot. So that's why there is a plus M into I1 I2. So the energy, this is the mutual energy basically. This formula you have to remember. Of course, like I will not derive because derivation is not important. Okay, so mutual energy. So this will be the mutual energy, and in the coil, in the overall coil, right? So if I have applied a voltage here and some current flows here, so this energy stored in the coil is half L1 I1 whole square. Okay, energy stored in coil L1 is half L1 I1 whole square. Now due to this current I1, a flux gets generated that links with this L2, and here what happens, another current is generated. Okay, so due to that current, again the energy stored in the coil L2 will be half L2 into I2 whole square, and there will be a mutual energy between these two coils. The value is M into I1 I2. The sign, will it be positive or negative, depends on whether both the currents enter the coil or one of the enter the dot, or one of the current leaves the dot and the other enters the dot. It depends on that particular notation. Okay, so that is the only thing. So overall mutual overall energy of the whole system, right? Energy of the whole system will be half L1 I1 whole square plus half L2 I2 whole square plus M into I1 I2, where this can be positive or negative depending if positive if both currents entered or leave the dotted terminals, negative if one of the current enters and the other leaves the dotted terminal, and vice versa, converse. Okay, so let's solve a basic question from this, and basic questions will only come from this topic. Very basic questions will come. Okay, so let's consider this circuit in the figure. We have to determine the coupling coefficient first. So how do I determine the coupling coefficient? The mutual inductance is given 2.5 Henry, and the both the inductance are given, right? So coupling coefficient K will be equals to what? K will be, for the first case, K will be simply uh, M divided by under root L1 by L2. Okay, so 2.5 divided by under root 5 into 4. Okay, so this value will be 2.5, like this is 0.56 that whatever we have calculated in the previous question, the same coupling coefficient value we are getting. So 20 under root, yeah, 0.56. So I think gate also maybe copies from standard textbook. So 0.56 is the answer. Okay, coupling coefficient is 0.56. Now what we have to find out, we have to calculate the energy stored in the coupled inductors at time t equals to 1 second. Okay, at time t equals to 1 second, we have to find out the energy stored in the coupled circuit. So how do I find out this value? How do I find out this value? So here what we need to do is we have to just write down the current expression, and from the current, like what we have to do is, first of all we have to find out the current I1 of t, I2 of t, and put the value of I1 and I2 of t at t equals to 1 second. So what is the energy? Energy stored in the inductors in the coupled circuits, E of t will be half I1 of t whole square into half L1 plus half L2 into I2 of t whole square into t plus now let's see like what are the directions of current. So we have not actually they have not given they have not given us any direction of current. So what we can do, we can assume the direction of current. So let's assume like mesh currents, right? Okay, let me assume this as current I1 and this is current I2. Okay, so in this case as well the current enters the dot, in this case as well the current enters the dot only, right? So as both of the sides are entering the dot, both of the currents are entering the dot, so this will be M I1 I2. Okay, so this value will be M I1 I2. So and we have to put like this is t only, a function of t only, so we have to put the value of t equals to 1 here. Okay, this will be a lengthy question, just bear with me. So we have to find out I1 I2. Okay, so this is a like AC circuit, so I will convert this into AC equivalent, right? Because like the frequency of the voltage is known, so I will convert this into my AC equivalent circuit. So my AC equivalent circuit will be somewhat like this. V, okay, and V is what I will assume this as my RMS. What is RMS? RMS is 60 by root 2. So this, right, I will write here, or you can write peak as well, that is no problem. Let's write peak only. So 60, and my like reference, what is my reference? Reference is 1 cos of 40. This is my reference. So with respect to reference, I am already leading by 30 degrees, and this is 60, like amplitude is 60. And this circuit will be what? This circuit is just a resistor, it will be independent of the frequency. This will be 10 ohms only. What about this one? So this is 5 Henry, right? So what is the inductive reactance? Inductive reactance will be plus J 5 Henry into the omega. Omega is 4. So it will be plus J 20 ohms. That will be the inductive reactance. Okay. And again I will have a circuit here. This will be like this. What will be the reactance here? So it is 1 by j omega c. So omega is 4. So it will be 1 by 4 into 1 by 16. So 1 by 1 by 4. So this will actually be minus of j4. That is the capacitive reactance. And what? How much reactance will this coil 2 will provide? It will provide plus 4 into 4, that is plus j16. And of course I have mutual inductance as well, that will provide j into m. So j into m, omega m. So omega is 4 and this is 2.5. So the mutual inductance basically will be j10 ohms, and the dot is here, the dot is here, and these are my directions of current. This is my direction of I1, this is my direction of I2. So I1 and I2. Okay, so this will be basically, this will be minus of 60 angle 30 plus I1 into 10 plus j20 into I1, and as both are like entering the dot only, so the voltage induced due to the mutual inductance will be in the same sign as the self inductance. Okay, so both the signs will be same. This will be plus j10 into I2 basically will be equals to 0. So from here I can directly write my I1 equals to 10 plus j20 plus 10 j I2 equals to 60 angle 30. Okay, so this is my first equation basically. Let's go and like this is the KVL loop 1. Let's try and solve the KVL loop 2. Okay, so KVL loop 2, this, right, again the assumption is this is acting as a load, so this will be plus j16 into I2, and again the sign of the mutual inductance drop will be same. So this will be plus j10 into I1 and minus, like again this will be acting as a load only, plus into the capacitive reactance into the current I2 equal to 0. Okay, so from here I can directly write what is my I2 equals to. So my I2 12, so this will be j12 I2 will be equals to minus j10 I1. Okay, so my I1 actually is equals to minus of 1.2 I2. Okay, so that is what my I1 is equals to. So I will replace it, I will replace in the previous equation here. Okay, so this is equation 1. and this is equation 2. So if I replace this thing, so from here my I1, so my I1 is minus 0.1 I2, so this will be minus 1.2 I2 10 plus 20J plus J 10 I2 will be equals to 60 angle 30. Okay, so from here I can directly write this is minus 12 I2 minus 24 plus J10 yeah, plus J10 I2 equals to 60 angle 30. From here I will be able to find out the value of I2. So I2, if I take common, this will be negative sign will come in common, so negative sign anyways I can take it outside. This will be 12 and minus J14, sorry, plus J14 equals to 60 minus 60 divided by 30. Okay, negative sign will be there because I've just taken the negative sign in common. Okay, so my I2 is actually equals to, if I calculate my I2, this will be 60, so 12 square plus 14 square whole under root, so 18.439, and if I divide this will come out to be my some negative sign is there, so I can add or subtract 180. It totally depends on what you want to do. So this value is, just hold on, this value will be 60 angle, this will be 210, just I have added 180 degrees inside, taken the negative sign. This will be 3.254, and what is the angle I want to calculate? 14 divided by 12 tan inverse, so this angle will be 49.4 degrees. Okay, so this value will come out to be 210 minus 49.4 degrees, so this comes out to be 160 degrees, 160.6 degrees, and this is 60 divided by 3.254, 18 point some value, right? No, this is not okay, this is wrong, right? This is wrong actually. This was supposed to be 12 square plus 14 square whole under root, 18.44. So if I divide this by 60, this will come out to be 3.254 amperes. Okay, okay, 3.254 amperes. This will be the current I2. What about the current I1? So I1 is basically minus of 1.2 into I2, so it will be minus of 1.2 into I2. So if I multiply minus of 1.2, so this, right, negative sign is there, so ultimately I can subtract 180 with the angle, so this will come out to be 3 point, I2 is minus 1.2 into I1 is minus 1.2 into I2, so it will be 3.9 angle of minus of 19.4 degrees. Okay, this will be the value of I1. Now let's bring it back to the time domain expression, right? So these are phasor. Now we'll bring it back to time domain expression. So I1 of t will be equals to, what does this represent? This represents the amplitude, because I've assumed this to be the peak value, not the RMS. So 3.9, and my initial reference was cos of 4t, and angle is minus 19.4. So this will be minus 19.4 degrees, and my I2 of t is equals to here, right, if I see the value is amplitude is 3.254. Okay, amplitude is 3.254 and the value is cos of 40 plus 160.6 degrees. Okay, so I can now, what are they asking? This expression, right, this energy expression, I have to simply find out this energy expression at time t equals to 1. I know I1, I know I2, just I have to put the values, plug in the values, right? So I will calculate at t equals to 1. So t equals to 1, what is this? So this will be, remember this is in radians, remember this is in radians, okay, and this is in degrees. So you cannot just simply add and subtract. Either you convert both into radians or both into degrees, right? You cannot simply add and subtract. Just be careful. Just be careful here. So this t is 1, so 4 radians. So if I want to convert into degrees, how do I convert from radians to degrees? So I know pi radians is 180 degrees. So 1 radian will be 180 by pi. This conversion I have to multiply. So if I have to compute 4 radians in degrees, this will be 4 radians will be 4 into 180 divided by pi. That is what I have to do. Okay, so this will come out to be 4 into 180 divided by pi. So it comes out, this angle comes out to be 229.183. Okay, so if I subtract 229.183, because like t is 1, right, that's why it is 4 radians, 19.4, and cos of this angle into 3.9, the current comes out to be, your current I1 of t at t equals to 1 comes out to be minus 3.374. Okay, what does this negative sign signify? This negative sign just signifies at t equals to 1, whatever direction I had assumed initially of current, it is actually the opposite direction. So current will be in this direction actually, but as I have assumed this direction, of course with respect to that direction it is telling me that it is negative. With respect to that direction it is telling me that it is negative. That's it. Okay, that is the only point that you need to take care of. What about I1? Sorry, what about I2? So I2 of t at t equals to 1, this will be equals to, so again 229.183 minus, sorry, plus 160.6. okay, cos of this 0.867 into 3.254, so it comes out to be 2.24 2 amperes. Okay, that is the value of the current. So this is positive, no worries. So remember, like the sign is according to the whatever initial currents, right? So you will put the currents as it is with respect to the sign as well here, right? If I have minus, I will put here minus 3.375. okay, sign I will put here minus 3.75. don't forget to put the sign correctly. So this value will come out to be E of t at t equals to 1 second. This value will be half L1 was how much? 5 Henry, if I remember, it was 5 Henry. Okay, so L1 is 5 Henry into I1 whole square. I1 is minus 3.375 whole square plus L2 is half into L2 is 4 Henry into whatever the current is, 2.824 2 whole square plus M mutual inductance was 2.5 according to the polarities, that's why it is plus according to whatever dot convention I have taken, and I will replace the current here as minus 3.275, whatever the direction of the current is. Okay, just be careful regarding the like directions and the signs of the currents. 2.28242. so this value we will calculate. Okay, so this value will be square into 2. So this is like almost near about 15.95 plus this will be 3.375 whole square into 5 divided by 2. This value will be 28.47 476 minus this will be 2.5 into 3.275 into 2.8242. So this will be minus 23.123. Okay, so this will be equals to plus 15.95 plus 28.476. So this will be 21.3. okay, roughly this will be 21.3 joules. So this will be the answer of this particular question. So like this was a big question, but some smaller things can be asked for W aspirants. For EC aspirants, like you just observe what I'm doing. Very very small thing can be asked from this thing. Okay, not much big. I'm just doing this calculation. So somewhat similar, like not similar question exactly, but a concept of energy of mutual inductance came in this gate 2025. Okay, so let's read the question. Consider two coupled circuits having self inductance L1 L2 that carry non-zero currents I1 I2 respectively. The mutual inductance is M with unity coupling coefficient. The stored magnetic energy of the coupled circuits is minimum at which of the following values of I1 but divided by I2. Very interesting question actually came. So they're asking the stored magnetic energy of the coupled circuit will be minimum when. So what is the stored magnetic energy of this coupled circuit? It will be E will be equals to half L1 I1 whole square plus half L2 I2 whole square, then plus M I1 I2. Now is this the only possibility? No, this is not the only possibility, because either the it can be in series, like it can be in what do you say, see aiding, right? Like both, if I have a coupled circuit here, this coupled circuit I have, what can happen is if the dot is here, then that means this current, right, enters to both the coils. So for this kind of combination the energy will be this, but I can have a separate kind of combination as well, right? So if the dot is in here, so in the first coil the current enters the dot, in the second coil current leaves the dot. So in this kind of cases the energy will be different. So here energy will be negative. Okay, I mean the mutual energy due to the mutual inductance will be negative. So that is the only difference that you have to consider here. Okay, and you will see, like we will solve for both cases, and you will observe that according to the given options only one of the cases is possible, both cases are not possible. We'll see. Okay, we'll see this. So they are asking me when the energy will be maximum or minimum. How do I calculate maximum or minimum? Maximum or minimum? Simply what we do, we differentiate, right? As there are two variables, so we will partially differentiate. So first of all, I will differentiate my energy partially. There are two variables here with respect to I1. So if I differentiate my energy partially with respect to I1, this will be half Li L1 into, like differentiation of I1, that will be 2I1 plus this will be 0. Okay, and this will be M I2. Because differentiation of I1 will be simply 1, right? So Mi2 is constant, partially differentiating, and we know in maximum minima we make it equal to 0. So just, if you don't know about partial differentiation, maximum minima, just trust me, we make it equal to 0. That's it, that is what we do. So from here I get a relation, the ratio of I1 over I2. So the ratio of, because in the question they have asked the ratio of I1 over I2. So I observe the ratio of I1 over I2 ratio of I1 over I2 will be equals to this will go there, so minus of M divided by L1. This is one of the possible cases. So minus of M divided by L1 is actually present in the option A. So option A is correct. This is a multiple select question. Now there can be, like, there is other condition, right? Other condition is what? That if I differentiate with respect to the current I2, if I differentiate current with respect to the current I2, so if I differentiate with respect to the current I2, then this will be half L1, because the first term will be simply gone. Okay, so one thing I forgot to mention is that, I'm sorry for that, although like they should not be in series, right? Sorry for that, they should not be in series. Actually there are two coils, there is multiple combinations, so something is there in the circuits, and the this is current I1 and this is current I2. So in the first case both currents enter the dot, and in the second case this current enters the dot I1 and I2 leaves the dot. Okay, so they are not actually in the series, because if they are in series then I1 I2 will be same. That is the only difference. So if I differentiate here with respect to I2, this will vanish, only this will be there and this will be there, right? So this will be half L2 into 2I2 plus M into I1 basically. So this will be equals to 0. So from here my I1 over I2, okay, will be equals to I1 over I2 will be equals to minus of L2 over M. Okay, so this will be equals to minus of L2 over M. So minus of L2 over M is over there in option D. So these two options are actually correct. Now you might have a question, what if, sir, I would have chosen this equation? So what if I would have chosen that both are in series opposing? I mean both are like one, for one coil current is entering the dot, for the other it is exiting. So if you would have assumed this one, right, what will be the difference is that your ratio of currents will actually be coming as positive. So here if you differentiate with respect to I1, you will see that you are getting this as L1 I1 and this will be minus M I2, that is equals to 0. So from here, right, my I1 by I2 actually comes out to be positive, that is plus M by L1, that is not present over here, that is not present, right? Minus is present. And same thing if I differentiate with respect to I2, so if I differentiate with respect to I2, my value will come out, this will come out to be half, like this will be half L2 into 2I2 minus M into I1, that is equals to 0. So from here I can directly say that my like my I1 over I2 will be again plus L2 divided by M, which is again not present in the options, right? From that's how you can understand that they were actually talking about this combination. They are not talking about this configuration. Okay, they are talking about this config, the first config. Okay, this is the two cases. So I hope you have understood this question, and this question actually came very recent. So GATE 2025 only this came. So that's why we like learning everything is important, and EC also they can ask. This actually got asked in EE, but EC also they can ask this question, but there's a real chance. So I hope you have enjoyed this lecture. If you did enjoy, make sure to hit the like button, make sure to comment down below in the video. And in the next lecture, we will discuss about three-phase circuits, and that will be basically the last lecture for the EC aspirants. After that, only EE aspirants will watch. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start with the lecture 5 of our this prerequisites of machines. So this will be the last lecture for EC aspirants. Okay. So in the first lecture, I actually told a mistake that it was the till lecture 4. The for EC aspirants, okay, for EEC for EC aspirants, this will be the last lecture. After that, you guys don't need to watch anymore. Okay, you are done. You're done with the whole network theory. So in this lecture, we will mainly discuss about three-phase systems. So let's discuss about three-phase system. So mostly whatever we have been discussing till now are single-phase system. Okay. So in a single-phase system, what does mean this phase, right? Phase means that all the supplies will have the same phase. supplies will have the same phase. Okay, supplies will have same phase. So if you observe in the left hand side diagram, this diagram, that here I have a supply which is Vp angle phi, and here also I have two supplies, but both of them are having same phase, right? So it is a single phase supply only because the neutral is common between these two supplies, and both of the generators have the same phase. But if I see in the right hand side diagram, I observe something different, that this voltage source has a amplitude of Vp, that is fine, but phase angle is 0 degrees, but here the phase angle is minus 90. So they have phase difference between them. So whenever there is a phase difference, that means it is a polyphase system. Poly means multi-phase system. So in this case, it is a two-phase, three-wire system because I have two phases and I have three wires. Here I have single phase, three wires. Here I have single phase, two wires. Okay. So that is how we classify our polyphase systems. Now let's come to why three phase. Okay, why we have used three phase? Everywhere you go, like whatever supplies you are getting from your home, okay, if you go around your home, right, the nearby distribution transformers, all those things, three phase supply is coming. Why three phase? So three phase system dominates the power distribution and generation for mainly three reasons. Global standards, almost all electricity worldwide is generated and distributed in three phase. So anywhere in the world, maximum 99% of the cases, the electricity that is generated and distributed are in the form of three phase. Okay, everywhere it is distributed in three phase, so it helps. It is a global standard. That is the first thing. Second thing is constant power delivery. Unlike single phase or two phase systems, three phase power does not pulsate, ensuring stable power transmission. Okay, so if you remember in the complex power chapter, we had derived the power expression. If the voltage and current are both sinusoidal, how will the power expression be? Okay, so in case of single phase, right, the power, if you remember, was pulsating. Sometimes it was negative, sometimes it was positive. Okay, but in three phase it will not be pulsating. Okay, so if in three phase it is not pulsating, that means the harmonics will be lower, and that means it will reduce the vibrations in machines. Okay, that is better and greater efficiency. For same power output, a three-phase system requires less wiring than an equivalent single-phase system, making it more economical. So if you see, this is a three-phase supply. Okay, how many wires I required for a three-phase supply? 4 wires. And here, to supply the same power, right, I will need three of this copy, right, 3 copies of this. So it will be what? How many wires I will require? 6 wires. Here I only required 4 wires, and here I required 6 wires to let's assume to transmit 10 kilowatt of power. Here I require so much lesser amount of wires, right? So of course, if I want to transfer or deliver power, right, from my generating station to your home or somewhere, I have to connect the wires. Okay, and those wires actually cost money. So of course, if we are able to save the costing in wiring, that will be better. And how, you might have a question, sir, how is it possible that with 4 wires I'm able to transmit the same power? Because all of them have a same common neutral. And if the neutral is balanced, right, then the neutral current is actually 0. If all the three phases are balanced, then the neutral current is actually 0. I'll discuss about that later on. Okay, and easy guys, right? Easy guys, don't have to take too much stress on this particular topic. Just listen to me whatever I'm saying and just do the numericals, whatever we're doing. That's it. Okay, no need to study it again, or just study once, that's it, and once in a while revise it. Okay, no need to stress. I'm talking about EC aspirants. Okay, so yeah, we will discuss more about this. So now you might have a question, sir, why 3 phase, then why not 6 phase, why not 12 phase? So as we increase our complexity, right, sorry, as we increase our phase, the complexity also increases. Okay, of course there is a what do you say, there is a drawback to everything, right? So it's not like I can increase my phase infinity times. Okay, as more and more phase becomes as I increase my phase more and more, the complexity increases, and to generate, right, 6 phase power or 12 phase power, it will be more difficult. We are easily able to generate 3 phase power because our generators that we built, so we will study this of course in machines only, that is why we will study that we are easily able to generate 3 phase power. Okay, so it is easier for us to deliver the same 3 phase power. Okay, 6 phase generation of 6 phase will be more and more difficult. Okay, I hope you have understood this point. So yeah, this is the machine, and you can ignore this particular thing right now, that how our winding plays, all those things we will learn when we will actually study the machine, electrical machines. Okay, so yeah, so in it, just these are the I just wanted to give you overview how is 3 phase power generated. You can ignore. Okay, now here, this is the important portion. So there are mainly two kinds of three-phase supply. Okay, one is the star connected three-phase source, another one is the delta connected three-phase load. Okay, there is a bit of difference between star and delta, because you can connect three phases in three different like two different ways. One is the star connected, another one is the delta connected. In the delta there is no neutral wire, in the star there is a neutral wire. Okay, neutral wire has its advantage. Okay, neutral wire has its advantage, so mostly we use star as well, sometimes we use delta as well, depending on the use case. Okay, and another important point is that if I have three phase, okay, let's say VA, VB, VC, so the three phase will be the supplies of the three phase will be phase shifted by 120 degrees. If it is a balanced three phase network, then all of them will be phase shifted by 120 degrees. So if I start from 0 for VA, for VB I will start after a lag of 120 degrees, for VC I will start after a lag, another lag of 120 degrees, and like this the three phases, the three phase voltages are phase shifted by 120 degrees. Okay, but their amplitude peak values will be same, just their phase difference will be different, because that is what the definition says. If I have a three phase system, I will have three sources with three different phases. Got it? Okay, so here, right, this I actually taught in my power electronics class. I will just quickly revisit this. So already discussed that three phases I have. So either they will call it VA, VB, BC, okay, or they will call it VR, VY, VB, RYB, either RYB or ABC. Okay, I hope you are comfortable. RYB was the older notation. Like previously we used to color code our wires for three phase supply: red, yellow, and blue. Okay, now we have changed. We have gone to ABC. Okay, so considering like this three phase supply, so if I have a red phase or AB, then it will have its value will be Vm peak into sine omega t. Then the value of the Y with respect to the neutral, I'm talking about neutral, I'm not talking about delta right now. I'm not talking about delta connection, I'm talking about star connection. This is a star connection. Okay, so Vyn will actually lag by 120 degrees of Vr. So if it lags, right, so if this is my reference, Vr is here, then I will lag my Vy will lag Vr by 120 degrees. So I will move in the clockwise direction by 120 degrees. I will move in the clockwise direction by 120 degrees. Okay, then VB is here. Okay, VB is here. So VB is VMP sine omega t plus 120. How is it plus 120? Actually, it lags by 120 of Vy. Okay, it lags Vy by 120. So it is minus 240, and I can change my minus 240 to plus 120. How? Just adding 360, because adding and subtracting 360 does not make any changes. If I add and subtract 360, it will not make any changes. Okay, so that is what my VBN is. So these are my phasor representation. Okay, because we will use this actually. We will use this. And if the load is a balanced load, I will discuss about balanced load. If the load is a balanced load and it is a lagging load, then the current IR will lag by some phi angle with respect to VR. The current IY will lag the voltage with respect to like VY with some angle phi. Current VB will lag the B phase voltage with respect to like by some angle phi. Okay, by some angle phi. Okay, so this is how like everything will work out. This is how everything will work out. Okay, and one more important point is, like, if I have a supply like this, okay, what if, like, there are two terms, one is the phase voltage, another one is the line voltage. Okay, I will discuss about that. So if I just reduce the size, so here if you see that this particular voltage, right, VAN, is actually called as the phase voltage, because with respect to neutral I am measuring for a single phase. So this particular voltage is called the phase voltage. Phase voltage. Okay, and this voltage VAC, right, or VAB, whatever you want to call it. Like, let's say I'm measuring the potential across these 2 points. So these are called the line voltages. Why line voltage? Why line voltage is called? So I'm measuring the voltage across the two lines, right? Not across it on a single phase. This is called as a single phase. I'm not measuring across a single phase. I'm measuring across the line. So this is called the line voltage. So for a star connected network, if we do this, right, if we do this calculation, okay, Vrn minus Vyn, I have taught this, okay, I will not derive here, we don't have time for to derive. It will come out, I will directly, like here also I think, I guess I have derived somewhere, right? Yeah, it will directly come out to be equals to, this value will directly come out to be equals to Vry, right? So Vry is what? Vry is Vrn or Van. Vab will be Van minus Vbn. Okay, that is what is written over here. So this directly comes out to be root 3. Like you can solve, it will come out like this value will come, right? I have to this from this value I have to subtract this value. So it will be a formula of sin A sin B. From there, if you remember the formula of sin A sin B, you can simplify, and ultimately your answer will come out to be root 3 Vmp sin omega t minus 30. Okay, so it will actually lag by 30 degrees. So that is the like difference that I think I have derived here. Okay, not lag, sorry, this will be plus, right? Sorry, that is what I am thinking. Sorry, not lag, it will lead, right? So like if you just calculate the result, this lead value will come out, okay, plus 30. So where will my Vry or Vab lie? Vab will lie somewhere around here, right? It will lead by 30 degrees. Okay, you can do the calculation. I'm not doing it. Okay, this you have to unfortunately remember. Okay, this you have to remember, because for electrical guys this is very important, and this anyways you have to remember, and this will automatically be remembered by you because you will use this multiple times in different subjects. Okay, so this will be Vab or Ry, anything. Vab and Ry both are same. So Ryb is same as ABC. Okay, so it will lead by 30 degrees. As it is a balanced system, all other voltages will have a phase difference of 120 degrees. So now my Vyb will be lying somewhere here. Okay, Vbr will be lying somewhere here, not here, sorry, sorry, we will be lying somewhere here. So I have actually derived it, you can see. Okay, I have already derived it. So my Vbr will be lying somewhere here, Vyb will be lying somewhere here, uh, Ry will be lying somewhere here. So the angle difference between the line voltage and the phase voltage will be 30 degrees. Okay, now there can be like opposite voltages as well. What do you mean by opposite voltages? Let's say we don't want Vry, we want Vyr. How will you write Vyr? Vyr is simply Vyn minus Vrn. Okay, so I had already calculated Vry. Vry is Vrn minus Vyn. If I multiply a negative sign, I will get this value. So simply what you do is, we already know Vry, just multiply a negative sign. So if I multiply a negative sign here, this will be minus under root 3 Vmp sin omega t plus 30. So this will be root 3 Vmp into sin omega t minus 150. Okay, so that is the thing here. That is the main point, main crux that you have to understand. Okay, so like just you have to remember these. What you have to remember, this one. Okay, this, either you make a short note or something, and you have to remember these values as well. Okay, Ryb and ABC are interchangeable. Please don't get confused. Remember this one and this one as well. So these slides are very, very important. Okay, and another point is that I was discussing about this, and what is the current. So in case of star connected load, right, in case of star connected load, the line current and the phase current are same, because like whatever current is coming out is the same, right? So if I connect a load here, this will be the load here across the neutral and the phase, and so this is coming out of the phase, and same is going to the line as well. So line current and phase current are same, But in case of delta connected load, the line current and phase current are different. So if I see here, if I let's say this is my voltage source, right? Where is my delta connected load? Here. So here, right, my load is here. Load will be connected across the 2 points. I don't have a neutral here. So line current is, phase current is coming out of this phase, right? Let's say this is I A B, but line current is different, IA. Like what will be line current equal to? Line current will be equals to the summation. This phase current will go here, like direction does not matter. It will be the KCL at this node, right? It will be IC will be equals to IAB minus ICA. Okay, so in case of delta, the currents are different. In case of star, the voltages are different. Okay, this also you have to remember. So like this slide is also very important. In case of star, the voltages will be different. Just the what will be the amplitude of the voltage? Amplitude will get multiplied by root 3. In case of star, the current amplitude will get multiplied by root 3. Okay, for the line current or line voltages will always be higher than the phase current or phase voltage. Okay, or always be higher or equals to. So line current or voltage, so line always have the higher power. That's how you remember that line always will be either greater than or equals to phase. Okay, when will it be equals to? It depends. So in case of star, it will be equals to line current and phase current will be equal in case of star. And in case of delta, the line voltage and phase voltage will be equal. How? So this is my line voltage and I don't have phase voltage is also this, right? So if you see, this is my line voltage and this is my phase voltage, both are same. Okay, got it. So that is the important point that you have to remember here. Now this we have discussed, whatever I have discussed, like it is written over here. Another thing is that if generally there are two phase sequence possible. So this whatever phase sequence I had discussed here, it is known as the positive phase sequence. What do you mean by positive phase sequence? Positive phase sequence means that first the phase A will come. Okay, if you see the diagram, if I copy this diagram, first the phase A comes, then the B comes, then the C comes. First A comes, then B comes, then C comes. Okay, so this is the first one, A, B and C. Okay, A, B and C, that's it. Now if maybe I don't want this kind of sequence, I want first C to come. So if I want C to come, so C voltage will be here first, then B voltage will be here. So in those kind of cases, it is known as negative sequence. So ACB. So there are only two possible cases. Like first A will come, B will come, C, then again A, B, C, like this. And there is another possibility that then first A will come, then C will come, then B will come. Again A, C, B. So you might ask that aren't there any other possibility? No, all the possibilities have been taken care of. If you see, if you use ABC as sequence, it is same as telling me that BCA as sequence. It is same as telling me that CAB as sequence. Got it? All these represent the same thing only. Okay, so if you tell me the phase sequence is ABC, then I can tell you phase sequence is BCA. That is same, right? That is same. How is it same? So you tell me that phase sequence is ABC. So that means A will come first, then B will come first, then C will come. I tell you the phase sequence is BCA. That means B will come, then C will come, then A will come. Okay, both are same. Or we can write here CAB. That is also same. Okay, first C will come, then this is the B waveform, then this is the A waveform. So all the combinations have been taken care, all the positive combinations. So and other three combinations are there like this. So ACB is one of the phase sequence, negative phase sequence. Then I have CBA, then I have BAC. So if we say that ACB is my phase sequence, I will say CBA is also can be called as a phase sequence for this system. So first C will come, then B will come, then A, then B, or BAC is also a correct phase sequence. Okay, so in this case, if it is like this, positive like clockwise, it is known as in clockwise, so it is known as the positive sequence, then the values will be like this. Okay, if it is a ACB sequence, if it is a ACB sequence, so my VAN will not change, of course. I'm talking about star load right now. Okay, everything has been discussed for star load, so star source. VAN will be VP angle of 0, and your VCN will be VP angle of minus 120, and your VBN will be VP angle of plus 120. Okay, that will be the difference. So from here I can directly say that what will be my line voltages. Okay, so my line voltages will be VAC will be equals to root 3 VP angle plus 30 degree. So how do I remember? Just remember whatever is coming second, right? Like that you derive. Now the whatever next. So this is how I remember, right? The first one I will remember. Then the next line voltages will be just phase shifted by 120 degrees. So just remember one voltage. I remember VAN, that is in 0 degree difference. So other voltages will be phase shifted by 120 degrees. That's it. That's how I remember. Okay. So V, now what will come? VAC I have taken. So now VCB will come. Just like that. If you see V, not here actually. This is wrong. Why is it? Okay, here only we have written it, right? What is it? Okay. Like okay, one more thing I forgot to say is that VBN minus 240. Okay, what is going on here? No, this will be 0, right? This should be 0. Like we can represent our phase in many ways. This should be 0 degrees. Okay. So like what, like this is my actual ABC sequence. So I can subtract 120 degrees with all the voltages, and still it will follow the ABC sequence. Okay, still this is following the ABC sequence because this will be minus 120, this will be minus 240, this will be 0. Okay, so still it will follow the ABC sequence. Okay, all this will follow the ABC sequence. Got it? So yeah, so that is the thing. This occurs when the rotor spins clockwise. So now where was I was discussing this, right? So here also if you see that initially I had derived that for VRY, next it was VYB, the other phase, next it was VBR. So that's how you remember. You make a note and remember how to remember. Okay, so first you write the VRY, the first two phases. Okay, VRY, you write the first two phases, then you continue, you write the second one Y you here, and the whatever is left VYB, then you write, then you copy this one, and then whatever is left you write that, because already you have taken Y, I will write R. Okay, same thing here. So now I will copy this last one, and whatever is left I will write that. And what will be the phase of this? This phase will be very simple. This will be root 3 times VP angle. Now there will be a phase difference of 120. Very simple. Lag phase difference of 120, because here also there was a phase difference of 120. So this will be minus 90. Now again I will write here, I will copy the last one, and I will write whatever is left that was not used. So this is VBA. So VBA, again the magnitude will be root 3 VP into this will be what? This will have a phase lead of plus 120, right? Because here also if you see from the first term I had a phase lead of plus 120. So this will have a phase lead of plus 120. So this will be plus 150 degrees. So I hope now you can derive for the other expressions like VCA, VBC, VAB, just the negative. Just add or subtract a 180 degree angle with this particular voltages, you will get your value. Okay, so that's how you remember. Just remember these two, and then from there you can derive the other ones. Okay, so in case of ABC sequence, what will happen? I will rotate in the clockwise direction. So first A will come, then B will come, then C will come. In case of ACB sequence, if I rotate in the clockwise direction, first I will encounter C, then I will encounter B, then I will encounter like that's how I will encounter, right? If I rotate in the clockwise direction. So just hold on. So this omega is actually wrong. This should be rotating in the clockwise direction, not in the anti-clockwise direction. So this is how also you can determine the phase sequence if the phasor diagram is given. If the phasor diagram is given and if I rotate in the clockwise direction, first I will encounter A, then I will encounter here. If the sequence is ABC and I rotate in the clockwise direction, first I will encounter A, then I will encounter B, then I will encounter C. So this is for the phase sequence ABC. Okay. If I encounter in the clockwise direction for phase sequence ACB, first I will encounter A, then I will encounter C, then I will encounter B. Okay. From this phasor diagram also you can determine the phase sequence. Now let's discuss like about three phase power. Okay, what is the three phase power? So the three phase power comes out to be this actually. It is not pulsating. Three phase power comes out to be this. It is not pulsating. You can derive it. So three phase power will be what? For a single phase, the voltage is VPH and current is IPH. Okay, and three phase power will be multiplied by 3, and obviously Y is I conjugate because it is a complex power. Okay, so if I write these expressions down, ultimately VPH into IPH will come out to be what? VPH into IPH will come out to be VP phase RMS, I phase RMS into cos phi. VRMS, IRMS into cos phi. That is the single phase power multiplied by 3. So this can be rewritten in terms of peak voltages. So VRMS is what? V maximum divided by root 2. IRMS will be what? I maximum divided by root 2. So it will be V maximum, I maximum, and root 2 is getting multiplied 2. So it will be 3 by 2 VMP IMP cos phi. Okay. So my three phase power expression can be written in terms of this. Also I know that in case of star load, this is in case of star load. Okay, star load, I know this, that, or any load, this will work for any load actually. I know in case of star or delta, either one of the relationship follows. What is the relationship? That my V line to line peak or RMS, whatever you want to discuss. So from here also I can come. So all this formula, you can remember one formula and derive all the others. So my three phase power will be what? Single phase power into 3. Okay. What is single phase power? Single phase power is V phase into I phase conjugate, or I can write V phase RMS into I phase RMS conjugate. So I phase RMS cos phi. Just hold on. Okay, and three phase power will be 3 times this. So it is 3 times this. Okay, so this is sorted. Now there are multiple variations of this formula. So sometimes you might require sometimes the peak voltages will be given, so you have to use this formula. Sometimes the line voltages will be given, so you have to use this formula. So you have to be smart. You have to be very, very smart. Okay, that is what you have to take care of. So I can directly write that if I want to write this in terms of peak value. So I know that my V phase peak value will be what? Root 2 into V RMS, V phase RMS. Correct? So or my V phase RMS will be peak value VMP divided by root 2. Okay. So I can directly say that I can replace this, right? I can replace V phase RMS, I phase RMS here. So what will this expression will come? Now another thing I can say is that we have already discussed that if I have star or delta, so for a star load the voltages change. For a star load the V line to line is root 3 times the V phase. If it is peak, then this relationship will be for peak. If it is RMS, this relationship will be for RMS. It is valid. So I will do that actually. So what I will do, I will replace my V phase by V line to line by root 3. So if I replace my V phase by V line to line by root 3, what will happen? This 3 divided by root 3 will come. So this will become root 3, and I know for a star load the I line to line and the I phase are same, so it does not change. So this I phase RMS will become I line to line RMS, that's it. So this is also another formula. Cos phi of course will be cos phi the power factor of the load. Okay. Now this factor you can ignore, the supply power factor. This is not important. Okay. So else you will get confused. This is for the power electronics guys. So you can ignore the supply power factor for now. Now let's discuss for delta load. So this formula is valid for delta load as well, and this formula is also valid for any kind of load. So for delta load, what will happen is that here I know for delta that the line to line current is root 3 times phase current. Okay, line to line current is root 3 times phase current. So this will be what is my voltage? Voltage is same, right? Line to line voltage and phase voltage are same. So what will happen now? Instead of this I phase RMS, I will replace in terms of I line. So this will be I line divided by root 3. So again root 3 and will get cancelled. So I will have root 3. This VL will just V phase will be replaced with VL. I phase will be replaced with IL. So ultimately this comes out to be root 3 VL IL cos phi. So that's how, like, this formula is always valid no matter what. Okay, so that was the formula for this one. Now let's discuss about a three phase load. Okay, I have not discussed about, like, I've discussed about three phase power. Actually this should have come later, is after discussing about three phase load, but that's fine. We will move this slide to here, right? So let's discuss about three phase load. So there are mainly two kinds of load. As there are mainly two kinds of source, star and delta connected, there will be mainly two kinds of load. Okay, so one is the star connected load, another one will be the delta connected load. So in case of star connected load, there can be two options again. The neutral wire can be present or not present. So neutral wire is generally used for like transferring the unbalanced current. Okay, if the system is completely balanced, then the current in the neutral wire will be 0. Okay, don't worry, in the syllabus only balanced supply is there, so you don't have to worry about unbalanced system. In power systems we will learn about unbalanced supply. Okay, so that is about the neutral connection. So I have two connections, star and delta. So for a star connection, if the load impedance is Zy, for the same this what will be the per phase impedance if the supply is also star connected? So per phase impedance will be between the a line and between a neutral, so it will be same Zy only. So let's assume all of them are Zy. Okay, if it's a balanced system, so all of them are Zy for now. Let's not keep them Z1, Z2, Z3. Let's assume all of them are Zy. So if all of them are Zy, okay, what will be the equivalent delta? Okay, what if I wanted to measure the per phase impedance in delta? What if my source is delta connected? Okay, so for a, if my source is star connected, then there is no problem. Okay, I will copy this whole thing. We'll just do one thing. Let me so here, right, if the, so where can I will go to the next page. So okay, it went away. Let me mark it log. Yeah, still it is log. Okay, yeah. So if I have a star connected supply and if I copy this thing, and if I connect it, so what will be the per phase impedance that we will measure? So per phase impedance, right, if I just connect these wires, if I just connect these wires together, okay, A with A, N with N, B with B, C with C, then the per phase impedance here, right, what I will measure is Zy only, that is the per phase impedance. Okay, now if I have a delta connected supply, and I want to measure the equivalent impedance, right, of the same star connected network. How will I measure? Because it is not that simple, right? It is not that simple basically. So how will I measure? So what I will do is I will convert this into delta. I cannot measure, I cannot connect A, B and C, then neutral wire will be left out, right? I cannot measure the impedance. So what we will do is we will convert this into delta. So how do I convert this into delta? So delta conversion is very simple. Delta conversion is very simple. So if you remember, if I have to convert from star to delta, how do I remember? Like how do I remember the formula? There are mainly two formulas. Star to delta, I remember with the first word, okay, first letter. So I have star, so it is summation. So there are mainly two formulas, right? If you remember, there are mainly two formulas. One formula was it was Z1 plus Z2 plus Z1 Z2 divided by Z3. Okay, another formula was Z1 Z2 divided by Z1 plus Z2 plus Z3. Okay, these two formulas are there. So if it is star to delta, then I have S here. So S means summation. Summation means this one. So I will choose this formula. Okay, that's how I used to remember. Of course, you can have your method of remembering the formula. So here I will convert this, right? So I have to convert from star to delta. So let's assume all the impedance are ZY only. All of them are same. So it will be ZY plus ZY plus ZY into ZY divided by ZY. So it will be 3ZY. So actually, if my supply is delta, right, then the per phase impedance delta will be 3 times the per phase impedance of the star connected load. So that is what I have written over here, the comparison. That is what I have written over here. Okay, I hope now you have understood the thing. So both the star and delta connected loads, balance loads, because all of them are balanced, that means all the impedance are same, can be transformed with this relationship. Okay, either you can remember this or simply use this formula, right? Whatever I have discussed, star to delta conversion, you have studied since childhood, so you will be able to do it. Now, three phase load can have two possibilities, right? Sorry, four possibilities. If as the source is star, so the load will be also star. If the source is star, load is delta. If the source is delta, load is delta, and if the source is delta, load is star. So we will cover these three. Okay, and this one, the third one, I will give you as homework, delta delta. Okay, like not that, like this is not that difficult, this will be easy, because whatever system will come, all of them will come as balance load. We will solve few gate PYQs as well, don't worry, we will solve few gate PYQs as well. So three phase power we have already discussed. So let's like solve few basic questions. Okay, so here we have to determine the phase sequence of the set of voltages. So if I assume my so everything is in cos, so we'll assume that my 200 cos omega t to be my reference. Okay, so 200 cos omega t is my reference. So if 200 cos omega t is my reference, that means that this VAN is leading by 10 degrees. So this is my reference. Okay, and VAN is leading by 10 degrees. Okay, now my VBN is lagging by 230 degrees. So 180 degrees will be somewhere here, 230 degrees will be somewhere here. Okay, so my VBN, okay, what angle is this actually? Okay, this is 180. Okay, I can measure the angle as well, that's great, man. So 230, right? How do I measure the angle? This is 180. Okay, it is 230 will be somewhere. Okay, it is, why is it reducing? Okay, it is measuring the angle in the clockwise direction. How do I measure the angle in the anti-clockwise direction? So in the clockwise it will be 130, right? Yeah, 130. So this angle will be 130. So 130 will be somewhere here. So this is great feature. Okay, 130 will be somewhere here. Okay, this is like 130 in the anti-clockwise direction or 230 in the clockwise direction. Both are same. So this will be VBN. Okay, now VCN is lagging by 110 degrees. So if it is lagging by 110 degrees, that means it is leading by 250 degrees, leading by 250 degrees. So to lead by 250 degrees, so I will be lying somewhere around here. Okay, so this will be my VCN. So now, like, how do I identify the phase sequence? Very simple, right? Very simple to identify the phase sequence. Just move in the clockwise direction, rotate in the clockwise direction, and see what phases I'm getting first. So I'm getting A, then I'm getting C, and then I'm getting B, ACB. Okay. So very simple, very easy. Or you can directly mathematically do it, or you can do it in the phasor format. Whichever one is suitable by you, you do it. Whichever one is suitable by you, you do it. Okay. Very simple. Like these kind of question also can get asked. Okay. This kind of simple question can get asked in EC. Okay. So just be careful about that. So now let's discuss about balanced start to star connection. Okay, let's discuss about balanced start to start connection. That means my supply is also star, my load is also star. So here, right, bit of like many things are here. So we will dissect each and every term slowly. So in a balanced star to star, what happens is I had assumed that everything is ideal, that I have only load resistance, I don't have any source impedance and line impedance. So the wires that come to your home, right, of course they will have some impedance, right? It will be small, but it will have some impedance. Okay, and your source of course will have some source impedance. Generally what happens, like overall your star impedance, right, overall impedance, these three will get added. So Zs, like these are three are in series only because current is flowing in series. So Zs plus Zl plus Zs plus the line impedance plus the Z capital L. Okay, so this is my Zy. Now generally what happens, generally if nothing is mentioned, we will assume our Zs and my Z ZL, this will be the line impedance, actually this will not be the E line impedance. ZL will be almost equals to 0. Okay, for our easier calculation. So approximately my Zy, the overall star network impedance, becomes ZL only, the load impedance only. Okay, that is what we assume. So I hope you have understood this basic point. Now, like how the current will flow. So if you see the currents, right, for the phase A, currents will start from here and then come back through the neutral. For phase B, currents will start from here and then again come back through the neutral. And for phase C, currents will come back here and then again come back to through the neutral. Okay, so this neutral impedance also can be sometimes neglected. Okay, so that's how that will be the flow of the current basically. Now voltages we have already discussed. So like we have now, this is the balanced star to star connection with approximated impedance. So voltages we had already discussed, currents also we had discussed. Since the sum of the voltage neutral wire carries no current, phase voltage. Okay, so like the balanced network, right, IA is coming here, IB is coming, IB is coming here, IC is coming here. So what will be IN? So if I apply a KCL at this node, IN plus whatever is the incoming current, IN plus IA plus IB plus IC will be equals to 0. Okay, so my IN plus IA plus IB plus IC will be equals to 0. So ultimately my IN will be equals to minus of IA plus IB plus IC. And if the system is balanced, you will observe that all of them are phase shifted by 120 degrees. So what will happen is that this sum will come out to be 0. So like visually also I can tell you that the, let's assume that the phase like the phase current IA will be somewhere here. Okay, just let's assume this. So IB will lag IA by 120 degrees somewhere here. Okay, so 120 degrees, where will 120 degrees lie? 120 degrees, right? It's lagging, so it is 240 degrees. So it will lie somewhere 240 degrees. Okay, so 240 degrees will be somewhere here. Okay, So this will be my IB, and my IC will lead IA by 120 or it will lag IB by 120. Any both way is same only. This B I am not able to write properly. Okay, so IB will lie somewhere, lie 120 degrees, so it will be somewhere here. Okay, so IB will be here, just like the amplitude also is same only, even though it seems that amplitude is different, but it is same only. This will be IC. Okay, so if you add these three up, right, what will happen if I add IC and IB? Actually the component will come somewhere around here, the addition of IC and IB. So these will cancel each other out, so ultimately the summation of all the three IA, IB and IC will be totally 0. Okay, all the summation will be totally 0. So that is the crux basically for a balanced system. For a balanced system, the sum will be 0. So like how can I prove it as well? I can prove it as well. So if I have a system like this, right, if I have a system like this, and what will be the phase current IA phase current will be what? This VAN by ZY, that will be the IA phase current, correct? The voltage across the impedance. So IA will be VAN divided by ZY, IB will be VBN divided by ZY, IC will be VCN divided by ZY. So same thing, if I add IA plus IB plus IC, so it will be VAN divided by ZY plus VBN divided by ZY plus VCN divided by ZY. So this will be equals to 1 by ZY VAN plus VBN plus VCN. Same again, if you remember the sum of the voltages as they are finite, this will also be equal to 0 only. Okay, so ultimately the summation is 0. So IN is also 0. Hence the drop in this impedance, right, even if there is impedance here Zn, the drop will be 0 because current is 0, hence there is no drop. So the V small n capital N, if there is impedance here, right, if there is some impedance here, current is 0, so hence the drop is also 0. It will be IN into Zn, which will be 0 only. So it does not matter if I have neutral impedance or not, the current will be 0, there will not be any loss in the neutral. Now if let's say if it is a balanced system, what I can do, I can convert, because it's a bit hectic, right, to draw all this, I can convert this balanced three-phase system into a simplified per phase system. So in per phase system I will just write the phase A voltage and phase A current. Okay, and all the other phase will be what? The amplitude will be same, just they will be phase shifted by 120 degrees. That's it. They will be phase shifted by 120 degrees, like phase B, phase C. Okay, so we simplify. So simply basically my IA will be what? IA will be VAN by ZY. This is enough. Okay, and for all the other phases I have to just add the angles. That's it. Add the angles. So let's solve a very basic question on this. So first you have to see whether your system is balanced or not. So I am observing that my system is actually balanced because I see this is my impedance 10 plus j8, this is also 10 plus j8, and this is also 10 plus j8. So in all the three phases the impedance is balanced. Is my source balanced? Yes. This is 110 angle 0, this is 110 angle minus 120, this is 110 angle minus 240. So all of them are phase shifted by 120. Load is balanced, source is balanced, and I have a neutral impedance. But it does not matter because I already know that the neutral current will be 0. Okay, it is a, okay, sorry, it is not a neutral current, sorry, it is like we don't have any neutral connection here, just we have a source impedance is also balanced, and the load impedance, that's it. Okay, so what we have to calculate, we have to calculate the line currents. So what I can do is I can convert this three phase system into equivalent single phase system. Okay, and then from there I can simply write down the expressions. So this, right, this is a VAN, and okay, where is the neutral here? There is no neutral. This is like a this is the common point, right? So neutral is here, right? So even though they have not shown my neutral, so I can assume a virtual neutral. Even though they have not shown any neutral, I can assume a virtual neutral because this is the common point of the star connected network. So this portion is a single phase only. Okay, I can write down this. So if I convert this, this will be V 110 angle 0, and 5 minus J2, 10 plus J8, and so this is a like single phase conversion, whatever we have discussed, single phase conversion. So I can directly find out the IA current, and if I know the IA current, I will be able to find out IB and IC as well. Okay, this is my neutral, this is small n, this is capital N, and this is my phase A, correct? So what will be the current here? So this is my VA basically. So current IA for the single phase equivalent model, IA will be equals to VA 100 divided by the whole impedance, right? So it is 5 minus J2 plus 10 plus J8. So this will be 100 divided by 15 plus J6. So I can directly from here calculate the values basically. So if I want to calculate the values, this will be 15 whole square plus 6 whole square whole under root 16.185. This by multiply by 100. This will be 6.19 angle. What will be the angle? That is what I have to find out. So angle I have to find out, right? Okay, something am I doing wrong? Like it feels like something I'm messing up here. This is J6, this is 15. Yes, everything is correct. Okay, just let me quickly verify this. 15 whole square plus 6 whole square whole under root, okay, into 100. No, it is correct only. It is 110. Okay, sorry, it is 110. That is what I was thinking. It is 110, sorry. So it is 110. This will be 110. This will be 110. So 210. So this will be 6.8. What about the angle? Angle is what? Angle is 6 divided by 15 tan inverse. So 21 minus 21.8 degrees. Okay, so this is the current, this is the load current. Okay, and this is the phase A current. What will be the phase B current? Phase B current will simply lag this by 120 degrees. Amplitude will not change because it is a balanced system. So it will lag by 120. So this will be 141.8 minus 141.8 degrees. And what about phase C? So phase C will lead by 120 of phase A current, right? So it will lead, the amplitude will be same, 6.81. So it will lead. So this value will be 98.2 degrees. Okay, so these are the currents. So that's how simple it is. So these kind of simple question will be asked only. Okay, you will be given a balanced three phase load like supply, and you have to convert this, analyze it as a single phase supply, and then calculate the currents and just phase shift all the other values with 120 degrees and you're done. Okay, that's how simple it is. So now let's discuss about the balanced star to delta connection. So if I have a star to delta, what we will do is, first of all, we will convert this delta to star load. Okay, we will convert this delta into star load. That will be easier for us. That will be easier for us. Okay, like two things we can do. Two things we can do. There are two ways to go about this. Either I convert this into line, like if you don't want to convert, right, from star to delta, you can directly also solve. Okay, without converting it star to delta, you can directly also solve. How will you solve? So there are two methods to solving this. So first method is simple conversion. So you convert this load, you convert the load from star to delta. Okay, this is the first way to do, first way to solve. Let's say if you don't want to convert, right? Next, what is the next way? Next way is you calculate using line voltages. Use the line voltages. So we have derived the line voltages, right? So these are my phase voltage, VAN, VBN, VCN. What is the line voltage? Line voltage is already given. This I have already derived. This I have already derived in the starting of this lecture. So what will be this value? IAB current. IAB will be VAB divided by Z delta. So what is VAB? VAB is the line voltage. So line voltage is given here. That's how simple it is. What is IBC? IBC will be VBC divided by Z delta. So what is the line voltage? Line voltage is VBC, that is given here, divided by the Z delta. Like that also you can simply solve. Like that also you can simply solve. For line voltages, what you have to remember, that the amplitude increases by root 3 times and the phase shift is there by plus 30 degrees. Phase shift is there by plus 30 degrees and amplitude increases by root 3 times. That is the only thing that you have to take care while using the line voltages formula. Okay, same thing whatever I have discussed is written over here. What this will be my currents, right? So these are the currents across the load. These are the currents across the load. Now if you want to measure the line current, IA, IB, IC, how will you measure the line current? So you can measure the line current with respect to like this. IA will be what? It will be IAB minus ICA if I apply KCL at this node. So like that you can calculate the line currents. Same here. And for this the current expression will come out with this you don't need to remember. No need to remember this. Okay, you can simply use the phasor addition formula and from there you can calculate these many things. If you remember, right, you will get mad. So I don't want you to remember everything. Just the voltage is enough. From voltage you will be able to find out the current. And if you don't want to actually calculate this without if I don't want to calculate this, right, so this method you will use when, second method you will use when I have to actually calculate the phase currents across the load, currents across loads. So if I have to calculate the currents across the load, I will use this line voltage method. So simply line voltage divided by the impedance will give me the currents across load. Now if I want to measure the currents across the line, what I will do is simply I will convert this uh, delta connected load from delta to star. Okay, after I convert from delta to star, what will happen? Simply this will become something like this, right? Okay, I will not be able to draw it unfortunately. So plus minus here will be there, minus plus, minus plus, and this load also will be converted into star load, right? So now, right, if this load is converted into star load, and we know that this will be Z delta by 3, correct? Z delta by 3, Z delta by 3. Okay, that is because it is in division. Yeah, it will be Z delta by 3. Now I can directly, because this is neutral, this also will be a neutral. I got my neutral point. So what will happen? This will be simply VAN. So what I will do is my line current IAN or IA will be equals to simply VAN divided by Z delta by 3. That's it. That's how simple it is. Okay, like this also you can find out without stressing, like without using this formula. Okay, this you will use when I have to find out the line currents, source line currents, source line currents. Okay, so yeah, that was about it. Whatever I've discussed, like simply convert this and solve using single phase method, that is also totally fine. So we will solve one question. A balanced ABC sequence is star connected source of VAN is equal to this. It's connected to a delta connected balanced load of 8 plus J4. Calculate the phase and line currents. So they are asking me to calculate the phase and line currents both. So if they, first of all, they are asking me phase currents. So phase currents means that I have a load here, I have a supply here, plus minus, then plus minus, VAN. So this is VB ABC, right? This will be VBN, this will be VCN. Z phase, so this will be 8 plus J4 and mm, 8 plus J4. Okay, so these are my basically line currents and voltages. So now what we can do is just hold on a second. We can sorry, this is not this is not connected. My load is delta connected actually. Sorry, load is delta connected. So if load is delta connected, ignore my drawing. Okay, please ignore my drawing. So the load is delta connected, this will go here and this will go here. Okay, so first they are asking the line phase currents. So phase currents I will calculate. So what I will do is I will convert this, right, line voltage into phase voltage. So what will be VAV, because this will be my phase voltage, right, VA and B. Okay, so my VAB will be root 3 times the phase voltage 100, so it will be 100 root 3. And what will the phase angle? Phase angle, it will lead the phase voltage by 30 degrees. Okay, so it will lead by 30 degrees, so this will be 10 degree plus 30, that is 40 degrees. This will lead by 40, 10 degrees plus 30, that is 40 degrees. So from here I can directly calculate the phase current. IAB will be VAB divided by Z delta. So this will be VAB divided by Z delta. So Z delta will come out to be like VAB is root 3 times this 100 root 3 angle 40 divided by Z delta. Z delta is 8 plus J4. Okay, so this value will be 173. This value is 173.2 angle 40 degree divided by 8 square plus 4 square under root 8.944, 4 divided by 8 tan inverse angle 26.56 degrees. Okay, so plus 40, 13, so this angle will be 13.44435 degrees, and this will be 173.2 divided by 8.944, so 19.365. Okay, so this will be the current, phase current. So what about the other phase currents? So other phase currents will be very simple, right? So BC, just copy the B over here and write the other term. BC will be equals to V BC divided by Z delta, which will be like the amplitude will be same, the phase will be shifted by 120 degrees, it will lag, so minus 120. So it will be, if I subtract minus 120 here with this value 13.435 minus 120, this will come out to be 100 and minus 106, right? Okay, this will be negative, this is positive. Just I'm checking if I'm doing this correctly. Yes, minus 106, minus 106.565 degrees. What about I? Again I will write I CA, so C will come here. Okay, and other one will be copied, so ICA will be again V CA divided by Z delta, which will be equals to 19. Amplitude will not change, 19.365 angle. Now it will lead the initial current by 120 degrees. So this will be 13.435 plus 120, 133.435 degrees. Okay, so this will be the uh, value basically. This will be the value. Okay, now what about the phase currents? So either you can use this formula, okay, but I have told you don't remember this formula. So what you will do is you will convert this star into delta and then calculate the phase currents, then calculate the line currents. So if I convert this star into delta, so my load now will become, sorry, if I convert this delta into star, so my load will now become, this load will be, here it will come, this will be one of the load, this will be the other load, and this will be the third load. Okay, so this will connect here. So here, right, if I'm converting from delta to star, so that means it is division. So the formula that I will use is Z1 Z2 divided by division, right, Z1 plus Z2 plus Z3. So ultimately what will happen is it will be Z delta divided by 3. Okay, so this will come out to be 8, what was the impedance, 8 plus J4 divided by 3. So 8 plus J4 divided by 3, here also 8 plus J4 divided by 3 divided by 3. Okay, so now I can directly basically calculate the currents, right? So neutral, it is a balanced load, so neutral can be connected. Again, I can write the equivalent single phase equivalent, right? So it will be simply a single phase equivalent will be, this will be VAN, this will be the load, and this will be my IA current, right? The line current now. Okay, so this is my IA current, that is what I'm interested in. So all this hassle I'm doing just so that you don't have to remember that formula, right? I don't want you to remember everything. Okay, so this will be the impedance 8 plus J4 divided by 3. Okay, so IA will be equals to VAN divided by 8 plus J4 divided by 3. So 8 plus J4, right, is okay, I have not written, I have written it. So 8 plus J4 will not change obviously, just a multiplication by 3 will come here with respect to the 10 100, right, 110, I guess it was 110, or what was it, 100 only. Okay, so this will be divided by 3 is also there, so 3 into 100, what is the angle, angle will be whatever is the VAN angle, VAN angle is 10 degrees, so this will be 10 degrees. Okay, so from here, just hold on, from here my current, right, line current, this will be, I will just quickly calculate this, 100 divided by 8.944 into 3, so it will be 33 point something. Okay, 33.54. What will be the angle, angle will be 10 minus 26.56, so this will be minus 16.56. Okay, this will be the phase A current. What about the other phase currents? Okay, the other phase currents will be just IB will, again what, IB will lag phase A by 120 degrees, so it will be like amplitude will be same, but it will lag by 120 degrees, so I have to subtract another 120, so this will be minus 136.56 degrees. IC will lead by 120 with respect to IA. So it will be 103.44 degrees. Okay, so what is the shortcut? Shortcut is basically another shortcut is like if you know my phase currents, what you will do is the line current will lag the phase current by 30 degrees and the amplitude will increase by root 3 times. So that is what is written over here. Okay, so if you don't want to, if you want to remember this, you can directly apply the formula. If you don't want to, you can use this simple conversion. Okay, so that was the solution of this particular question. Now let's discuss about another type of load, that is balanced delta load. Again, same thing, right? I will not discuss again. I will not discuss the same thing again. Like if I have delta connected load VAB, like what will be the, how do I sorry, this is not balanced delta, sorry, it is balanced delta to star. Okay, if it is balanced delta to star, that means the easiest method would be, if I want to calculate the line currents, what will I do? I will convert this star to delta and I will calculate the line currents. So for line currents, if I have to calculate the line currents, what I will do? I will convert my star to delta impedance. Okay, load I will convert from star to delta. So I will be easily able to find out the line currents. What will be the line current? It will be simply VAB divided by whatever the delta impedance, equivalent delta impedance. In our case, it will be what? It will be 3 into star impedance, right? 3ZY. If I have to calculate the phase currents, now things will be a bit different. So if I have to calculate the phase currents, how will I calculate the phase currents? So phase currents, if I have to calculate, so there are two ways to go about this phase currents, right? So either what you can do is, either you can convert this delta into its equivalent phase source. So how do I convert? So I remember that if I have a delta source here, if I have a star source here, okay, and I have a neutral here, and I have another source here, right? Another source here. So whenever I calculated the VAB, what was happening? The equivalent VAB, right? This VAB was coming out that it is root 3 times the initial voltage, this V angle 0, root 3 times V and plus 30 degrees, correct? Now let's say if I change this, now my VAB, let's say, is V angle of 0 degrees. Now if I want to go back to my star, equivalent star, so how will I do? So if I have to go from star to delta, what I did, I added angle of 30 degrees and multiplied by root 3. So if I have to go from delta to star, what will I do? I will subtract angle 30 and I will divide by root 3. Subtract angle 180 and I will divide by root 3. That is the only thing that we will do. Okay, so that's it. So same thing, let's say if I have to find out the phase currents. So phase currents, how will I find out the phase currents? So as I am comfortable more in star, if I have to find out the phase currents, what I will do, I will convert my source from delta to star. Basically my VAN will be VAB divided by root 3 angle of minus 30 degrees. Okay, that's the only thing that we have to take care of. Everything else is sorted. So these are the conversions. Basically I don't want to go, I will just solve with using this method, right? This equivalent method, that is the easier method, because in question you will be asked a balance, like you will be asked a balanced load only, you will not be asked any like unbalanced load. Okay, you will not be asked any unbalanced load. So this is the last question of the textbook. Next we will solve the gate PYQs. So like I want you to try out. So please pause the video and try out this question. This is the first question. This is a gate question. This is an unbalanced load, but trust me, this will be easier question. Okay, if gate has asked unbalanced, it will be very easy question. And this also came in gate recently only, and this also is a gate question. And this is the last question. So try it out by yourself, and then I will solve all the questions. So let's solve this question. A balanced star connected load with a phase impedance of this is supplied by a balanced positive sequence delta connected load with its line voltage as 210 volts. Calculate the phase currents. So I have a balanced delta connected load here with the line voltage. So this line voltage is 210 volts. Okay, and I have a star connected load, and they are asking me the phase currents. They are asking me the phase currents. Okay, so if they are asking me the phase currents, it is difficult, right? Calculating the phase currents is difficult. What I'll do, I'll convert this delta load into delta source into star source. So this will be here 210 divided by root 3, and angle will be phase shift because they have not given me any angle. So initially I will assume this as reference. So this will be uh, actually they haven't even asked us angle, but still we will calculate the angle. This will be minus 30, and I will have B phase over here. This will be 210 divided by root 3 angle. Uh, this will be minus 150 210 divided by root 3 angle. This will be plus 90 degrees. Okay, so this will be my star connected load basically, and star connected source basically, and my star connected load is already here, right? Already my load is star connected, that is 40 plus j 25. So this is my, just ignore my drawing. Okay, my drawing is really bad. So this is my star connected load. I can not this will not connect it. This will connect here only. So this is my zy, zy. So my zy equals to 40 plus j25 ohms. So this will be so right, I can directly convert this single phase, right? Single phase I can connect the neutrals. So basically my phase current I phase will be what? This 210 divided by root 3 angle minus 30 degrees divided by the zy. Zy is 40 plus j25. So the values will be, this value will be 40 whole square. Okay, I can take common 5. So if I take common 5, right, this will be 42 divided by root 3 angle minus 30. This will be 8 plus 5 j5. This will be equals to, so now if I calculate 8 square plus 5 square whole under root, this will be if I multiply into 42 divided by root 3, so this will be 2.57. And what about the angle? So angle I have to calculate. Angle will be, this is 5 divided by 8 tan inverse, and minus is there already, so minus 30, so minus 62. Okay, this angle roughly comes out to be minus 62 degrees. And the other, what will be the other phase current? So this will be the current of the phase A. What about the other phase currents? So this was A, this was B, right? This was B and this was C. So the other phase currents will, the amplitude will be same, just the phases will be different. So this will be IB. IB will be equals to 2.57. It will lag by 120. So minus 120 if I do, so it's almost equals to minus 182. Okay. Either I can subtract 120. Yeah, this will be minus 182. 182 182, yeah, 182 degrees. And what about the other phase current? other phase current will be IC. IC will be it will lead by 120. So I will add 240. That will be 58 degrees. Okay. So IC will be 58 degrees, IB will be this. So these are the phase currents that they have asked. So these kind of questions can get asked. Now let's solve the gate PY question. Okay. So although it seems like it is a delta connected, like it is a unbalanced load, but still you will be able to easily solve it. Okay. So let's solve this question. So like very basic question. So unbalanced load is given, balance supply is given, but unbalanced load is given. You don't have to worry about this. Okay, you will be able to solve using the balance concept. So in gate, if some three phase question will come, question will be on the easier side only. It will not be on the difficult side, not be on the calculative side. So here they are telling me that a three phase balance voltage is applied to the load. Load is like unbalanced and phase sequence is RYB. So this is my R phase, this is my Y phase, this is my B phase. Okay, the ratio of magnitude of IR over magnitude of I, so ratio of magnitude of IB over magnitude of IR. That is what we have to find out. We have to find out the magnitude of IB over magnitude of IR. So what is IB? If I notice IB, right, IB is actually equals to the summation, like if I apply KCL at this node, it will be IB plus IR plus IY equals to 0. So my IB is actually equals to minus IR plus IY. Okay, so IB is minus IR plus IY. What is IR and IY? So my IR is equals to what? IR is this phase voltage divided by the phase impedance. So phase voltage, this is neutral, right? This is neutral. So it will be VRN divided by the impedance, that is minus J10. IY will be what? IY will be V. This will be Y actually. This will be Y and this will be B. Don't get confused. Okay, don't get confused. It follows RYB sequence. So this will be Y and this will be B. So it will be V Yn divided by plus J10. Okay. Now what is VRN and VYN? They told me that it is a balanced three phase supply. So my assumption is I will assume an initial reference. So I will assume VR to be reference. So it will be V angle 0. So my V, then after this, what phase sequence I will follow? I will follow VYN. VYN will be V angle minus 120 degrees and VBN will be angle V plus 120 degrees. Okay. So VRN, YN, VBN is all these values. So simply just put the values. And you will get your result. So your IR will be what? IR will be equals to VRN, that is V angle of 0 divided by J10 or minus J10. So this will actually be V by 10 into angle of plus 90 degrees. Okay. Or I can directly write this as plus J V by 10. Now what is my IY? IY will be V angle of minus 120, divided by plus J10. V angle of minus 120 divided by plus J10. Okay. So this will be equals to basically V by 10 angle and another minus 90 will get added. So this will be minus 210 degrees. This will be my IY. And what will be my IB? My IB will be the negative of these two, right? So J V by 10 and plus V by 10 angle minus 210 degrees. Okay. So this will be minus sign will be outside, V by 10 angle 1 angle 0, 1 angle 90 degrees plus 1 angle minus 210 degrees. Okay, from here you can simply calculate these values. I can calculate these values, right? So this value will be what? This will be like, this will be j only, this will be j, this will be minus v by 10, and this value, right, cos of 210 is minus 0 point, that is root 3 by 2, and sine of 210, right, sine of 210 it will be plus 1 by 2, j 1 by 2. So this will be minus v by 10 minus root 3 by 2 and plus j 3 by 2. Okay, so I can take common here, root 3 by 2 minus root 3 by 2 I can take common. Okay, so this will be v by 10 into root 3 divided by 2, this will be 1 minus j root 3. Okay, this is my IB, this is my IB. Now what do I have to calculate? I have to calculate the magnitude of IB over magnitude of IR. So magnitude of IB over magnitude of IR, magnitude of IB over magnitude of IR. So magnitude of IB will be what? So from here I can directly write that my magnitude of IB will be equals to v by 10 into root 3 into 4, right? That is the magnitude of, not 4, sorry, into 2. So, and what is the magnitude of IR? Magnitude of IR, if you see, it is simply v by 10 only. It is v by 10 only. Okay, so this will be v by 10 into root 3 divided by v by 10. So this will be root 3, that is 1.732. So 1.732 will be your answer for the question. So like, although the question seems difficult because it is unbalanced load, but if you solve with basics, right, whatever I have discussed in this lecture, you will easily be able to crack all the gate exam problems. So let's now move on to the next question. So this also came in gate exam only. So this is the next question. So here what we have to find out is, in the circuit shown below, a three-phase star connected load is connected to a balanced three-phase supply with phase sequence ABC. The star connected load has impedance ZA as 10 ohm, ZB is 20, and this is ZC is in ohms. I don't know what is the value of ZC, and it is an unbalanced load. So they are asking unbalanced load, but don't worry, you will be able to solve it. For which the voltage difference across the node N dash will be 0. So they are telling me that the voltage difference across these two nodes will be 0. For which value of ZC? What will be the value of ZC such that the voltage difference across these two nodes are 0? Okay, so if the voltage difference across these two nodes are 0, that means my N and N dash, right? N and N dash are at same potential. N and N dash are in same potential. That means if, let's say I assume I connect a impedance here, it does not matter. It does not matter if even if I connect an impedance, even if I connect these two wires, because they are in same potential, I can connect these two wires, right? Because they are in same potential, I can connect these two wires. So the current, right, here, let me assume a current IN, let me assume this current as IA, let me assume this current as IC, let me assume this current as IB. So the current IN will be equals to IA plus IB plus IC. Okay, that is what I know. Now if N and N dash are in same potential, that means even if there is some impedance, let's assume there is some impedance. So there is some impedance, the voltage drop is 0, V N dash is 0. So if voltage is 0, that means the current is also 0, right? If there is some impedance, if the voltage is 0, that means the current is also 0. So my neutral current will also be 0. My neutral current will also be 0, because if I assume an impedance here and the voltage across this, like both of these points are in same potential, so there is no potential difference across this impedance. So if there is no potential difference across this impedance, that means the current is also 0. That means the current is also 0. So I can simply apply this rule. So I can write my IA, although the load is unbalanced, it will behave like a balanced system. IB plus IC will be equals to 0. Okay, so from here I can directly write what is my IA. IA will be the phase voltage VAN divided by ZA. IB will be VBN divided by ZB, and this will be VCN divided by ZC. Okay, so this will be equals to 0. So like it follows, it is a balanced three phase supply, and the like connection is 100 root 3. So whenever this voltage is given, right, this voltage is actually line to line voltage. So phase voltage will be what? Phase voltage will be divided by root 3. So 100 angle 0 VBN. It follows the phase sequence of ABC. So this will be 100 angle minus 120, and this will be 100 angle plus 120. Okay, that is what it will follow. So now if I just simply calculate these values, so this will be 100 angle 0 divided by ZA. What is ZA? ZA is 10 ohms. VBN is 100 angle minus 120 degrees divided by ZB. ZB is 20 angle 60. 20 angle 60 plus 100 angle 120 degrees divided by ZC. That is what I have to find out, equal to 0. So will be a bit difficult. So this is 10 angle 0 degrees, right? This is 10 only. Yes. So this will be 10 only. 10 plus 100. This is 5 angle of minus 180. So this is actually getting simplified. This will be 100 angle plus 120. I can take it on the other side actually. Divided by ZC. So this I can calculate. This will be 100 angle 120. ZC will be equals to minus 5. This will be minus 5. So ZC will be this will be minus 180. So 100 angle minus 60 divided by 5. ZC will be 20 angle minus 60. Okay, so these kinds of phasor calculation will come actually. So whatever we have been doing, right, it is actually required. So if they are giving some unbalanced load, it will be easier only. It will not be very difficult thing. Okay, so 20 angle 60 will be the correct answer for this particular question. So let's solve this next question. So in this question, what they're telling us, that two balanced three phase loads are shown, okay, in the figure, are connected to a 100 root 3 supply. Okay, this is the line voltage, and given that Z1 is this and Z2 is this, and like it is a balance, so these are all same, these are all same. The ammeter reading will be what? So they are asking me the ammeter reading. So it is a like delta connected load, okay, and they're asking me the ammeter reading. So what I can do is I can convert this star into delta, because I have to find out the line voltage. So I'll convert this star into delta, right? I'll convert I have to find out the line currents. Okay, sorry, I have to find out the line currents. So in case of line currents, right, which are same. In case of line currents for star are same. Line and phase currents for star and star are same. Okay, if you remember that this is my source, so line currents for the star connected load is same. Correct. This is my load, and here whatever is the phase current, this is the phase current, and this is the line current. Both of them are same. So I will actually convert this whole load into star connection. So this is already in star. I have to convert Z1 into star. So I have to go from delta to star. So what formula I have to use? I have to use division. D, right? Division. Division means this is the division. Z1 Z2 divided by Z1 plus Z2 plus Z3. So all of them are same only, that it is Z1 only. So it will be Z1 divided by 3. very simple. So Z1 is 18 plus J24. So this will be 6 plus J okay 8. Six plus J8. Okay. So this is what my like equivalent uh, star connected load is. Now now what we can do, we can actually find out the equivalent impedance, right? So basically this Z1 I have converted into star, so this is also in parallel with Z2. So equivalent single phase load, right, will be this Z1 divided by 3 parallel with Z2. Okay, so Z1 divided by C is 6 plus 8J, and Z2 is also, I guess, 6 plus 8J only. So if both same impedance are in parallel, basically I divide by 2. So this will be 3 plus J4. So what they are asking me to find out the equivalent ammeter reading. So it is ammeter reading is the line current. So current, right, IA. So IR or IA, whatever the current they are asking, this will be the phase voltage divided by the phase current actually. So sorry, phase voltage divided by the phase impedance, right? So it will be V phase divided by Z equivalent, because my loads are like this, right? This is my Z equivalent, and this is my star connected load, right? Here I have star connected load. Okay, so basically I have to find out this line current, right? I can convert this single phase. So line current will be this voltage, phase voltage divided by the phase impedance. So this is my Z equivalent. Okay, so this will be what is V phase? So V phase will be like this is the line voltage, right? They have given me the line voltage 100 root 3. So this is the line voltage, but I have to find out the phase voltage. Phase voltage will be divided by root 3 100. So actually they are just asking the like current magnitude. Ammeter can only measure current magnitude, so I don't care about the phase. Okay, so this will be magnitude of 3 plus J4. So magnitude of 3 plus J4 is 5, so this will be 20 amperes. Okay, this is 5 actually magnitude, so 20 amperes will be the reading of the ammeter. Okay, so let's solve this next question. So in this question, like we haven't given a balanced delta connected load, RC series RC circuit. It is a balanced delta connected load, and we have like a balanced supply. Okay, and it has a line inductance. Considering the change in the supply terminal voltage with loading to be negligible, calculate the magnitude of the voltage across VEB. Okay, so if I draw the circuit for now, if I draw the load, so it is like a delta connected load, right? Because the phase A phase A and phase C is like phase A is here, and in between these two points, so in between these 2 points phase B is here, right? In between AB I have a RC circuit, between BC I have a RC circuit, between CA I have a RC circuit. Okay, AB RC, BC RC, CA RC. Okay, now uh, now what we have to do, it is a balanced delta connected load, so I will draw the load for now. I will draw the load. So I have a delta connected load here, so this will be RC, RC, ignore my drawing. Okay, RC and RC. So I have R XC here, minus JXC, minus JXC, and R minus JXC. Okay, so now what I can do, is I have a like this line inductance I have, right? This line inductance I have. Here as well I have line inductance. Here as well I have line inductance, and my supply is here. Okay, it is a, let's assume this is a star connected supply, so it will obviously be a star connected supply only. Most cases it will be star connected supply. Okay, so this will connect here, or this will connect here, and this will connect here. So now what we need to do is, they are asking me what is the voltage at this is my A point, this is my B point. So what is the voltage in between this A and B point? So actually, right, it will be very difficult for me to solve this, right? It will be very difficult for me to solve this. So there is a way out. What is the way out? Way out is everything is balanced. So let me convert this into star. Then let me calculate the per phase voltage across that equivalent model. And then if I multiply it by root 3, I will get my line voltage AB magnitude. Okay. So what do I mean? So if I convert this, right, into equivalent star, right, this will be ZY, this will be ZY, 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 and ZY. Okay, so I have a ZY, ZY, ZY here. So this will be here, the inductance will be here, okay, and this inductance will be here, and this inductance will be here. So ultimately, right, these AB points will not shift. What has happened is that only I have converted this from delta to star, and this AB voltage will be still same. So if I am able to somehow find out AN voltage, VAN, right? So my VAB will be what? VAB, magnitude of VAB will be root 3 times VAN. Okay, magnitude of VAB will be root 3 times VAN. That's it. That's simply it. So I can directly write here, right? So this is my equivalent star connected load. So what ultimately what we have to do? So this, it is a balanced load, right? As it is a balance, like this is also XL, this is also XL, this is also XL. As it is a balanced load, so this neutral are connected. So I can convert this into single phase, because multi-phase calculating all this will be very difficult for me. So I'll convert this into single phase model. So single phase model will be something like this. This will be plus JXL. Okay. So single phase model, if I write, this will be my VAN. VAN. This will be the XL inductance, JXL. Okay, and this will be my basically R and XC as well, because like what is the equivalent? So I'm converting from delta to star. So I'm going from delta to star. So I'm doing division again, right? So this is delta to star. So I will do division. Division means Z1, Z2 divided by Z1 plus Z2 plus Z3. Okay. So basically everything is equal. So it will be the initial delta by 3, Z delta by 3. Z delta is R minus JXC. So this will be R by 3 and minus J XC by 3. So this is my neutral point, right? So what are they asking? If I just somehow, like, this is my initial voltage, this is my supply voltage, this is my point A, this is my point A, okay, this is my point A, this is my point A here, right? So I can say that my what will be my voltage basically? What will be the voltage? So they have given me 415 volts. So with respect to what? 415 volt, whenever they give this voltage, right, it is always line to line voltage. Whenever they give any voltage, this is always line to line voltage. But this is a phase voltage, right? So it will be divided by root 3. So this will be 415 divided by root 3. So whenever they mention the voltage, unless and until specified, by default you will assume line voltage. So I will write here one point, key point, that by default, if nothing is mentioned about the supply voltage, assume line voltage. Okay, that is the assumption that you will take. So now it's very simple, right? I have to find out VAN. It will be what? Voltage division. So it will be basically 415. So this is angle 0 basically, the phase A. So 415 divided by root 3 into simple voltage division, right? So this will be R minus JXC divided by 3 into R plus JXL minus XC. Voltage division. Simple voltage division. That is what I am doing. So what is R, what is XC, all these we have to calculate. So I can directly see from here, my R is 15 ohms. So R will be 15 ohms. Okay, my XC is 1 by j omega c, 1 by omega c. So it will be 1 by omega is 2 pi into 50 into C. C is 212.21 microfarad. So into 10 raised to power minus 6. So this will be XC will be equals to, this roughly comes around I think 15 ohms. So 100 212.21 into pi inverse into 10,000, this will come out to be 15 ohms. 15 ohms. What about XL? So XL, right, will be omega into L. So it will be 2 pi into 100 into 2 pi into 50 into like frequency is 50 Hz, 31.83 millihenry, right? So this will be 10 raised to power minus 3. So this will be basically 31.83 into pi. So this will come out to be, XL will be equals to roughly 10 ohms. Okay, so I can replace all this here, right? So my value will be 415 divided by root 3 into, this will be 15, R is 15, XC is 15, divided by 3 is there, and R is again 15 plus XC, XL minus XC. XL is 10, XC is 15. So this value, right, this value will come out to be, all these I am calculating phase, right, my phase voltage. So my phase voltage will be 415 divided by root 3. I can take here 15 common, right? If I take 15 common, this will be 15 divided by 3, 1 minus j, and in bottom, right, I can take 5 common here, right? I can take 5 common. If I take 5 common, this will be 3 minus 3 minus j, yes, 3 minus j, yes, 3 minus j. So what will be this value basically? So this is 115 root 3 into 5 into, this will be under root 2, right? I guess this will be under root 2. Okay, yes, this will be under root 2, and this will be just calculating the phase voltage, plus minus 10 j5. Okay, just hold on, anything wherever I have done something wrong, this is okay, sorry, I messed up, right? This will not be just this, right? Sorry, I messed up. This will be R by 3 and XC by 3. I messed up here, sorry. So this will be actually 5 and this will be 5. So this will be 5 plus j5. I can take 5 common. Okay, so I can take actually 5 common. So this will be 1 plus j. So now what we have to do is we have to simply calculate the magnitude, right? Okay. Oh, sorry. 1 3 was already here, right? Sorry, 1 3 was already here, right? This 3 was already here. Okay, this 3 was already here, and I have taken 5 common. So what happens is that this becomes like I have to ultimately calculate the magnitude. Magnitude will be, this will be 1, and this is 1 minus j, 1 plus j. So magnitude will be root 2, root 2. So this will ultimately become 1. So your value will come out to be 415 divided by root 3. Okay, this is my phase voltage, but they have asked line voltage. So what will be the line voltage? I've already discussed that the line voltage will be root 3 times this. It is a balance system. Line voltage, I have to find out VAB. So VAB, right? VAB will be magnitude, will be root 3 times the phase voltage. So this will be root 3 into 415 divided by root 3. So 415 volts will be your answer actually. So it seems like, how is it the 415 volt answer? But 415 volts luckily is answer. Okay, so answer will be 415 volts. So this question was actually very good. So sometimes they do ask a bit like tricky question as well from this, right? What you have to do, you have to simply convert this into star, then you have to write down the equivalent. So good questions do come from gate exam from 3 phase, right? So recently also these questions came recently as well. Okay, so don't skip this topic. So yeah, that's it basically from my end. I hope you have enjoyed this lecture. If you did, make sure to hit the like button, and all the ECR friends, your class is done. From next lecture onwards, you don't need to see my face again. You will see Himanshu sir's face. Okay, so if you have enjoyed this whole marathon, this whole video, please make sure to hit the like button. Please make sure to comment down below if all the concepts are cleared. That really helps us out. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I am Anish, and today we will start with the lecture 6 of electrical machines chapter, that is prerequisites of machines. So from this lecture and from this onwards, only EE and IN people will watch. EC people, EC aspirants don't need to watch it. Okay, so yeah, today we will discuss mainly about per unit system. What is per unit system? Like we will discuss briefly. We will discuss it about comprehensively in power system analysis. Here we will discuss about it briefly, and also we will learn about electrical and magnetic materials, few properties of electric and magnetic materials, which is a very important topic for ESC aspirants. Okay, for gate aspirants, you just listen to me. Whatever I am saying in this particular section of the video, just listen to me. Don't have to stress too much like I have to remember this, remember that. No need to remember anything. Just whatever I will say, listen to me, because listening is important. Listening is important because later on I will actually do few numerical questions on whatever concepts I will tell you here. Okay, so that's why you must listen, but you don't have to take any stress that do I need to put this in my short notes for gate. No, you don't have to put this anywhere in your notes or something for gate. Okay, so let's start with per unit system. So what is per unit system? In per unit system, electrical quantities such as voltage, current, power, impedance are expressed in decimal fractions relative to a predefined base value. So there will be a base value. With respect to that base value, the per unit, like whatever, let's say I have a current that is 2 amperes. Okay, and let's say the base current will be assumed by me only. Base current is 10 amperes. So the per unit value of this current, right, IPU will be the actual value divided by the base value. So this will be 0.2. 0.2 PU, we write it PU. So it is unitless quantity. It is a unitless quantity. And your first question would be, sir, why do we actually convert? What is the need of conversion? So the conversion actually, you will understand this more better in power system analysis. I will just give you a brief. Let's say I have a transformer in the, like this is my generator. Okay, 100, let's say some 220 volt generator, 50 hertz generator. Then I have a transformer here. Okay, if you don't understand the drawing, ignore it. Okay, don't understand the drawing, ignore it. I have a transformer here, right? Let's say this is like some step down transformer. So this is 10 is to 1 step up transformer, 1 is to 10 transformer. Then this is my transmission line. Okay, and in the transmission line, again after that, in the distribution side, I will have a step down transformer. Let's say 1 is to 10 transformer. And then here I will have a load, right? Load will be connected here. Load. Okay, so this transformer might have some different rating. Let's say this is 100 kVA rating. Okay, and its impedance, like this transformer also will have some impedance, right? Let's say this is 10 ohm impedance, this is 200 kVA rating, this is 5 ohm impedance. So you will not be able to do the analysis of this whole line, right, of this whole power system. You will not be able to do the analysis. To do the analysis, what we do is we have a common number, fixed base, and we convert all these numbers in that fixed base and then do our analysis. Otherwise it will become very difficult and complex and tedious to do all the calculations, find out the currents and voltages. Okay, because this 5 ohm is respect to this 200 kVA, this 10 ohm is respect to 100 kVA. Okay, so it will be very hectic and difficult. That's why we have a system known as per unit value. Okay, in machines it is not that used, but basic concept of per unit will be used. That is, what is per unit quantity? You should know. Per unit quantity is the actual value divided by the base value, whatever base we will choose. So mainly we choose two kinds of base. One is V base, another one is the kVA base. These two base only we choose, and others we derive actually. So how will I find out the I base? I base will be what? So I know my I is equals to V into I equals to kVA, right? kVA rating is V into I. So I can directly say the I base will be equals to V base, sorry, kVA base, or generally we write it as MVA base, VA base divided by the V base. Okay, this is my I base. And Z base also, what will be Z base? Z base will calculate. Okay, Z base will calculate. So Z base will be what? So basically my my Z is equals to what? V by I. So it is V base by I base. So what is V base? V base is V base only. Correct. And what is I base? I base is kVA base divided by V base. kVA base so this will be equals to V base whole square divided by kVA base. So this will be my Z base basically. This will be equals to my Z base. So we just derive the base quantities for two values, and others we actually simply use this formulas, right? So sometimes this kVA base is also called as S base. Okay, here we have written S base, V base whole square divided by S base, and Y base will be just inverse of Z base, right? So we generally have two values, that is S base and V base, and from that we derive all the other values. Okay, now another formula we have this per unit conversion. Okay, what is per unit conversion? What do I mean by per unit conversion? So initially, let's assume that we had a base is SB1 and VB1, and now I have changed my base to SB2 and VB2. So now if I have changed my base to SB2 and VB2, and in this base I had some per unit value, right, XPU. What will be the value here? XPU1. What will be the value of XPU2 with respect to XPU1? So for that, what we have to do is like we have to equate. So what is XPU1 actually? XPU1 is X actual divided by the X base. And what is X base 1? That is XB1, right? XB1. And what is XPU2? It will be X actual divided by XB2. Okay, so I can directly write that my I can equate the x actual, right? Here, what is my x actual? X actual is equals to xpu 1 into xb1. And same here, right? Same here. My x actual will be equals to xpu 2 into x base. Now the thing is x actual will not change, like actual value of the quantity. That can never change, right? Per unit value will change depending on the base, but actual value of the quantity will never change. Okay, it will never change. So what I will do is I will simply equate these two. Okay, if I equate these two, my value will become, that is my xpu1 into x base 1 will be equals to xpu2 into x base 2. Okay, I'm just observing, is this lagging? Seems like it is lagging a bit. I guess now it is fine. I will just close few apps. Seems like it is lagging. Just close few apps actually. Give me 1 second. Now I guess it is fine. Should not lag anymore. Yeah. Okay. So I wanted to write my new per unit value with respect to the previous values. So my xpu new xpu2 will be equals to xpu1 old value into x base 1 divided by x base 2. So this is what is written over here, right? This is the same formula that is written over here. New per unit will be the old per unit, here old per unit into the old base divided by the new base. That's it. So no need to remember these formulas. You can easily derive these formulas, right, in the examination hall. It will not take you hardly, it will take you hardly 10 to 20 seconds. Okay. So like if you are experiencing bit of like you're not able to remember all this, you can always derive this, right? That's why I'm deriving in front of you. So these are the per unit values, and this is the only theory that is required for you in case of per unit values. So this is the amount of theory that is required. Okay. So now let's solve few questions on this. So this is the first question. For a given base voltage and base volt amperes. Okay. So VA is given. So S base is given, and my B base is given. Okay, V base is given and S base is given. The per unit impedance value of an element X is X, right? Per unit impedance of an element is X. What will be the per unit impedance value of this element when the voltage and volt ampere bases are doubled? Okay, if it is doubled. So if it is doubled, what is my, like, currently my XPU, like my ZPU is actual, Z actual upon Z base. So what is my Z base? Z base I just derived, it is V base whole square, VB whole square divided by S base, correct? So from here I can directly find out the value of, so ZPU is X in our case into Z base. Z base will be V base whole square divided by S base. This is equals to my Z actual. Okay. Now what we are doing, we are changing our Z base. So our Z base is becoming now ZB2, which is VB2 whole square, VB2 whole square divided by SB2 whole square. So not SB2, SB2. Okay. So this will be equals to VB2. VB2 will be VB2 whole square divided by SB2. So VB2 is what they have told me, that voltage and volt ampere both are doubled. Okay. So both are doubled. So this will be 2VB whole square. VB2 is 2VB whole square divided by 2SB. Okay. So this will be 2 VB whole square divided by SB. Okay. So this is my new Z base. So yeah, this is my new Z base. So I will use this, right? So my new XPU X or ZPU2 will be what? Z actual divided by Z base 2. So Z actual is still the old value. The actual value cannot change, right? Actual value will not change. So this will be x into V base whole square, x into V base whole square divided by S base divided by ZB2. ZB2 is this, right? 2V base whole square divided by S base. So 2V base whole square divided by S base. So it becomes x by 2. So my ZPU2 is x by 2. So it will be half, right? So it will be x by 2. So that is option A. Option A will be the correct answer for this question. Okay, this came in GATE 2000. So for machines, these kind of easy questions will mainly come. Okay, now let's go to this second question. Second question, we have a 3-phase 5 kilovolt system. What is the base impedance? So the base impedance is very simple to calculate. ZB will be what? VB whole square divided by SB, correct? So VB is the like rated values, so we will choose rated values, that is 5 kilovolt whole square. So this will be 5 kilovolt whole square divided by 5 MVA. So this will become mega actually, 5 megavolt. So 25 divided by 5, mega will get cancelled. So this will be 5 ohms. So 5 ohms will be your correct answer for the Z base for this second question. Okay. So now let's move on to the next questions. Like this easier questions will be only coming for machines. I'm talking about machines. In power system we study it a bit more comprehensively. There we will discuss more new things. Here that much knowledge is not required. So here we have a 25 MVA 33 kilovolt transformer. The per unit impedance is 0.9. The per unit impedance at a new base of 50 MVA at 11 kilovolt. So previously the MVA base SB1 was 25 MVA and VB1 is 33 kV. Okay. So my ZPU1, okay, in the case 1, this will be Z actual divided by, like I can use the formula, right? I don't want to use the formula, that's it. I just don't want to use the formula, that's why. So it will be Z actual upon Z base. Okay, so my ZPU1 is 0.9, so 0.9 into Z base will be this VB whole square, kilo square becomes mega, and this will be mega only, so mega will get cancelled. 33 whole square divided by 25, this is my actual value of the impedance. Okay, now I want to find out the new PU. So new PU will be ZPU2 will be Z actual divided by Z actual divided by the Z base 2. So what will be the Z base? Z actual is this 0.9 into 33 whole square divided by 25. Don't worry, the kilo square is mega, so mega automatically is cancelled. Don't worry about that kilo mega thing. Okay, and Z base 2 will be, the new base is 11 volt whole square divided by the S base, that is 50. So this will be basically 0.9 into 3 whole square and into 2. So this, right, this will be 0.9 into 9, 0.9 into 9 into 2. So 16.2 PU. So 16.2 PU will be the answer for this particular question, the simple base conversion. So these kind of simple questions will be asked. So this is the last question that we will do in per unit system, then we will move on to the theoretical topic. So here they are telling me that ZPU old is the per unit impedance on a S base, SB old and V base old. What would be the per unit impedance on the new power base and the voltage base? Very simple, right? So again we are equating the actual values. So my ZPU old will be what? Z actual upon Z base. Z base is what? Z base is V base 1 whole square or V base old whole square divided by S base old, correct? And ZPU new will be what? ZPU new will be Z actual will not change, actual value of the impedance of course will not change, and this will be VB new divided by SB new. This is whole square actually. So I can say here, I can take the ratio. So if I take the ratio, like I can easily use the formula, right? I can easily use the formula. I'm just not using it for your sake because I want you to solve in the exam like this only. I don't want you to remember formulas. So ZPU new, I'm just taking the ratio. Z actual will get cancelled. So ultimately this will be here this will be ZPU old, and here Z actual will get cancelled. This will be S base new divided by S base old into V base old whole square divided by V base new whole square. Okay. So my ZPU new will be basically like ZPU old into S base new divided by S base old into V old whole square divided by V base new. So option B will be the correct answer for this question. Very simple and easy to understand. So yeah, that is the change in per unit. How do I change like the impedance, like few students remember this formula, but I am telling you to don't need to remember. It will hardly take you 10 seconds. Okay, so it's up to you. Of course you can remember if you wish to. It's up to you. Now let's come to the next topic, that is electrical materials. So first we will discuss about electrical materials, then we will discuss about magnetic materials. So electrical materials can be bifurcated into mainly three components. Okay, conducting materials, magnetic material, insulating materials. Okay, so in electrical materials, conducting materials are the materials which allow currents to flow. So if I have a transformer, right, I have a transformer. So this, right, winding is used for what? Winding is used for the current to flow, right? So this winding will be made of a conducting material. Okay, what is the core used for? The core is used for the flux to pass. So of course for the core I will need a magnetic material. And what about for the insulating material? So insulating materials are those kind of materials which does not allow flow of current. So let's say I have a transmission line, right? Transmission line, and of course you will provide enough insulation like over the transmission line, because here there will be road, right? This is road and people will be walking here. So there should be enough insulation between this wire and the whatever the free space, so that current does not go to this person, right? It will, else he will be dead, he or she will be dead, right? So we have to provide enough insulation for this wires. So in those kind of cases insulating materials are used. Okay, so let's discuss about electrically conducting materials. So there are many types of conducting materials like copper, aluminum, silver, gold. I know you have heard about these materials. Okay, insulating materials. What are the insulating materials? So we have rubber, glass, oil, diamond, dry wood. So these are the insulating materials. So these are my conducting materials. Just one thing that you have to keep in mind for ESC is that the conductivity, like whoever has the higher conductivity will allow more electrons to flow. So conductivity of silver is actually the highest, of course, but its material properties are bit bad, so that's why silver is not used everywhere. Then the conductivity of gold is very good. Okay, so if you know that in semiconductors, in chips, right, in chips small portion of gold is used actually. That is not your normal gold, that is industry gold, that is used for semiconductors. Okay, then after that copper, conductivity copper is the highest. After that conductivity of aluminum is there. These are cheap materials, aluminum and copper, but of course conductivity is lower than gold. Okay, so whenever I will require good conductivity and cost is not an issue, so I will use gold. Okay, silver has some material drawbacks, that's why silver generally is not used. copper, whenever I don't have budget, my infrastructure is lower, so I have to use lower budget products, so I'll use copper or aluminum. Okay, this particular thing you have to remember for ESC. Okay, only that's it. So what are the properties of a highly conductive material? What should be the properties? The properties, first what property should be, it should have highest possible electrical conductivity. Okay, conductivity should be very high, just like copper, aluminum. These are excellent materials, and these have great electrical conductivity. Next property is low temperature coefficient of resistance. Why is it so? Why it should have low temperature of coefficient of resistance? So we know that any resistor can be written like this, right? R equals to R naught 1 plus alpha delta T. So whatever is the change in temperature, the resistance value actually changes. Now this is known as the temperature coefficient, right? This is known as the temperature coefficient. Now if this is known as the temperature coefficient, that means what? I, of course, if the resistor is more current is flowing, what will happen? It will heat up. It will heat up, so the temperature delta T will increase. If delta T increases, then what happens? My resistance will change, right? If this alpha is very large value, resistance also will change by large amount. But if alpha is very low, right, then alpha into delta T, even though delta T is very large, alpha is very low, let's say 0.01, then this difference, right, R will not change much. R will be like R plus some 0.01 R. The delta in R will be very low, and we want that. We don't, of course, whenever we are using a component, let's say I intended to use a component like 100 ohms in a circuit. So this is my circuit, this is ZS, and I intended to use this circuit in 100 ohm resistance. Now if the current changes, this resistance value changes to 99 ohms. Is that a good thing? No, right? Or is it changes to 102 ohms? That is not a good thing, right? If the current increases, the resistance value changes. So that will change everything. Whatever I had planned initially, that this voltage, this point voltage will be something, this point voltage is changing. So that is not good, right? So that's why we don't, of course, the resistance of temperature coefficient must be lower. Okay. Now, of course, the mechanical properties, it should have high mechanical strength and ductility, good drawability, reusability, and corrosion form resistance. So the material should resist oxidation and environmental degradation. So because it will be used in environment like transmission lines, right? Coppers are used transmission lines. So like the wire is just bare, right? Wire is bare. It is used on the atmosphere. So if it gets oxidized, then its properties like electrical properties will take a hit. Okay, that will not be a good. It will not be able to transfer the current smoothly. So of course it should have all these properties, mechanical properties. Okay, these are the properties about the conductive materials. Now these are the individual properties, right? How aluminum is made, how copper is made. So I'm not explaining you each and everything. I'm not telling you. Just go through this. For ESC aspirants, you should know what are the properties of aluminum, what are the properties of copper, individual properties, how is it used in electrical machines. Okay, what is corrosion resistance, like all those things. Okay, so this is the comparison. So this is the most important thing that you can put for ESC aspirants I'm talking about. So cost of copper will be higher than aluminum. Because copper will have higher conductivity than aluminum. Cross sectional area also it will take smaller than aluminum. Weight it will be heavier than aluminum, and corrosion resistance will be moderate here, and it will be highly corroded. Basically it will be oxidized, right? Aluminum can get oxidized to aluminum oxide. Okay, aluminum oxide, I guess I also have forgotten the names. Okay, except from bauxite ore. So this is known as the bauxite ore. Whatever the component is, I have also forgotten, right? Mechanical strength of copper will be higher. So this you can put in your short notes. Okay, of course these are just theoretical points. I have to explain this, that's why I am telling you. So no need to remember all these things. Okay, just no, I mean for ESC you need to remember all these things. That is what I mean. Okay, now there are few electrical carbon materials. So electrical carbon materials are used where moderate electrical conductivity with special properties like wire resistance and self lubrication are required. So electric carbon materials are also used in special cases. So these are carbon actually. And if you have ever studied DC machines, in DC machines we have brushes, right? The brushes. In DC machine we have brushes. Okay. In DC machines we have brushes. So in those kind of cases we use actually carbon. Brushes are actually made of carbon, because what happens is the rotor, right, rotor actually comes in contact with the brush, so it rotates, so there is bit of corrosion here, mechanical corrosion, not oxidation. So it needs a self lubricating material that can heal from this corrosion. So in those kind of cases we use electrical carbon material. So it is made for generally graphite and other carbon forms used in electrical applications like brushes in motors and generators. Okay, it has low conductivity than metals. Conductivity is lower than metals, but it is suitable for making brushes where controlled resistance is required. Okay, it offers smooth surface to reduce wear and tear. It has negative temperature coefficient, so if the current increases the voltage will reduce, that's why it has negative temperature coefficient. So yeah, uh, that is the only thing. The decrease in resistance ensuring the voltage drop across the brush remains stable. So these were the properties for brush. Now we have a few more materials like what is it, alloys, which are high resistive materials, which can be used as insulators or heating devices. Okay, which have high resistance. Like if you ever see in your heater, right, your heater is basically a resistor which can actually carry huge amount of current. So that resistance has a power loss of I square R, and this I square R is actually totally converted into heat energy, and that heat energy is used by your heater to provide you heat. That's it. Okay, that's how the heater is made. So we need a, like, we, how can I increase this heat energy? Either by increasing the current or by increasing the resistance. So I cannot, obviously I have a limit to the current, so what I will do, I will increase the resistance. How will I increase the resistance? So resistance is equals to rho L by A. Okay, resistance equals to rho L by A. So resistance equals to rho L by A, and so I will increase my rho resistivity, so my resistance also will increase. Okay, that's it. So yeah, so yeah, these kind of materials are nichrome, constanine, magnetic. Okay, so these are the materials that is used for the resistivity, like for use for heaters and all those things, heating devices where I need high resistance, where I will need high resistance. Okay, now let's come to the magnetic materials. So magnetic materials are like that will be used in transformers as well. So let's first understand few types of magnetic materials. So first one is diamagnetic materials. So what is magnetic material? Magnetic materials exhibit different behaviors when exposed to magnetic field. So if I have a field here and this material is there, right, and let's say this flux phi, magnetic field is there, flux phi. Okay, so how the fields will behave inside this material, that depends on what type of material it is. Okay, so first type is diamagnetic material. So what is diamagnetic material? Diamagnetic material exhibit weak and negative response to an external field. When placed in magnetic field, they develop a small magnetization in opposite direction to the applied field. So basically what happens is, if let's say this material is diamagnetic material, okay, if this material is diamagnetic material, that means that field will come and they will separate out, because it does not allow magnetic field to pass through it. So it will develop its own internal field that will oppose this field. That's it. Okay, and that kind of field is known as magnetization. Okay, so like this is known as the, what do you call, this is known as the magnetic susceptibility. So magnetic susceptibility is what? Magnetic susceptibility is the magnetization divided by the external field. So what is magnetization? Magnetization is the magnetic field produced by the material, in this case the diametric material, divided by the external field. So if the magnetization will be greater and external field will be lower, then this will be greater than 1. In this case the material develops a magnetization in the opposite direction of the actual external field. So this magnetization is actually equals to magnetic moment divided by the external magnetic field, that is H. Okay, so in this case the direction of M and H, direction of the magnetization and direction of magnetization and magnetic field will be opposite to each other, opposite. So if it is opposite, right, if I'm dividing two numbers, and let's say I have a vector here that is going in from this from left to right, right, I have another vector that is going from right to left. So if I take the ratio of these two numbers, what will happen? So basically it's like I am in the xy axis and I have some number that is here 2 and I have some number that is here minus 2, right? So it will be what, minus 2 by 2 or whatever the value is, so it will be something negative. So in this kind of cases, my susceptibility will be negative. For diamagnetic material, the key point is my susceptibility will be negative. That is written over here. So negative magnetic susceptibility. Why? Because the direction of the magnetic field and like magnetization and the external magnetic field are opposite to each other. So if I divide those two numbers vectorically, obviously it will come out to be something negative. Okay. So uh, I hope you have understood this point. And relative permeability is slightly less than 1. So relative permeability, formula for relative permeability is actually mu r equals to 1 plus xm. Okay, so as xm is negative, so mu r will be less than 1. Xm negative, so mu r will be less than 1. Of course xm can never go less than minus 1. Okay, xm can never go, like limit of xm, right, limit of xm will be always greater than minus 1. It can never go less than minus 1. Why? Because it can never generate a magnetic field that has greater moment than the creator. So creator is this external field, right? So this external field was here. Now the material in itself cannot generate a magnetic field as strong that can actually totally oppose this, and the magnitude is even greater than the external magnetic field. That is not possible. That is simply not possible. Okay, so that is what you have to understand. Okay, so yeah, that is so ultimately what happens, as mu r is less than 1, so your magnetic flux density reduces. That's why the field lines are very further away from each other. So flux density reduces, as density will reduce, field lines will be further away from each other. So your B will be equals to mu into H. B will be equals to mu into H. So it is basically equals to mu r mu naught into H. So as mu r is less than 1, so B reduces. So B reduces for the same magnetic field intensity, because magnetic field intensity will not change because it is a independent parameter. This we have learned in the first lecture itself. So this will not change actually. So if this does not change, so basically ultimately mu r is reducing, so mu r reduces, magnetic flux density reduces. That's why there is a gap between the fields. So external field is here, there is a gap here. Okay, now let's understand about the few examples of diametric material. Okay, few examples of diametric material. So these are few examples like copper, silicon, germanium, diamond, gold, superconductors. All these are diametric materials. So if I have a diametric material here, let me draw this material actually. Can I draw a cuboid actually? Yes. Okay. So let me draw a diametric material. So this is a diametric material here, and let's say there are magnetic fields. Okay, and this is vacuum and this was my diametric material. So once I will reach inside this diametric material, so not diametric, sorry, diamagnetic material, what will happen? The flux density will reduce, right? The B will reduce. B will reduce. So if B reduces, here field lines were very dense, but what will happen here is that my field lines will deflect basically. Okay, I am not able to draw. Okay, field lines will deflect. They will not be as dense. Okay, so that is the important point to note here. So this will be my magnetic field lines that move away from each other inside diametric materials. So here the field lines, actually this should be in more bigger text actually. The field lines diverge inside the magnetic material, making them appear as if they are pushed away because the magnetic flux density is lower. Okay, that is the important point here. So now let's discuss about paramagnetic material. So what is a paramagnetic material? So paramagnetic material are those material which exhibit weak and positive magnetization when placed in an external magnetic field. So they also exhibit a weak magnetization like diamagnetic material. They also exhibited weak magnetization, but here they exhibit a positive magnetization. What do I mean by positive magnetization? So positive magnetization basically means that my like xm is what, susceptibility is what, m vector by h vector, right? So if I have a material and if the magnetic field is in this direction, then the material also will develop an extra magnetic field that will be very weak in nature, that will be also in the same direction. So it will aid the field, it aids the field. So basically m, in this case m and h are in same direction. Okay, so if m and h are in same direction, that means that my xm will be positive. Although I know that m, right, magnitude of m will be very less than magnitude of h. Why? Because it has told it develops a weak magnetization, which is positive, but it develops weak. So magnitude of m will be very less than 1. So xm, the range of xm will be like, it will not be very high. Okay, it will not be very high. So my mu r is what? Mu r is 1 plus xm. So my mu r will be slightly more than 1 because xm will not be very large, very high value. Okay, xm will be very small value, small positive value, small. So my mu r will be slightly larger than 1. Okay, that is the difference here. So yeah, same thing, whatever I've written, same thing is written over here. So as mu r is slightly larger than 1, so what will happen? The magnetic field density will increase. Okay, so it will have stronger magnetic field lines compared to diamagnetic material. Paramagnetic field lines will be stronger than diamagnetic. So if I copy the same thing right here, copy the same arrangement. Now instead of diamagnetic material, I have paramagnetic material. So if I have paramagnetic material, what will happen is that if I have paramagnetic material, then the magnetic field lines, the magnetic flux density will increase. So the magnetic field lines will be more closer to each other. So it will be somewhat like this. Okay, they will be more closer. Like if I have more fields, right? If I have more fields here, So this will be more closer, this will be also more closer, more field lines will be there, right? More field lines basically, so it will be more dense basically. Okay, it will accommodate more field lines. Okay, that is the crux basically. So that was about the paramagnetic material. Now the comparison, like few examples of paramagnetic material are given here, like aluminum, platinum. You can go through this and visualization. The field lines will converge slightly within the paramagnetic material. So they will converge. They will not diverge. Previously they were diverging. Now they will converge, indicating there is attraction of the magnetic field, but it is a weak attraction. Okay. These are the differences between the diamagnetic and paramagnetic material. Okay, so diamagnetic material repel external magnetic field, paramagnetic so weak attraction. Okay, diamagnetic material has negative susceptibility, paramagnetic material has positive susceptibility. Both are very small, both are small actually, small. This is also small and this is also small. Okay, so superconductors exhibit perfect diamagnetism due to like, don't ignore this Meissner effect, ignore this, don't need to study. Okay, so these are the differences. You can go through this. Now let's discuss about ferromagnetic materials, and these are the materials that we will be using in our transformer core. So ferromagnetic materials exhibit strong magnetization due to permanent alignment of their atomic dipole moment. Okay, so what happens here in ferromagnetic materials, right? These are my diamagnetic materials where the field lines were actually separating out. In paramagnetic, still it was attracting. In ferromagnetic, all the field lines will be attracted and it will be very dense. So my mu r will be very greater than 1. That means what? That means whatever magnetization, whenever this ferromagnetic material is placed near a magnetic field, it develops a magnetization xm that is large, very large and positive. So my m, the developed magnetization, right, with respect to the external field will be very high, very large. It will develop a magnetic field that will be very large and it will be in the same direction. So m and h will be in the same direction and it will be very high, same direction. And my magnetic field magnitude of m will be very larger than magnitude of h. Okay, so that's why my xm will be very larger than 1, and if xm is very larger than 1, that means my mu r also is very larger than 1. Simple as, right? So very simple thing. So this is a property of ferromagnetic material, and where are the is found? These are commonly found in D block of the transition metals and F block of the lanthanides elements. Okay, I also don't remember, it is written over here. For ESA aspirants you can go through this. I also don't remember all these things. Okay, it is just written over there. So generally, right, generally the mu r value for ferromagnetic materials, mu r value generally lies in the range of 3000 to 5000. So these are used as a transformer core. And iron is a very good ferromagnetic material. Few elements are also mixed in the iron to improve it further. Okay, so that was about the ferromagnetic material. So in case of diamagnetic material, what happens is that there are few dipoles in the diamagnetic material which are totally, like, if I apply a magnetic field, the dipoles, right, will develop a magnetic field in the opposite direction. So initially, when no magnetic field is applied, the dipoles in the diamagnetic material are totally unaligned. Okay, dipoles are totally unaligned. As soon as I will apply a magnetic field, all the dipoles actually will align in the opposite direction, so that it will oppose the initial magnetic field. In paramagnetic material, what happens here? Also dipoles are totally unaligned, but as soon as I apply a external field, then the dipoles align in the same direction as the actual external magnetic field, so it supports the external magnetic field, so the magnetic field increases, that is the flux density increases. In ferromagnetic material, dipoles are already aligned, so as soon as I apply a magnetic field, what happens? It increases it more further in the same direction. Okay, in the same direction. So that's why the ferromagnetic material has strong alignment and it has more magnetic permeability. Okay, so you can go through, read through this, how the origin of ferromagnetism came. Okay, how it attracts magnetic fields. You can go and read through this. I will not explain. So let's discuss about another topic, that is the hysteresis loop and BH curve. Okay, so what is BH curve? So to understand this, let's basically understand a very basic thing. Okay, so let me take few states. So let me draw this. Okay, and let me take few states. Let me copy this. Let me copy this, and let me copy this. So the important fact is, initially let's say I have a paramagnetic material. Okay, and the paramagnetic material, you know, the dipoles are not aligned at all. Okay, they are just disjointed. So at t equal to 0, let's assume that I actually provide a magnetic field, external magnetic field in this direction. Okay, okay, this got deleted, sorry. So I provided external magnetic field in this direction. Okay, something, it's very weird. I provided an external magnetic field in this direction, right? So what happened is, of course, you know, dipoles will get aligned. So dipoles will be aligned here. Dipoles will be aligned. So as the dipoles have been aligned and is a paramagnetic material, so my magnetic field, of course, will also increase. That is fine. This, let's assume the dipoles get aligned at t equals to 5 seconds. Now let's assume at t equals to 10 seconds, I take out the magnetic field. So there is no magnetic field. So if I take out the magnetic field, will the dipoles be disaligned again? No, right? Once the dipoles have been aligned, I will need another external energy to disalign the dipoles. It's not like it will go back to its previous state. So as soon as I remove the magnetic field, the dipoles will still be aligned. The dipoles will still be aligned. And if the dipoles are still aligned, so still there is some internal magnetic field, right? Internal magnetic field in the material. Still there is some internal magnetic field in the material. So how will I remove this internal magnetic field? So I have to apply a magnetic field, external magnetic field in the opposite direction, so that the dipoles get disaligned again. Okay, so this internal magnetic field actually is known as, there is a term that is known as the residual magnetic field. This is known as the residual magnetic field. Okay, that is a difference here. So this actually is known as the residual magnetic field. Now if this is known as the residual magnetic field, so ultimately what we are doing, so initially I was here, I provided a magnetic field externally, so my internal field, magnetic field of the material came here. Now I want to make it, I want to make this magnetic field 0. If I go back and make the external magnetic field to be 0, the magnetic field inside the material will not go to 0. Actually I will need to provide another magnetic field in the opposite direction, so that I make the magnetic field totally 0. So this B is the magnetic field of the material, inside the material, and H is the external magnetic field intensity. H is the external magnetic field intensity and B is the magnetic field inside the material. So that's why this is known as the BH curve. Okay, so each term has a name. Each term has a name. So I will discuss about the name, right? So slowly let's discuss about the name. Slowly let's discuss about the name. So this, right, this kind of curve is also known as the don't laugh by the name. Okay, don't laugh by the name. This curve is also known by the vaginal curve. Okay, I will not explain you what is vaginal. Vaginal basically means it is new, something new. Okay, it is a new material. Vaginal basically means it is new. Okay, if you want to research more about it, Google it. Okay, new material. So it is a new material. So generally the BH curve for a new material looks something like this. Okay, like for a new material, what happens, initially the magnetic field will be 0. I mean the internal magnetic field will be 0, the dipoles will be disaligned, and of course no external field is happening. So as soon as I apply external field, it will reach somewhere here, saturation, right? Now, sorry, this whole thing is known as the BH curve loop, hysteresis loop. This curve is known as the vaginal curve. Okay, Why vaginal? Because when the magnetic material is new, dipoles are not aligned, then if I apply a magnetic field, I will start from 0 and I will go until here. Okay. As soon as I remove the magnetic field, external magnetic field, what will happen? My internal magnetic field will not go to 0. It will still somewhat remain somewhere, right? It will still remain residual field. It is known as residual. Okay. Still somewhat it will remain. To remove that, I will need to demagnetize. So how do I demagnetize? I apply a external magnetic field in the opposite direction. So this curve, right? This curve is known as the demagnetization curve. Demagnetization curve, to demagnetize whatever magnetization is present inside the material. So demagnetization curve. Okay. And as I demagnetize, or let's say this curve is known as the demagnetization curve, and one more thing is known as this point, right? This point is known as the retentivity of the material. What do we mean by retentivity? Retentivity basically means that even though my external magnetic field is 0, still the material retains bit of magnetic field inside it. Okay, so that's why this is known as the retentivity, and this Br is known as the residual flux. Residual flux. Okay, and as I now, as my magnetic external field is 0, as I provide a magnetic field in the opposite direction, HC, what happens? I reach to this point, and this point is known as the coercivity. Okay, coercivity. Coercivity. What do you mean by coercivity? Coercivity means the magnetic field, the amount of magnetic field that I need to provide in the opposite direction, so that the flux, residual flux goes to 0. That is, my dipoles are realigned again. They are not in alignment. Okay, so so they are realigned. Now if I keep on applying the external field in the negative direction, what will happen? Of course, again dipoles will be aligned in the opposite direction. If I keep on increasing, just hold on, if I keep on increasing my magnetic field in the opposite direction, what will happen? Dipoles will be aligned in the opposite direction, so they will be staying here. Again the same thing. Again, if I want to make it to 0, again I have to apply a external field in the opposite direction. Again I have to apply external field in the opposite direction. So this point is also known as the residual magnetic field, residual flux or magnetic field. And this curve, right, this particular curve, is known as the magnetization curve. Okay, this is known as the magnetization curve. So this curve is only for generally for ferromagnetic material. Okay, I gave you example of paramagnetic, but generally this BH curve, this is known as the BH loop. This whole thing, right, is a loop, right? This is known as the known as the BH loop of ferromagnetic material. Ferromagnetic material. Okay, so yeah, that was about the, this is known as the, this loop is known as the hysteresis loop of or BH curve. Hysteresis loop or BH curve. Okay, I hope you have understood. So whatever I have described, same thing is written over here. So retentivity is the residual magnetism. Even after removing an external magnetic field, the material retains some residual magnetization, that is known as the retentivity. Okay, significance, it determines how well a material remains magnetized even though without the external magnetic field. Now we have coercivity. Coercivity is known as the HC. HC is the strength of the reverse magnetic field is required to bring the magnetization to 0. That is, all the dipoles are misaligned. It indicates how hard it needs to be demagnetized, how hard it is to demagnetize the material. Okay, now saturation, the point where all domains are perfectly aligned. I cannot align it. Okay, when all the domains are perfectly aligned, I cannot align it further. Even though if I keep on increasing, even though I keep on increasing my magnetic field, external magnetic field, the dipoles are aligned, so they will not provide any like additional field, right? So that point is known as the saturation point. Okay, that is known as the saturation magnetization. And last point, last term is the magnetostriction. Okay, so what is the magnetostriction? So magnetostriction is the term in ferromagnetic materials that describes the change in size when subjected to a magnetic field. Okay, so under alternating field, materials expand and contract each cycle, leading to humming sound. So what happens, as I'm providing alternating field, so for t equal to at t equal to 0, my field is in right hand side direction. At t equals to 10 seconds, my field is in left hand side direction. I keep on changing the field direction. What will happen? The dipoles also will keep on changing the directions, right? And if dipoles keep on changing the direction, so inside the material, particles are changing the direction. Particles are moving around. So if particles move around, what will happen is that the materials size of the material will change. And now if the particles are moving around, there is actually what do you call that, there is collision between the dipoles. Okay, so just like this mouse and phone, right? If there is, sorry it became very loud noise. So if there is collision, they will sound, right? There will be some noise. So same thing is happening in a lower level. Okay, so what is happening, the dipoles are colliding with themselves. If the dipoles are colliding with themselves, so they will actually cause a humming sound. Collision between dipoles, so there will be a sound, and that sound is known as, that sound is like something like this, humming sound. So that happens generally in transformers where there is alternating magnetic field. So that is the property of ferromagnetic material known as magnetostriction. So there is a friction between the collision between the dipoles when there is an alternating field. Okay, these are the few terms. Now we have the last material known as the ferrimagnetic material. So what is ferrimagnetic material, also known as ferrites? So ferrimagnetic material is similar to ferromagnetism but with oppositely aligned dipoles of unequal magnitude. So what happens in a ferrimagnetic material, right? Ferromagnetic material, if I apply a magnetic field, initially all the dipoles are aligned along the direction of the magnetic field. But for a ferrimagnetic material, what happens is that the dipoles are present in both directions. They are totally not misaligned, they are in a pattern, but they are present in both directions. Okay, and so what happens, that the overall resultant magnetic field, right, is very small, very small. It is in the same direction as the external magnetic field only. So my xm is again positive but small. Okay, so they are used for reducing eddy current losses. We will discuss about eddy current losses. So ultimately what happens is, if they, as they are producing like very low amount of magnetization, so net magnetic moment of the material will be approximately 0. So approximately my mu r also will be 1 only. Okay, and now one more point is there about hard and soft magnetic materials. So what is a hard and soft magnetic material? So a hard magnetic material is very, like, the term hard means it is very difficult for it to demagnetize and magnetize. Okay, so if it is very difficult to demagnetize and magnetize, that means basically that I will need higher field intensity. Field intensity required will be very high. High, okay, to magnetize it. So to demagnetize also it will be very high. So the magnetic field will be very high. So that's why the BH loop will have larger area. So it will have larger area, okay, which will consist of large loss. We will discuss about hysteresis loss in the chapter 1. Don't worry. And for soft magnetic material, it will be very easy to magnetize. So that means I have to provide very low amount of magnetic field. So that's why the area of the BH curve will be very low. That is the only difference between the large and low. So generally our electromagnets, our electromagnets electromagnets are soft magnetic materials, and our permanent magnets are hard because they are very difficult to demagnetize, right? And like their magnetic field is fixed for permanent magnets, so that's why they're very difficult to demagnetize. Electromagnets are very easily magnetizable. So hard magnetic materials are the permanent magnets, and the soft magnetic materials are the electromagnets, because electromagnets the magnetization can be very easily changed. Okay, so that is the important point. So basically the magnetic field intensity, external magnetic field intensity for hard materials will be greater than the magnetic field intensity required for soft magnetic materials. Very basic thing. Okay, so these are the differences. If you see, coercivity will be low, high, retentivity will be high. So applications is also written over here. Okay, so now let's come to the last kind of materials, which is known as the, where is the this gone? Okay, this is here only. Okay, somehow this is gone, right? Just hold on. This thing is gone somehow. Just hold on. Okay, let me paste this. Okay, yeah. So last few things are left. So electrical sheet steel. So it is a transformer core material, silicon steel, which we use as a core. Okay. So why is it used for a core? I will discuss about it. These are the properties. These are used to reduce the eddy current loss, hysteresis loss. We'll discuss once we'll study about the core. Okay. And last we have the insulating materials. Insulating materials for magnetic applications. So what are the properties? So properties are, it should have obviously have high dielectric strength. It prevents the breakdown under high voltage stress. It should have high resistivity so that no leakage current will flow. Low dielectric hysteresis, that is like the BH curve is also low, so that the hysteresis loss is also low. We will discuss about hysteresis loss later on. It has good thermal stability. Even at higher temperatures, it should not break down. The material should not break down. Okay, and it obviously should be chemically stable. Okay, these are a few properties of insulating materials. Now let's do few questions and we will end our chapter 0. So which of the following properties are essential for core material in power transformer? Okay, so in power transformer, although we have not discussed, transformer is a magnetic device. Okay, so if transformer is a magnetic device, although I have not told you what is like power transformer, what is distribution transformer, but we know the transformer is a magnetic device. So if it's a magnetic device, of course the core material should actually be able to pass the magnet, pass the flux field lines. So the permeability should be very high, and the saturation should also the saturation magnetization should also be very high. So it should have high permeability. No, low permeability is cancelled. No, not possible. Low saturation magnetization, no. It should have high saturation magnetization. So the core material, right, does not get saturated by the field. So high permeability, low resistivity. Let's check. This can be the possible answer. High permeability, high saturation magnetization. Yes, these two properties are most important, right? Transformer. Although I have not explained to you what is a transformer and stuff, but you basic idea you have. The transformer is a magnetic device that passes the magnetic field, because we use the flux to link to the secondary coil. So there is passing of flux, so the core should have high permeability so that it allows maximum amount of flux to couple to the secondary coil. Also it should have higher saturation magnetization so that the material, so that the core does not get saturated. Okay, so that the core does not get saturated easily. So high permeability means it easily allows flux to pass. And high saturation magnetization basically means that it does not saturate very easily. Okay, does not saturate. Even if the flux is very high, it does not saturate, right? Should not saturate. The core should not saturate. The core should work, as the transformer action will not happen. In which of the following magnetic material the net magnetic moment is 0? diamagnetic, antiferromagnetic, ferrimagnetic, paramagnetic. So in antiferromagnetic, actually the uh, net dipole moment is actually zero. Okay, in antiferromagnetic. Okay, I have not discussed about antiferromagnetic, but briefly, if you see here, I forgot to discuss that antiferromagnetic, right? In ferromagnetic, in ferrimagnetic material, dipole moment still will be there, very small, smaller net dipole moment will be smaller but non-zero. But in antiferromagnetic, what will happen? The net dipole moment will be totally zero. Okay, in antiferromagnetic, I will write here antiferromagnetic. I forgot to discuss antiferromagnetic. The net dipole moment will be zero. Okay, you can see from the diagram as well. Okay, net dipole moment will be zero. There will not be any dipole moment. So antiferromagnetic are those materials in which the net dipole moment will be zero. Okay, so yeah, what should be the characteristic shape of hysteresis loop for core material of a transformer? So for a transformer, right, the flux is alternating in nature. So if the flux is alternating in nature, so it should have soft magnetic material, right? Because my flux, right, transformer, the flux is alternating. So if it's alternating, so the sign will keep on changing, so direction of the field will keep on changing. So I should have soft magnetic material. Soft magnetic material. So if I should have soft magnetic material, that means the curve should be very short and tall. Okay, tall and narrow basically. So tall and narrow. So it will be tall and narrow. Narrow means like the width is very small, it is very tall. So tall and narrow. Option B will be the correct answer for this question. And with this, we have ended our chapter 0. I hope you have enjoyed the journey. If you did, make sure to put a comment below the video and like the video. And of course, from the next video onwards, we will start with the chapter 1, that is the like very important chapter, transformers. So we'll discuss about transformers, we'll discuss about testing losses of transformers, we'll discuss about core materials, we'll discuss about equivalent circuit, we'll discuss about phasor diagram of transformers, we'll discuss auto transformers, single phase, three phase transformers, all those things we'll discuss. So I hope you will enjoy the journey. So yeah, that's it basically from my end, and I will see you in the next lecture. Until then, happy learning.